Hello guys, welcome to this video. In this video, I'll try my best to introduce the concept of modular groups and how the fundamental domain or the fundamental region is defined for the modular group, and I'll try to cover the mathematics at a fairly rigorous level. I mean, just the modular groups, and of course, modular group is a topic in advanced mathematics, which has a lot of applications in theoretical physics, and I mean it's a fairly advanced topic. I won't say it's particularly difficult to understand at a basic level, but to get a good understanding, a really good understanding, a really deep understanding, it takes a lot of time and effort on your part. Plus, what I noticed was that when I was learning about modular groups and modular symmetries and modular forms, what I noticed was that there was especially for the beginners, there was no well defined, I mean, there was no good literature on the internet that I could find. I mean, there are a lot of papers you can find on archive and all, papers on modular symmetries, and especially the application of modular symmetry on some particular problem in physics, in standard models, say flavor problems or whatever. But I couldn't find any good document or PDF or any good resource or material on the internet that introduces the concept of modular groups to the beginner. I mean, there are some, but they are, the way they are explained, it takes a lot of effort on your part to make sense of it. It's not simple, which is a good thing. I think it's a good thing than to have everything fed to you. But sometimes it might feel frustrating because a lot of things are not well defined, and you need to do a lot of you can get stuck on some problem for a very long time, which is a bad thing if it's a very long time, because it will be a waste of your time. Because uh, I mean, because some things are not defined clearly, and I had to do a lot of reading on my own, and I had to uh, consult a lot of websites, and talk with a lot of experts in the field to get to actually understand the real concept. So that's why I made this Google Docs Gold document. I'll not share this right now. Maybe I will in the future, if depends. Maybe I'll write an article out of it and publish, whatever. That remains to be seen. But yeah, in this video I'll discuss. I will try to explain introduce you to modular groups uh, in a simple yet rigorous way, and I'll try to not do the mistakes which I found in most websites on the internet. If you want to learn modular groups, especially this video is especially for physics and math students, physics and maths undergraduates, who because if you want to do research in theoretical physics, or if you want to do research in mathematics, this will be very this will be important for you. I mean, of course, modular groups are not taught at undergraduate level for physics or maths, but I think you will find it important, I mean, interesting and even important in the future. And I think, of course, this video is not like my other videos, like popular science level videos. It's not meant for lay people, because there are some concepts, advanced concepts, which a person who is not formally trained in undergraduate mathematics or even high school mathematics might not understand. It's not possible for me to cover everything from the basics. So I will assume that you have basic knowledge about complex analysis. Basic. I don't. You don't need to know Riemann sphere, branch cuts. Not that. But yeah, the more you know, the better. If you know more, you can connect the dots. But yeah, that's not required. But at least you should have a basic knowledge in complex analysis, linear algebra, vector theory, and all, and of course, also group theory. I mean, at a basic level at least. I will discuss all the things which are important, specifically important to understand modular groups. But yeah, some basic understanding you must have. Otherwise, you'll not be able to make sense of some portions, because this is not like a popular science discussion video. There are some mathematics here. Still, I will try to keep it as simple as possible. So let's begin. Okay. First of all, what are modular group is a kind of group, and by group I mean group as we define groups in mathematics. It's like in group theory. We will discuss what that means in basic. But first of all, we need to understand why do we need to study modular groups? Because without knowing what a modular group is, we cannot define a modular form. And now, why do we need to define modular form? Because, I mean, what is the significance of modular form? Because see, modular forms are basically complex functions, which means they're just functions with a defined over a complex variable. I mean, they are functions of complex variables, and they are defined with in correspondence with the modular group, which we will understand why. That is the main part of the video. Anyway, modular forms, we'll just discuss how it is defined, the basic conditions you see that follow certain conditions near the end of the video. But the main point of the video is to understand modular groups deeply. I mean, at a fairly deep level. Modular form is even more advanced, and that is not the point of this video. Even I myself don't have a very deep understanding of modular forms, but I will try to share with you what I know about modular groups in this video. So basically, modular forms are important from the mathematics point of view because they combine complex analysis and group theory, and also many other areas of mathematics, including number theory and algebraic geometry. All these areas in advanced mathematics. Uh, so see, just like in case of real analysis, when we deal with real numbers, uh, complex analysis is a study of complex numbers. And see, in real analysis, we deal with the numbers lying on the one-dimensional real line. So since the line is one-dimensional, it's just a single line. There are only two directions from which we can approach a point, a point on this line. That is a real number, basically, either from the left or from the right. But complex numbers, see, what was the need of complex numbers? Because basically, complex numbers means they are of the form z equals a plus ib, where I is this imaginary number or the iota, which is under root I mean, I is this under root of minus 1, square root of minus 1. So why do we define I? And see, in the real domain, I makes no sense because under root of minus 1 is undefined. If we confine ourselves to real analysis, to real numbers, of course, this is not a real number. How can we define in real number? How can something be negative if it is under the root? Because that means I squared is minus 1. That means something squared is negative, which is not allowed in real analysis. That is why we needed to, mathematicians had to expand the concept, move to complex analysis from real analysis. And see, if you ask why, what was the need? Suppose if I give you this quadratic equation x square plus 1 equals 0, what is the solution? You see, x square equals minus 1, then x equals plus minus I, plus minus under root of minus 1, right? So you may say that this equation has no solution, and if you are in the real domain, then indeed this equation it has no solution. If you try applying the quadratic formula, you will see you will get a negative number under the root. But there are many such quadratic equations which the solution, there is a negative under the root, and some of these equations have important applications in real life, in physics. So, and yeah, complex analysis is not just a mathematician's play tool or something like that. It has a lot of, we use it everywhere in physics, in electronics, in signal processing, Fourier transform, in quantum mechanics, everywhere. So it's not just mathematics, just abstract mathematics. It is important in physics. So, and yeah, and so basically, real numbers, we just have a one-dimensional real line. For complex numbers, we have this one-dimensional real line. Let us call it the x-axis, and this a is called the real part of z, which we denote as like this, re in bracket z or z, whatever. Z is the complex number, and then we have this imaginary part, which is b. B is the imaginary part, and because b is multiplied by the imaginary, I mean by iota. And any complex number is the general representation is the real part plus the imaginary part times I. This is a plus ib. And so basically, this complex plane is a two-dimensional plane where the x-axis is the real line, basically all the real numbers, and the y-axis is contains all these b's, I mean all the real numbers multiplied by I. So, and any complex number, say we have a number 3 plus 4i, that means a is 3 and b is 4. So we can represent this number as the point 3 comma 4 on this two-dimensional uh, uh, plane. I mean, right? Because yeah, so because that is the complex plane. It's just like a Cartesian plane, but yeah, it means something else. Yeah, fine. So now, and yeah, we denote the upper half complex plane by capital H. That means all the complex numbers with y greater than 0. I mean the y coordinate, that is the imaginary part. I mean the y-axis, the y coordinate should be greater than 0. And see, it's strictly greater than 0. We don't include the 0. That means the real numbers, I mean the numbers which are strictly real. Of course, every real number is also a complex number with the imaginary part equal to 0, but we don't include that in capital H in the upper half complex plane. Right. So in a two-dimensional plane, now see, in the case of real number, we have a one-dimensional real line. So for any point, we could approach it either from the left or from the right. No other option. But if we have a two-dimensional complex plane, we can approach any point on the plane, that is any complex number basically, from any direction, because it's a two-dimensional plane, right? We could approach, follow my cursor. We could approach from here, we could just slightly change the angle from here. There are infinitely many possibilities if you think about it. So yeah, of course, complex analysis, that means it's a bit more complicated than real analysis, but it's much more interesting as well. All sorts of things in chaos theory, this Mandelbrot set and all these interesting patterns and fractals, they are all, Mandelbrot set is basically, it's on the complex plane, right? Now, yeah, so, and yeah, now we need to know what we mean by analytic or holomorphic. So if a complex function, suppose f of x is every function of x, where x is some real number. That's the usual notation. Similarly, f of z is a complex function where z is a complex number or a complex variable. So if a complex function is complex differentiable, then we say that in some region of the complex function C, then we say that it is analytic in that region or holomorphic in that region. And what do you mean by complex differential? That's basically just fz is complex differentiable if its derivative with respect to the complex variable z is finite and well defined. I mean, if ddz of fz is finite and well defined, but since z is a complex variable, we say it is complex differentiable. Basically, it's the same thing. I mean, yeah, the concept is the same, but if you actually do the mathematics, it's a bit different because you need to do some. I mean, it's a bit different from real, from ordinary differentiation because you need to take into account the real and imaginary parts and do it that way. But because here you're doing the differentiation with respect to z and not with respect to x or anything, right? So yeah, I mean, these are all basic complex analysis which you should know by high school. I mean, at least by first or second year of your undergraduate degree. So and of course it's not possible for me to go into detail here because we have a lot to cover, and the main point of this video is modular groups. So yeah, this was just to give a basic idea of complex analysis, and now we will discuss a bit about group theory, because what modular forms do is that they kind of combine these two different seemingly different areas of mathematics. That's group theory and what was this, complex analysis. Yeah, so group theory is the field of mathematics that studies symmetries, abstract symmetries. What do you mean by symmetry in mathematics? I mean, a symmetry is essentially a transformation. A transformation means simplest example, you have a number 2, you add 3 to it, you get 5. So 2 is a point on the real line, you add 3 to it, and this point becomes 5. In the sense, it is shifted 3 units to the right. So this 3 plus 3, or this you're adding 3. This is an example of a simple transformation. You could then, this is a simplest example on a one-dimensional line. There are possible transformations on this two-dimensional plane. You could transform some point to some other point by multiplying it with something, some matrix or some number, whatever. There are many possible kinds of transformation. So a symmetry is essentially a transformation under which the object being transformed remains unchanged. A transformation did not always be a simple shifting along a straight line. It could be a rotation. A rotation is also transformation, a bit more complicated. But every transformation has a mathematical definition. Rotation can be defined by a matrix. There is a matrix correspond which you multiply with the number. In the sense, we have to write the number as a column matrix. Maybe that depends on the exact situation. Then we can get the resultant matrix which we'll get, that will represent the number, the transformed number. So yeah, and we will see that it is actually rotated. I mean, yeah. So every transformation has a mathematical it can be defined mathematically. I mean, it is defined mathematically. In mathematics, it's defined mathematically. We cannot just see, visualization is important, but after some point, I mean, when you are going deep into abstract mathematics, suppose say n-dimensional space, you can visualize a simple transformation in 2D. But if it's but even in 2 dimension, some complex, if I give you some complex conformal mapping, you cannot visualize it that easily. You have to do the mathematics to see where the transform point lies. Even that is not simple. But if I give you say 5-dimensional space or any n-dimensional space, mathematically you can still compute or calculate where the transform point will lie. That is well-defined mathematics. That is on solid ground, solid foundations. But you cannot really visualize that. So yeah, at some points you need a well-defined mathematics. Only relying on visualization will not always work. Like if you think about the Heisenberg's formulation of quantum mechanics, that was matrix mechanics. This was just pure mathematics. Heisenberg didn't even care whether what atom looked like. He just did away with all the visualizations. He just said that I'm giving you my theory. If you use my theory, you will get the answers. You will get the measurables in quantum mechanics. You will get the energy state of the system and all these eigenvalues for which you will calculate. Schrodinger's wave mechanics is equivalent to Heisenberg's matrix mechanics. Both of them are correct. Both of them are equivalent formulations of quantum mechanics, and both of them gives the same answer. But Schrodinger took a different approach. He used this wave concept and he developed his wave equation. So there was still some scope of visualization in Schrodinger's formulation of quantum mechanics, this. But in Heisenberg's theory was purely mathematical. Yeah, if there is some scope of visualization, it's always good to go to walk that path, because at least I am a physicist, or a would-be physicist, an aspiring physicist, more than a mathematician. But in some cases, there is actually no scope of visualization. You have to rely on mathematics. That's what I'm saying. So it's always good to have a mathematical basis, a solid mathematical definition of a transformation, because not all transformations are simple translations or rotations that can be easily visualized, right? So yeah, a symmetry is essentially a transformation under which the object being transformed remains unchanged in some respect. I mean, of course, the object remains unchanged in some respect. I should have written this anyway, because okay, let's give an example. For example, mm, in some respect or in some aspect, whatever. So anyway, if I rotate an equilateral triangle by 120 degrees 3 times, so an equilateral triangle means the interior angles are 60 degrees, and you take one vertex, any vertex of this triangle, and the interior angle is 60 degree, and the corresponding the exterior angle corresponding to that vertex will be 120 degree, because 180 minus 60 is this 120 degree. So if I rotate this triangle by 120 degree, then basically I'm rotating it about one of its sides, the opposite side to this vertex basically. Yeah, like one of its sides. And then I do this 3 times. That means I rotate the triangle thrice through like about all the 3 sides. So basically if I do this, then I will get back to the original triangle. In the sense, before I started the rotation, the triangle, the orientation of the triangle, and after I end it, it will be same. I mean, it will look the same to me if I don't myself move. You see, if I do this transformation, this rotating the triangle, the equilateral triangle by 120 degrees 3 times does not change the orientation of the triangle. And so this transformation is order 3, because I am carrying this out, this transformation 3 times. And this is a member of the symmetry group of the equilateral triangle, because see, the symmetry group of any object is the group of all transformations under which the object remains unchanged. So this is just one example, but suppose say if I rotate the triangle by 120 degrees 6 times, then also it will be unchanged, because yeah, 3 times unchanged, again 3 times unchanged, 9 times, 12 times, all of these are members of the group. This is the simplest one, and this is just one member. And then there are many different other members also, different types of member as well. For instance, reflecting the triangle through a symmetry line. I mean, if you can just visualize, these are very simple examples, I'm not going deep into this. So if you just reflect it like this twice, then also it doesn't its orientation doesn't change. This I should use the word orientation instead of structure. So this is another element, and this is of order 2, because I have to reflect just 2 times. So this is also another element of the symmetry group of this equilateral triangle. So basically when we say that something, we always make these statements in physics and mathematics, something is symmetric under a group. So what do we mean by that? And this is what this group, as in group theory. So when we say something is symmetric under a group, what do we mean by something? In general, we say that this something could be some particular states in a mathematical theory that may or may not have some physical significance. So when we say that something is symmetric under a group, we mean that the elements of that group transform those states in such a manner that some quantity does not change, and this quantity is said to be conserved. Of course, it does not change under the transformation, so it is conserved. That means it is symmetric under the group. That means all the elements of the group, if we each element of a group is basically represents a transformation, right? So all the elements of the group represents those such transformations, or transform these states in such a way that something does not change, and that is conserved, that quantity is conserved. And see, this is basically the statement of Noether's theorem, in roughly loosely speaking, that every symmetry thus gives rise to a conserved quantity. I can give you a simple analogy. I won't say, of course, this is not a mathematically rigorous, not even a mathematical explanation, because Noether's theorem is not as simple. The statement may be simple, but it has a mathematical basis, and it's an extremely important and fundamental theorem in mathematics, and has a lot of applications in physics. But just to give you a feel, because the point of this video is not Noether's theorem. So yeah, we claim that for every symmetry, there is a corresponding conserved quantity. And we claim that time symmetry is associated with the conservation of energy. So I won't be proving this here, but I can give you a simple kind of, you can say, a thought experiment. So what do you mean by time symmetry? In very simple terms, it means that the laws of physics don't change with time. The weight of an object is its mass times acceleration due to gravity, both of which are constant, provided the object is at a fixed point in space, so that the acceleration due to gravity will be constant at that point in space, and the object is the same object, so its mass is also constant. So that according to the laws of physics, the weight is just m into g, that is mass into acceleration due to gravity, which we denote by g. Now, time symmetry means the laws of physics don't change with time. That means after 5 minutes also, the weight of this object will still be m times g. After 5 days, after 5 years, it will still be m times g. The weight of the object doesn't change with time, as long as we don't move the object, because in that case, the acceleration due to gravity will change, right? But let us assume that time symmetry does not hold. This is not the case. This means the laws of physics are changing with time. Maybe right now the weight is m times g. After 5 minutes, it is 2 mg. Then after 5 days, maybe it is 10 mg. Just an example, right? So that means when the weight is mg, it's the minimum weight, then it would take the least amount of energy if we lift the object up when its weight is minimum. But if we drop the object at a later time when its weight is maximum, say after 5 days, if we choose to drop the object when its weight is 10 mg, because the laws of physics are changing. Just a thought experiment. This does not happen. Then in that case, see, we used a minimum amount of energy to lift the object, but right now the object's weight is more. So if we drop it, it has a lot of, it has more energy, more potential energy, which will be converted to kinetic energy as it falls. So in that case, we get more energy than we use to lift the object if we choose to drop the object when its weight is maximum, or more than the weight when we lifted the object. Now, so of course we get more energy than what we put in. So this is a violation of the law of conservation of energy. Energy cannot be conserved if there is no time symmetry. Just a rough thought experiment. This is not a rigorous proof that time symmetry is associated with the conservation of energy, of course. Now anyway, back to group theory. Now in group theory, what is a group? Of course, in loose language, a group is just a collection of objects. But in mathematics, a random collection of objects is what we call a set. But not every set is a group. A group is a set. I mean, in mathematics, we have some, a set must satisfy some particular conditions for it to be called a group, to be a group, as in mathematics, as in group theory. So first of all, for any set to be a group, first of all, we should define a particular operation. Associated with each group, there is a single operation, and this is basically a mathematical operation. It can be addition, subtraction, multiplication, whatever. And we use the operation on the elements of the group. Suppose if the elements of the group are real number, and if this operation is addition, then say we take two real numbers from the group, say 2 and 3, and then 2 plus 3. That is what we mean. And star is just a general notation. This star could be anything, addition, multiplication, depends. That we have to define when we are defining a group. So group is a set with the operation star that satisfies the following 4 conditions. Number 1, the closure property, which means that if A and B belongs to this group or to this set, because right now we still have not proof if it's a group or not. So if A and B belong to the set, A and B are 2 elements of the set, and the operation is star, then A star B, we get C, then C must also belong to the same set. Number 1, closure property. Number 2 is identity, that is there must be an identity element or an element E belonging to this set such that A star E equals A for all elements in the group. That means if we use the operation, the group operation, on this identity element E and any element of the group, any other element of the group. Any other element means if we use E on E itself, I mean E star E, that is also E, then we get back that element itself. Then E is an identity. So an identity must exist in a group, and it should be unique. I mean, a group has a single identity, not more than one identity. All these are very basic level group theory. This can be proved, right? And for each element A, the third condition, there is an inverse element C such that A star C equals C star A equals E. This is also one more condition. And finally, for elements A, B, C in the group, associativity holds. That means A star, B star, C. I mean, you can just see this. As long as the order does not change, A, B, C, then does not matter whether we first evaluate B star C and then operate the result, use the operation on this result and A, or we do first evaluate A and B and then do that and operate it with C. Doesn't matter. It will be the same. So all of these 4 conditions must be satisfied. Only then we can call that set as a group under the operation star. All of these 4 conditions must be satisfied. And simple examples, for instance, consider the set of all integers. It forms a group because, and let us say the operation is addition. Simple, very simple example. So you take any 2 integers, let us say -2 and 3. So -2 plus 3 is 1. So -2 and 3 both are integers, both belongs to this set of all integers. And star is plus, so -2 plus 3 is 1, and 1 is also an integer. So C also belongs to the set of integers. So closure property is clearly satisfied. Identity element is present because it is clearly 0, because any integer you take, and this is plus, right? So any integer plus 0 will give you that integer itself. So identity element is 0, and there is an inverse element. For instance, suppose if we take 2 and then the inverse element is -2 also belongs to the group, to the set of all integers. So 2 plus -2, that is just 2 minus 2 is, or if we do the opposite, that is -2 plus 2, whatever, that gives us 0 and is 0, right? In this case, so inverse also exists. And finally, for A, B, and C in the group, yeah, this also holds. Any 3 integers, of course, this will hold. Now, the thing is that If we took the set of all positive integers, then would that be also a group? No, because in that case inverse would not exist. Say we take 2. 2 belongs to the group of all positive integers, set of all positive integers. 2 is a positive integer, but its inverse is -2. Yeah, 2 minus 2, it gives you 0. Fine, but -2 does not belong to the set of all positive integers in the first place. So the inverse does not exist within the group. That means the set of all positive integers is not a group, but the set of all integers is a group. Simple example. Now, this axiomatic definition of a group enables us to effectively study more abstract symmetries than the familiar shapes of polygons. Like I said, polygons, equilateral triangle, these things you can visualize, but more abstract, more complicated symmetries, for that you need some mathematical definition. Now, coming back to modular forms, they have wide-ranging applications in and beyond the field of mathematics, and what makes them so special is that they satisfy infinitely many hidden symmetries. Yeah, even today modular forms are not, they are being studied. We don't understand all the aspects of it, and it's expected that their study will reveal a lot of important secrets in mathematics as well as theoretical physics. Now, and not just that, the sheer richness of the theory of modular forms makes it much easier to investigate real world transformations, complex ones I'm talking about, complex transformations. I mean, not complex analysis, but I mean complicated transformations, not the simple ones that can be described by modular form. In physics, modular forms have made it possible to study various models of interaction of elementary particles. I mean, these CFTs, conformal field theories, which of course, which is of significant help in quantum field theory and string theory research. Presumably, most of the fundamental symmetries of the physical world can be studied using modular forms, which demonstrates why modular forms are so important in physics. Of course, I cannot go into the details of this because point of this video is to introduce you to modular forms from a mathematical point of view. Just know that they are very important in physics. They have a lot of significance in physics. How exactly that is, I can't discuss in this video, and even I don't know in detail, right? It's a PhD level physics. So yeah, general linear. Now that we know why do we need to understand modular groups, because modular groups are needed to understand modular forms. Now let us start our journey of understanding modular groups. For that, first we need to know what a general linear group is. Basically, we know what a group is, right? Now, general linear group is a group of degree n, is the set of all n by n invertible matrices. Now again, I will be assuming you know basic matrix theory, the basic ones. Yeah, I mean these things you should know even from high school mathematics. These basic matrix and determinants. And it's better if you know matrix. If I've studied matrix in a bit more detail, as in linear algebra and everything, eigenvalues, eigenvector, all these things. So anyway, general linear group of degree n is a set of all n by n invertible matrices, or invertible matrices mean matrices with non-zero determinants. I won't be discussing what a determinant is and why invertible means the determinant must be non-zero, because the inverse of a matrix must exist for a matrix to be invertible, and inverse is defined as the adjoint of the matrix divided by the determinant. So the determinant is 0, we cannot divide by 0, then the inverse does not exist and the matrix is not invertible. Or of course, so that means invertible matrices must have non-zero determinants. So basically, general linear group of degree n is a set of all n by n matrices with non-zero determinants, or the set of all n by n invertible matrices. And the operation is just ordinary matrix multiplication. Again, I'll be assuming you know how matrices are multiplied. They are not just as simple as multiplying two numbers, of course. And why does this set of all this kind of matrix they form a group? Because see, the product of two invertible matrix is again invertible. So closure property is satisfied. Why? Because see, again, there is a very basic theorem of about matrices, that the determinant of the, suppose we have two matrices A and B, and then we have determinant A. The determinant of A is say det A, and the determinant of matrix B is det B. And suppose if we multiply AB, just matrix multiplication, we get a matrix C. And let us say the determinant of C is det C. So if AB equals C, then we have a theorem that det A into det B equals det C. Now let us choose matrices A and B from this set of all invertible matrices. So that means det A and det B are non-zero. So det A into det B must also be non-zero, because if you multiply two non-zero numbers, you cannot get 0, right? The determinant is a number. So then det C, that means det A into det B, which is det C is non-zero. That means the determinant of C is also not 0, which means the matrix C also has a non-zero determinant, or the matrix C is also invertible. And of course, if we the product of two matrices has the same order, so the matrix C is also a n by n invertible matrix. So that means the matrix C, or the product of A and B, also belongs to this general linear group. Just showing that the closure property is satisfied. And matrix multiplication is of course associative, and the inverse of an invertible matrix exists by definition. It is invertible, that means the inverse exists, and if the inverse exists, then again, if we multiply a matrix with its inverse, we get the identity matrix, and that identity matrix is the identity element of the group, because any invertible matrix, I mean any matrix, if we just multiply with I the identity matrix of that order of n by n, then we get by the same matrix. So it's a very simple exercise to prove that this set is it actually forms a group, and this group is the general linear group, right? So, and why is it called general linear group? Because see, again, this will only understand if you know some basic linear algebra. The columns and also the rows of an invertible matrix, they are linearly independent. Basic vector algebra, I cannot explain this here. So the vectors or points that define are in a general linear position, in the sense, now linear position doesn't mean the line, a straight line or something like that. It's actually you see, you can also understand it like this, from the point of view of hyperplane. Just you can just take a reading, you can just read this, just take a screenshot if you would like to explore further, but I cannot go deep into this. It's already 30 minutes, and we're just, I mean, it's a lot more to cover. And yeah, the notation, if we define a general linear group over the set of real numbers R, over R means basically the matrices, the elements of the matrices are all real numbers. That is what we mean by over R. So, and this is again the group of course, the n by n invertible matrices of real numbers, and matrix multiplication is the group operation. Then this is denoted by GL, or general linear n comma R. N is the order of the matrices, and R is because it's defined over R. Similarly, if we GLV means it is the general linear group over the vector space V. What is a vector space? You need to understand, again you need to learn vector algebra and some basic linear algebra to understand what a vector space is. It's very important actually. Vector space is forms the basis of physics. You will need it everywhere in from quantum mechanics. Even before that, you will need that. So yeah, if you are here to learn what modular groups, probably you already know what a vector space is, right? And of course, a vector space means it will satisfy the conditions, and it has a well-defined dimension, and its elements are vectors, and they're identical in some aspect. And basically, if we're defining this over V, that means we already were specifying this n, right? And this R, I mean, that depends on the vector space. All this information is contained in V. So here we just write GLV, or we could also define it. I mean, this is the denotation, the notation of this general linear group. And now there is something called the special linear group, which is basically just a subgroup of the general linear group. I mean, it's basically the set of all these n by n matrices, invertible matrices, with the determinant 1. For general linear group, it could be any n by n invertible matrix with, any n by n invertible matrix. That just the determinant should be non-zero. That was the only condition. It could be 1, 2, whatever, just non-zero. But here we have a further constraint. The determinant must be 1. It cannot be just any n by n invertible matrix. We will only include those in the SL special linear group whose determinant is 1. Of course, they are of course part of the general linear group. Of course, the general linear group is the parent group, kind of the bigger group of the special linear group. So that is why we say that the special linear group, the notation is SL n comma F. It is the subgroup of the general linear group. Here n is the dimension of the matrices, and F is any arbitrary field, could be the set of real numbers, complex numbers, whatever. So now basically, if we have this, suppose we have a general linear group. So we took all the matrices from the general linear group. We took only those matrices from the general linear group with a determinant equal to 1, and we form a set called that we are claiming is the special linear group. But we have to prove that these few matrices with determinant 1 that we have chosen, individually they also form a group. That they also satisfy the 4 conditions. We have proven for the GL case, but we have to prove this here also. Only then we can say that SL is a subgroup. Only then we can say this is a subgroup of the general linear group of the same order and over the same field. Because subgroup means, first of all, it itself is a group, and then it consists of elements from a bigger parent group. That's why it's a subgroup of that group. But for that we need to prove that it's a group. It's easy to prove because again, in this set all the matrices have determinant 1. So if you take 2 matrices from this set and just multiply them, a into b equals to c, then determinant of a is 1, determinant of b is 1. So determinant of c is also 1, because 1 into 1 is 1, and that means c also has determinant 1. So c also belongs to this group. Closure property is satisfied, and the other 3 properties I have not it's a pretty simple exercise. See, associativity, inverse, and identity will anyway, it will be satisfied by n by n invertible matrices, by matrices with non-zero determinant. Any non-zero determinant matrix will satisfy identity, associativity, inverse, and identity, right? And yeah, here we are just considering only those with determinant 1, but yeah, they will also satisfy. So it's a simple trivial exercise to prove that the special linear group also forms a group. It actually is a group. Now we need to understand normal subgroups and cosets. See, first of all, for n to be a subgroup of G, say the group operation is multiplication. This means that n consists of some elements of G and is itself a group. This must also be satisfied, like I said for the special linear group case. That means these few elements of n, they individually they also must satisfy the four conditions, and all the elements of G are satisfying already because yeah, already G is a group we have assumed. So then we can say n is a subgroup. Now then n is a subgroup of G. But when is a subgroup a normal subgroup? If and only if for every x in G and for every y in n, xy equals to yx. That means commutative. By itself, it's not necessary. But see, this does not mean that G is an abelian group, because if for G to be an abelian group, every element of G must commute with every other element of G. But here all we are saying is that every element of G must commute with only those elements of G that are also part of n, that is every y. See, if y is in n, y will also be in G because n is a subgroup of G. But yeah, this is the condition for normal subgroup, but this does not necessarily mean that G is an abelian group. Because for instance, there is some element x in G and also x dash in G, but x dash is not in n. I mean, so x dash doesn't belong to n. So then x in, and say y belongs to n, then x y equals to yx must be satisfied, x dash y equals to y x dash must be satisfied for normal subgroup. But x dash equals to x dash x need not be satisfied for normal subgroup. But for G to be abelian, even that must be satisfied. If you get what I'm trying to say. We are not studying abelian group in the video, but think about this. If you are, especially if you're unfamiliar with group theory, this kind of thing, the more you think, the more you will get a good understanding. Okay, normals, yeah, whatever. Now this is how we define a normal subgroup. Now if n be any subgroup of G and x be any arbitrary element of G, nx is a right coset of n in G and xn is a left coset of n in G. But so this is what we mean by coset. So n is a subgroup, that means n is a set of elements and x is a single element, any arbitrary element of G. So nx basically, suppose simple example, suppose n is just a simple example, suppose n is this group, or say 1 2 3, and just a second, yeah, and let us say x is what, say 2. So then nx is what, just 1 2 3 2. I mean, actually nx means we are writing n star x, but here we assumed that star is multiplication, so just nx. So that means this will be, we will just multiply 2 with individually with each element, so that will give it 2 4 6. And if we do xn, then also the same thing, then the xn will just be this, right? I mean, just be this xn, yeah, then also it will be 2 4 6. So nx is the right coset and xn is the left coset. Mathematically we say that it is the right coset of n in G and the left coset of n in G. And if n is a normal subgroup, that is a special case, then the left coset and right coset are equivalent. Like in the example we considered, they are equivalent, because anyway in the example, our example was also simple, because we just any two integers, 2 3 4, all these are integers, right? So in any integers, if you just multiply two integers, it's always commutative. But for some in special cases, say if we say matrix multiplication, for instance, if we have two matrices A and B, then AB is not always equal to BA. They're not commutative. So in those cases, if n is not a normal subgroup, then the right coset may not always be equal to the left coset. That is why we define separately. Otherwise, there was no need of introducing the terms right and left. We could just have defined coset. But yeah, if n is a normal subgroup of G, then we don't need to think about matrix or whatever. Then always the left coset and the right coset will be equivalent. So now we know about cosets and these normal subgroups. What are quotient group? A quotient group is a set of all cosets of a normal subgroup of a group. So for instance, in the example we consider, n was, say we took 1 comma 2 comma 3 and we took a particular x2. So basically x is any element of G and n is already a subgroup. So let us say there are three elements of G, x1 x2 x3. Then how many possible cosets are there? Let us say the left and right cosets are equivalent. So let us just consider this, the right coset. So then nx1 comma nx2 comma nx3, there are three possible cosets. Now this set of all these possible cosets of a normal subgroup, it's a normal subgroup. That's why took the right and left coset to be equivalent. So the set of all the possible cosets of a normal subgroup of a group that forms a set, and this set also itself forms a group. We can prove it, and this is what is known as the quotient group. So if G is a group and N is a normal subgroup of G, group operation is again multiplication, then the set of all cosets of N in G is a quotient group, and it's written as G slash N and pronounced G modulo N. So of course, mathematically, from the definition of cosets, G modulo N is Nx for all x belongs to G, all the possibilities, right? All the possible cosets, and the elements of this set, I mean G slash N, are in the form of cosets, like I said, Nx1, Nx2, and so on till Nxn, such that there are small n elements in G, and this forms a group because, see, you can just take a screenshot and see this later on. I'm not discussing it, but yeah, for instance, the closure property. It's pretty simple to just okay. Let me just discuss the closure property. The other three properties you can discuss. I mean, you can verify for yourself. It will be a good exercise as well. So the closure property, see, we already know that G is a group, and let us say we have two elements x and y that belong to G, and since we already know G is a group, so x into y, the group operation is multiplication. So let x, y be equal to z or z, then z also belongs to G already because G is a group. Okay, so now N is the subgroup, right? And this is the definition of G modulo N. So of course, if x and y belong to G, then Nx and Ny belong to G modulo N, obviously from the definition. So Nx into Ny will, now Ny we can write Yn because it's a normal subgroup, so Ny is equal to Y. We already discussed this, right? You see, must be satisfied. So Nx into Ny, that is Nx into Yn. That now again, if we are not changing the order, we just just regrouping, then we say that this is Nzn, we can say, and then we can say that Nn, then Nzn, because x, y, z, and again Zn can be replaced by with Nz, so Nnz is Nz. Again, here I've explained a bit why Nn is equal to N, because you can essentially you can prove that Nn is a subset of N and N is also a subset of Nn. So which is, if both of these are to be true, then Nn must be equal to N. So yeah, so that means see, Nx into Ny, that means we took two elements from this G modulo N and we multiplied them, the group operation is multiplication, and we got Nz. Now Nz is again an element of G modulo N because we already know that Z belongs to G, so Nz belongs to G modulo N. So that means we have proved the closure property. The other properties also you can easily prove. So closure property we have proved, right? Okay. Now G modulo N also satisfies the associative property. Say some x belongs to G, Nx belongs to G modulo N, Nxn equals Nxne is the identity element. So Ne is just N, we can replace N with Ne. That is Nn Xc, we can again reorder, of course. That is Nx, because Nn is N and Xc is X. So that is Nex again, just in place of X, just a bit of playing around with mathematics, nothing else. So that is again Nnex, that is Nex, that is, I mean, you can just, if I just kind of just read it like this, it will not make sense, but you can just watch this, you can just see this for yourself, maybe pause the video and take a screenshot. It's pretty simple to prove that G modulo N is a group. So this is what we mean by quotient group. Now let's talk about projective space. Projective space is basically an extension of the Euclidean space with points at infinity. Basically what we mean is that, how do we define parallel lines? Parallel lines are lines that never intersect, or mathematically we can define that they intersect at infinity. Infinity is at infinity. That means kind of they never intersect because we can never reach infinity. I mean, that is how they're defined, that they intersect at infinity. Every other line they intersect after some finite distance, but parallel lines intersect at infinity. So in a projective space, two lines, but yeah, that is how we define projective. In a normal space, parallel lines never intersect, because in a normal space we are drawing on a piece of paper, we cannot draw till infinity, right? I mean, infinity, we cannot represent infinity on pen, with pen and paper, right? So parallel lines don't intersect on a normal Euclidean space, although we define them that parallel lines intersect at infinity. But in the projective space, two lines must always intersect. That means even parallel lines must also intersect. That is why we include this. I mean, we also denote infinity with some point in projective space. That is how we define projective space. Suppose we have a classical, like a normal one-dimensional line, that is the x-axis itself, let us say. So this blue line in the figure below, you can see. Then the corresponding projective line will be this red circle. See this red curve. It will be a circle touching the classical line at exactly one point. If you look at this figure, okay. So that means you see every point. The thing is that this is how we define a projective space mathematically. Every point on the classical line, on the blue line, has a one-to-one correspondence with every point on the projective line. I mean, corresponding to every point, there is a unique point on the red line. Every point on the blue line, there is a unique point on the red line corresponding to that point. And how do we find that out? So for that, we define a point O. We define a point O. You see this point here at this kind of the north pole kind of. We define a point O on the projective line as both positive and negative infinity. Right. So see, that is how we define, and this projective coordinates we write like this. In third brackets, 1:0, or some people write 1,0 also, because basically this means 1/0, and 1/0 is infinity, and then this is the same point also represents minus infinity. So you see that is also equal to -1,0 or -1:0, whatever. Basically they represent a ratio. Here -1,0 means -1 divided by 0. And suppose this point P, it is -1 on this blue line. So if I just join this P with this O, it will intersect the circle at exactly one point P dash. So this P dash is the point, the point P dash on the red line corresponds to the point P on the blue line. That is what I was trying to say. And the coordinates of the P dash will be -1, 1. I mean, comma 1 means it's -1. It's basically -1, right? -1 on the blue line, and this is -1 on the red line. But in projective coordinates, we denote like this. It is -1 divided by 1. I mean, anything divided by 1 is that thing itself, no issues. But that is how we write -1, comma 1, or -1 semicolon 1, whatever you write, -1 colon whatever. And in this case, we have to write comma 0, because dividing by 0 is significant. Dividing by 1 is not significant, maybe. So you see, that is what I was saying. What I was saying. It's kind of, and see, basically you are kind of, if you think about it, I'm just giving a rough analogy. This blue line, it extends forever, both toward the left and toward the right. So to the left it goes on to minus infinity, to the right it goes on to positive infinity. So think about it, just try to visualize. If I try to, kind of fold this, if I try to take this blue line and fold it into a circle, then the extreme left point, that is minus infinity, and the extreme right point, that is plus infinity, they will meet at the same point, and that point is O. Just a rough way to visualize. That is why this O corresponds to both plus infinity as well as minus infinity. So this red part, it's a projective line. See, any point you take on this blue line, suppose I take the point here P to be say 0, say +1, 2, whatever. If I join that point with O, it will cut this circle exactly at one point, and that point will be the corresponding point. That point on the red line will corresponding to the P we choose on the blue line. I just showed for a single example for -1. Right. Now if we choose P close to positive infinity, suppose we choose P to the -1, suppose we choose P towards the very right, suppose we choose P to be say at 1 crore, I mean a very large number close to positive infinity. In that case, if you see, if you try to join O with P, you try to follow my this cursor, this pointer, whatever, it will be like this. You see, it will be like this. It will almost be as if a tangent to the circle, kind of. You see, I've written it here. As P moves closer and closer to negative infinity towards the far left, then P dash will move closer and closer to O. Then see, I mean, it will this thing. If I draw the line like this, then it will cut this red circle at somewhere here. It's very close to O. And similarly, if we go close to minus infinity, also it will go the corresponding point on the red line. This P dash will be close to O. And similarly, if we actually, I mean, just mathematically, it's not possible. But if when P actually becomes plus infinity or minus infinity, whatever, either way, then the corresponding point will be exactly O. That is why O is both plus infinity and minus infinity. You can understand this mathematically or visually also. If you just fold or bend the blue line into a circle, then also the endpoints will kind of be the same, coincide. Okay, and then this is how we write modular, I mean, what I'm saying, these projective coordinates. Okay. Now the projective coordinates of the point +2 on the classical line would be 2:1, and so yeah, okay. And like I already said, this one roughly translates to dividing the first coordinate by 1. This may seem unnecessary, however, this is how homogeneous coordinates or projective coordinates are defined. Homogeneous coordinates of the point x lying on a 1D line will be of the form x is to 1. And we can also say, see, basically this is division, x by 1. We can also say 2x by 2, same thing basically, because 2x by 2 is x, x by 1 is also x, 3x over 3, that is also x, and so on infinitely. We can say anything, nx over n. It will go on. There are no, we will never run out of choices, and so on, because essentially we are dividing the first coordinate by the second coordinate, and the division should yield the original coordinate x. And x is to 0 is corresponds to infinity because we're dividing by 0. And yeah, 0 by 0 is not allowed. I mean, x cannot be 0. This is not allowed because 0 by 0 is not defined. Yeah, in projective space also it's not defined. That is why you see this at this point 0, when p is exactly 0, the red line touches the blue line at this point 0, right? So p cannot be 0. I mean, if p is 0, that means see the p dash will be 0 comma, no, then p dash will not be 0 comma 0. I'm sorry, this, no, forget this. This has got nothing to do with this. But yeah, 0 is not allowed. I mean, because 0 by 0 is undefined. Similarly, yeah, the homogeneous coordinates of the point lying on a two-dimensional plane will be of the form x is to y is to 1. X is to y means x comma y. That's already, we need two numbers to define because it's in a 2D plane. Here we just took a simple example of a one-dimensional line. So in that case, the homogeneous coordinate will be of the form x is to 1, y is to 1, or x comma 1, y comma 1, whatever. For 3D, it could be x comma y comma z comma 1, whatever. Also, two projective lines in the same plane must meet at least at one point. Because see, this is a project. This red line is a projective line. The blue line is not a projective line, but see the red line, it's a projective line. If we define another projective line, I mean, you can just try to think why projective lines, the way we have been defining, the way they are defined, they will always meet even at infinity, because here infinity is a point, right? It's within our reach. I mean, of course, we have just defined it to be a point, just denoted this O to be infinity. Infinity is not a point like in that sense, but yeah, in projective geometry, it even parallel lines do intersect. And it's important. It's important to define. I mean, in many problems in physics, I mean, projective geometry are very important. So that's why we define projective geometry. We define projective space. Otherwise, Euclidean space, we already had Euclidean space. Why did we form the idea of projective space? So I gave you the concept, and yeah, here's the formal definition. I'm just going through this briefly, quickly. For a vector space V defined over some field F, the projective space PV is a set of equivalence classes of V. This is V. This means V except this 0. I mean, we're just excluding 0 from the equivalence classes. That is, we consider all V except 0. Under the equivalence relation, X is equivalent to Kx for some non-zero K in F. That is why you see this x comma 1 is equivalent to 2x comma 2 is equivalent to 3x comma 3. They're the same. They represent the same point. Now I will not be discussing in details what an equivalence relation is and how equivalence classes are defined. Basic set theory. But yeah, I mean, a set can be divided into equivalence classes, and two elements belong to the same equivalent class if they are equivalent. Like x is equivalent to kx. That is the equivalence relation we have defined here. Formally, the equivalence class of an element, just a mathematical definition, element A belonging to a set capital X is defined in this way. A in third brackets consists of all x belonging to this capital X, this set X, such that A is equivalent to X. Where, I mean, yeah, this denotes an equivalence relation on X. So if a basis of V has been chosen, basis vectors, the projective coordinates of a point P are the coordinates on the basis of any element of the corresponding equivalence class, and these coordinates are denoted like this, like I said, x0 comma x1 and so on till xn. Now if these are projective coordinates of a point, then kx0 and so on till kxn, they are also projective coordinates of the same point, because x is equivalent to kx. I already showed you one example, right? You see above that x comma 1 is equivalent to 2x comma 2, 3x comma 3. So similar, that is basically, see, this is x comma 1, we're just multiplying both by 2. So here k is 2. Here k is 3. This is again x comma 1, just multiplying x with 3, that is 3x, and 1 with 3, that is 3. So same thing, since x is equivalent to kx, this thing will be true. They are also projective points of the same point for any non-zero k in F. This means if we scale all the projective coordinates of a point by some constant non-zero scalar, the new coordinates will describe the same point. Now if you think about this visually, that means you are kind of filtering out some points, or kind of, folding the space such that some points fall on the other points. They coincide such that they're equivalent, because like I said, the point is being described by x comma 1 and the point being described by 2x comma 2, they are the same point. So that means you don't need to separately define 2x comma 2. You just need to put 2x the second point on the first point. To do that, maybe you do some folding or whatever. That is the visualization part. It's a bit difficult and it's not strictly relevant, but yeah, here I've given a simple example. Even this is difficult to visualize, I know, and you can see some animations on the internet that will give a better understanding than just reading this text. But yeah, I know I'm going a bit fast because I need to cover this, and it's already 55 minutes. But yeah, if you can always pause the video, take a screenshot, and do your own research. That's highly recommended. Okay, I'm just leaving this for you, and let's move to group action. What is a group action? A group is said to act on a set when a certain transformation of that set is consistent with the group structure. I know this is a bit difficult to understand group structure and everything, so just forget it for now. Mathematical definition of a group action of a group G is that let the group operation be star on a set S. So group action first of all is defined on a set S. This set S is not a group. Group is also a set, but it satisfies the 4 conditions. But this is a set, so it's not a group. It's not necessarily a group. So a group action is some function f from G times S. I mean this is the kind of, what is this G cross S? It is the Cartesian product of G and S. So it is from G and G times S, G cross S to S. The function is defined from this G cross S to S, satisfying this condition E star S equals S and G star H star S equals GH star S, where E is the identity element of G, hence A belongs to G, and S belongs to S, and G and H, small g and small h, belongs to the group G. And the action of group G on the set S is faithful. We call this a faithful action if G star S equals S implies G equals E. E is the identity element of G. Okay, faithful action, I'm coming to it in a moment. But yeah, basically this is the definition of group. And if you're not familiar with all these things, Cartesian product and how we define a function from this is the domain, and then codomain, range and codomain, then that it's not possible for me to discuss that here. But yeah, this is how a group action is defined. This was important to introduce the idea because we will need the concept of faithful action at a later stage. That's why I just included this in short, as short as possible. But yeah, so this is a group action of a group on a set, and this action will be faithful if G star S will be equal to, if suppose we have G star S is equal to S, G belongs to the group capital G and S is an element of the capital S set. So faithful action means if G star S is equal to S, that means inevitably G must be E, where is the identity element of G. That means for no other G, for no other element of the group, this condition will be satisfied. This condition will be satisfied only for G equals to E. That is that only then we can say that this particular group action is a faithful action. And now we're in the position to now we have come to projective linear group. We already discussed general linear group. So what is projective linear group? Projective linear group is a special type of general linear group. It's also called projective general linear group, or simply in short just projective linear group. So it is the induced group action of the general linear group of a vector space V, that is GLV, on the associated projective space PV. We know what a general linear group is. We discussed near the very beginning, and we also discussed right now what a projective space is. So the group action of this general linear group on the associated projective space, that means projective space on the, that means here the set S basically it is a set of all the elements that belongs to the projective space, kind of. See, in terms of quotient group, PGLV, that is the projective general linear group V, is GLV slash ZV, or GLV modulo ZV, where ZV is the center of GLV. Center means the center of a group G is denoted by Z, ZG is the set of elements of that group that commute with every element of that group G. So in this case, you see ZG will be small g such that it belongs to the group, such that for all small g belongs to G, ZG will be equals to GZ. Z is an arbitrary element of the group and G is also an arbitrary element. So the center will only consist of those elements that commute with every other element of the group. Right. So this Z belongs to the center, small z, because small z commutes with every other arbitrary element, small g. That is how a center is defined. So the mathematically you can define PGL like this, very simple to understand. And if you want to try to see it visually, see, the elements of the projective linear group can be understood as tilting the plane along one of the axes This one is from Wikipedia, by the way. I've just copied from Wikipedia. This particular, this only just this part. Okay. Uh, Along one of the axes and then projecting all the points in this tilted plane to the original plane. This is a group action. So basically, see, if GLV here the set is PV, right? So GLV cross PV to PV. So GLV cross PV corresponds to the rotation transformation which rotates the projective plane PV along one of the axes, and then we project to the original plane PV. So that is why it is GLV cross PV to PV. I mean, basically, you just forget this, and this is a bit difficult to understand like this. But see, basically, it is the induced group action of the general linear group of a vector space V. So that means, yeah, basically, you're just a group action. I mean, for now, this mathematical definition will suffice. Basically, if you try to think from the point of view of projective space, you are kind of, what do you mean by projection in very simple terms? Suppose you have a, let me give you a simple example. Okay, I mean, let me just try this here, like this very crude way to show you, but just so that you get the idea. So just consider this to be my x-axis and this to be my y-axis, this dashed line to be my y-axis, and this to be my x-axis. And suppose I have, just a second. And I'm sorry, but okay, anyway, so suppose I have this vector here. Just think about, I can actually insert a line, I guess, in Google Documents, right? Just let me just pause the video for us, just a second. Just a line, right? Horizontal line. No, I'm looking for a general line. Okay, drawing. There's nothing called shapes. Okay, get it. Okay, so you see, just a second. Yeah, so you see, this is the x-axis, this is the y-axis, and this is simply a vector. I'm just showing a simple example of what I mean by projection. So if I say this vector, if I say the projection, if I tell you what is the projection of the vector on the x-axis, on the horizontal axis, and not the mathematical formula, just the visually, then that means what? Kind of, just to show you the example, you are kind of shining light from above. Oh, sorry, it's a bit difficult, it's just kind of, yeah. So you are kind of shining light from above, kind of shining light from above, and you are seeing only the reflection in the sense, it's very disturbing, just okay, so you're only, so if you that means you are here, you are seeing the entire situation from the above, that you're just seeing the projection on the x-axis. So that means you will only be able to see just this much, right? This much, just this much. This is basically this is basically just, if I just drop a perpendicular, so just only this portion, only this portion, it's only this portion. So this is the projection. So similarly, if you have a plane, if I ask you to take the projection of the entire plane, I mean, you can just try to imagine it like this. You are kind of, if you fold a plane in along some particular line and just fold it, that means all of these points on it, on the first part, they are kind of being mapped to some point in on the other part. They are kind of, you are kind of saying that they are equivalent, right? uh, just a second, yeah, fine. Yeah, so oh my god, just sorry about this. I have, so far I have been using whiteboards. I've never tried to draw on Google Docs before. I've only just used latex and just normal typing, so sorry about, I just wasted a bit of your time. But yeah, anyway, so for now this is enough. But if you want a little bit of rough visualization, this basically means we have the general linear group, all the groups, so we are just taking the projection of all the elements of the group. We are just using all the elements of the general linear group on a particular projective space, and then we are taking a projection on that same space. we have the general linear group. That means all the elements of the general linear group, basically they all are represent some transformation matrices, and we have some, say, PV, some projective space. Now we transform all of the points on this projective space, all the members of this set, with the transformation matrices of the general linear group, and we then basically after the transformation we will get a new space. And now we take the projection of the new space on the original space, just like we took the projection of the vector on the x-axis. So then that is how we define a projective linear group. Kind of, yeah. Mathematically, you can, if you're mathematically inclined and have good training in mathematics, you can try to see why what I said, the visualization part, why that and this mathematical definition, why they must be equivalent. You can try to, you know, figure out, because if you can actually understand this, then you'll have a very good grasp over the concepts. It's always important to prove why two definitions are equivalent, right? It's very important to prove. Of course, for the part of, you know, solving problems or the basic at a basic level, just knowing a single definition is enough. But if you want to do research or understand it at fundamental level, you should always know why the two definitions are equivalent. You should always prove it mathematically rigorously, or at least have a good visual understanding of why the two definitions are equivalent. Not a rough understanding, but a rigorous understanding. It's very difficult to, you know, even I don't have a very good understanding about uh, modular forms and all. I just did a bit of study in modular groups, and as for this, but it's very difficult to make you understand without some visualization tools. But anyway, right now I don't want to do that also, because let me move to modular groups now. We've already wasted over 1 hour. Not wasted, but yeah, we're moving slowly, that's all. So this is projective linear group or projective general linear group, whatever you say. And then we can similarly define projective special linear group, the same thing, but here we will only include those matrices with just a second, yeah, with determinant 1. We'll only consider those matrices with those members of the projective linear group with determinant 1, and then that will form the PSL, projective special linear group, over V, that is PSLV. Yeah, it is the induced action of the special linear group on the projective space PV. Same thing as before, but here we use the special linear group instead of the general linear group. And yeah, the definition is also the same thing. It's SLV modulo SZV, just like here we had this. I'm sorry, it's SLV modulo ZV, not SZV. Why S? Yeah, ZV. And here, what is this? Yeah, ZV is the set. Actually, it should be SZV, because ZV is the center of the general group, and here is the special center, because it's the center of the special group. So that is why we denote it as SZV. That's all. This SZV is total. It's the notation. That's all. So here SZV is the center of SLV, just like ZV is the center of GLV. See, ZV is the center of GLV. Okay, so it's obvious that the center is I and minus I, because see, what did I say? Center of a group is the set of elements of that group that commute with every element of the group. So see, I and minus I, any element you pick from this group, and you multiply, either you pre-multiply it with I or you post-multiply it with I. You can just do the calculation, simple, or minus I, you will get the same thing. See, I said in case of matrices, suppose we have two matrices A and B, it's not always true that A, B is equal to BA if we multiply them. But if one of them is the identity matrix I, and say we have another matrix A, then IA is always equal to AI, and that is equal to A again. I is the identity matrix. And same for minus I. Minus IA equals to A minus I equals to A. I mean minus A. So yeah, they form the center, right? And where I is the identity matrix of the same order. Suppose if we have taken the special linear group of order 2, then I is the second order identity matrix. Doesn't matter. You could divide the identity matrix of any order. Now the identity matrix and its negative matrix are the only invertible matrices that give matrix must be invertible, because they should belong to the special linear group. Only then they can be center of that group, that give the same result regardless of whether they are left multiplied or right multiplied, pre-multiplied or post-multiplied, with an arbitrary matrix belonging to SLV. Matrix multiplication is not commutative in general. However, Im equals to Mi and minus Im equals M minus I for some matrix M belonging to SLV. Just what I told you. And the condition that a matrix must have determinant 1 to belong to SLV prevents any other matrix except I and minus I from being a part of SZV. Yeah, there could be some other matrix also other than I, which, for which you see this condition may be satisfied, Im equals to Mi. But see, it should be satisfied for all the cases, for all the matrices. You see, the center of a group is a set of elements of the group that commute with every element of G. And plus, since it's a special one, it should the determinant should be 1. So the determinant of the identity matrix is 1, right? Okay. And then we have see, this is not required because anyway, even in the case of general linear group, only I and minus I will be in the belong to the center, right? Because for other matrices, it will not even commute in the first place. So you don't even have to worry about the determinant case in this case. And in this case, so in both the cases, only I and minus 1. And yeah, in this case also, I and minus I, and they are automatically satisfying the condition that the determinant should be 1. So yeah, I think in this case also it should be, the center should be I and minus I. Anyway, yeah, so for the matrix A B C D to belong to, suppose here we have taken a 2 by 2 matrix, so that means this is the special linear group of order 2, n is 2 here. So for this matrix to belong to this center, SZV, or the center of SLV, it must satisfy the condition that A equals D and B equals C equals 0, because for the determinant to be 1, what is the determinant of this matrix? It's AD minus BC, that should be 1. So see, that means if A is equal to D, that means that is basically A square minus B C, again B and C both are 0, that is A square equals to 1 basically. I'm sorry. The determinant AD minus BC equal to 1, the determinant should be 1. And yeah, to belong to the center, it must satisfy the condition A equals to D and B equals to 0, not for the determinant 1. These two conditions arising, why? Because to the center, that means if I multiply this matrix with any other matrix, then suppose I take another matrix, say E F G H. So if I do ABCD and multiplied by EFGH should be the same as EFGH multiplied by ABCD. Only then we can say that this matrix belongs to the center. So if you do a little bit of mathematics, you can see that for this condition to hold true, you can take any random matrix. You can take some particular values of EFGH. You will see that A must be equal to D and B and C must be 0. Because see, when you do matrix multiplication, see, that is how you do, right? First you multiply A here and then B here and then C here and D here. So if you do pre-multiply and post-multiply, and for that to be equal, you see this condition must be satisfied. And plus we have this, since it's a special linear group, AD minus BC equals to 1. So if we just, combine these two conditions, we get A square equals to 1, which means A is plus minus 1 and D is also plus minus 1 because A is equal to D, and B and C are 0. So this means the identity matrix I and its negative minus I belongs to SCV, because you see I is what? For I, A and D are just 1 and B and C are 0, that's fine. And if A and D are minus 1, then that is, and B and C are 0 of course, then that is minus I. See, A equals D equals plus minus 1 means either both A and D are 1 or both A and D are minus 1. You see, it's not like A is 1, D is minus 1, that is not allowed. Okay, right. Next, let us just talk a little bit about linear fractional transformations. This will be important for the remaining discussion. A linear transformation can be represented by some function between vector spaces that preserve the structure of the space. That is why linear. Structure of vector space, I cannot discuss in detail here again. But yeah, an invertible transformation, of course it must be invertible, of the form Z is being transformed to AZ plus B over CZ plus D, such that the numerator, that is AZ plus B, this is the numerator, and the denominator, that is CZ plus D, the numerator and the denominator of the fraction are linear. Of course they're linear. See, Z is Z, and here also it's a function of Z. There is no Z square or Z cube, it's linear, right? So this is a linear fractional transformation. And this can also be defined as a projective. This is not required right now. You can just maybe study it later if you're interested. So, I mean, let me just forget all of this. Basically, what I'm trying to say is that this transformation, linear transformation, is basically you're transforming Z to this point AZ plus B over CZ plus D. You can just calculate it. For a particular case, you will know the value of A, B, C, and D. So and you are starting with the initial point Z. So if you just calculate AZ plus B over CZ plus D, then you will get some new point, say Z prime. So that Z prime will be the transform point. So you're transforming Z to Z prime, and this is an example of a linear fractional transformation. So you can also represent this transformation as a matrix. Z prime is some matrix, say gamma times Z, because this thing here which you're seeing, this is basically nothing but, you see basically what, you just consider the same matrix, see A, B, C, D. So you have A, B, C, D, and then you consider a column matrix Z. Column matrix in the sense it's just a column, like you have a matrix of this form. I mean, just this matrix. You have Z, and then you have 1. Just this. This is your matrix. Yeah, this is your matrix. It is like this is a 2 by 2 matrix. There are 2 rows and 2 columns. This is actually a 1 by 2 matrix. There is only 1 row, and there are, I'm sorry, this is a 2 by 1 matrix. There are 2 rows. This is the first row, this is the second row, and there is only a single column. So this is a 2 by 1 matrix, and it's possible. See, so that means if we multiply this ABCD with Z1, what I showed, then you will get AZ plus B, and as the top element, you will again get back a 2 by 1 matrix like the column matrix, and the upper element will be AZ plus B, and the lower element will be CZ plus D. So that only, if you write it as a fraction, you see you have AZ plus B over CZ plus D. So basically this transformation can be more elegantly represented as multiplying this Z with the matrix A, B, C, D, this matrix, and then you are getting this this thing, which is the new point, Z prime, or whatever you call it. So Z prime is basically this matrix multiplied by Z, pre-multiplied by Z. That is what I've shown here, you see. Yeah, see, this is what I was talking about. You have this matrix A, B, C, D, and you are pre-multiplied. The matrix is first to the left, and then you have Z1. Z1 basically represents the point Z, but like I said, in projective coordinates, we have to write Z comma 1 or Z divided by 1. That is what the meaning. So if we do this multiplication, we get this, and this can be written as, again, this means AZ plus B divided by CZ plus D. That's what I've written there, and comma 1 in projective coordinates. And yeah, if we want to represent Z1 as a row matrix, in this case, then we have to post multiply the matrix A, B, C. We have to actually post multiply the inverse of the matrix. You see, A, C, B, D. Then also we get the same thing. See, basically what I'm trying to do is that, you see, actually this is the transpose of the matrix. You see, again, if you know some basic matrix, you will understand. Okay, let's see. When the second coordinate is non-zero, a point can be represented like this, Z comma 1. Thus, when AD minus BC not equal to 0, that means the determinant is not equal to 0, the action of projective general linear group, or 2 comma F, is by linear transformation, this thing. So since PGL means the action of GL on the associated projective space P, the transformation above, in which we essentially multiply the projective coordinates with the matrix, represents an element of PGL. The 2 by 2 matrix M, this matrix A, C, B, D, we are calling M, is invertible, since AD minus BC is not equal to 0. Here also the determinant will be AD minus BC. We just integer position of B and C, right? Thus it belongs to the general linear group. Now after the first step in the above transformation, we get this, which can be equivalently written as shown. Now in the above representation, we have denote Z comma 1 as a 1 by 2 row matrix and post multiplied it with M. We have taken the transpose of the matrix M dash. ABCD is M dash, but here this ACBD is the transpose of M dash. We have called it M. Transpose means we just change the rows into columns and columns into rows, nothing more. Interchange the rows and columns. So note that if M dash belongs to GL 2 comma F, then M will also belongs to the GL because it's both of them are invertible matrices, and yeah, they're satisfying, same order and everything. Transpose of an invertible matrix is also invertible, and determinant of a matrix is the same as the determinant of its transpose. Thus an equivalent representation of the above transformation is this, ABCD Z1. Yeah, because see, we must determine the order of multiplication and the choice of matrices M or M dash, row or column matrix, for the point Z comma 1, by keeping in mind that two matrices A order M cross N and B order P cross Q can be multiplied only if and only if N equals to P, because you cannot multiply two matrices of any random order. See, we can do this multiplication because the first order matrix is of order 2 is 2 cross 2, and this is 2 cross 1. So you see, this 2 and this 2 cross 1, so they are the same. And in this case, see, this matrix, it is 1 cross 2, and this is 2 cross 2. So again, this P, this N and P are the same. So if we choose to represent the point Z as a column matrix in this form, then we have to post multiply with the transpose. Why with the transpose? Because yeah, otherwise we will not get this form. Otherwise, if we want to pre-multiply with the familiar form ABCD, then we have to express Z as a column matrix in this form, Z1. This is all about linear fractional transformation. And finally, modular group. Modular group, see, we have discussed a special linear group. The the group of all so suppose here we are taking this particular special inner group of order 2. I mean for n equals to 2, that is SL2 comma z. So we are taking the special inner group over the integers z, and all the and we are taking 2 order. That means this is the group of all 2 by 2 cross 2 matrices, invertible matrices with integer elements z and determinant 1, of course, because special inner group. And the operation is of course matrix multiplication as usual. So the modular group is the quotient of the special inner group SL2 comma z over the set of integers z by its center SZV, which is I comma minus I, where I is the identity matrix of order 2. So yeah, mathematically the modular group is this thing, which is just the projective special inner group 2 comma z. So modular group is actually a the projective special inner group of order 2 and for integer elements, nothing else. It is actually a projective special inner group. That is why we had to, I introduced you to general linear, special linear, and projective, all these things. Now the modular group acts on the upper half of the complex plane. We define why the upper, only the upper half. That is how we define. I will tell that to you just shortly. But yeah, so it acts by fractional linear transformations of the form, this same form, where a, b, c are integers and ad minus bc equals to 1. Of course, a, b, c are integers. It's for integers, and this must be 1 because it's the special inner group. So in other words, modular group consists of all 2 by 2 matrices A. Here now, from now on, we'll be talking only about 2 by 2 matrices, where A has the form this, where A, B, C, D are integers and AD minus BC, or the determinant is 1. And group operation is matrix multiplication. And yes, sometimes the special inner group SL2 comma Z itself is defined as a modular group, and sometimes we define the projective special inner group 2 comma Z, that is PSL2 comma Z, as the modular group. So this is all about, not all about, this is the basic definition, the basic definition of modular group. But of course, we need to understand why it's important and what it is. For that, we need to go beyond this, just this definition, right? So there are basically will be there are one way to define modular group is via generators. What does that mean? The modular group SL2 comma. So right now we are considering the special inner group, okay, not the projective one. Projective one will come later. I will discuss that. So this group SL2 comma Z, this is what we are calling the modular group right now. This can be generated by 2 transformation matrices, or 2 transformations, or 2 matrices S and T. Just these two, S and T. This S and T, you don't need any other matrix, any other transformation matrix. Just these two are capable of generating all the elements of SL2 comma Z. So that's why we call S and T the generators of the modular group. And S is basically this transformation Z to minus 1 over Z. That means it transforms any point Z, any complex number Z, any point on the complex plane Z to this, to the point minus 1 over Z. So right now since it's a 2 by 2 matrix, we're in 2 dimension and in a 2 dimensional plane, and that is the complex plane. We'll be studying the complex plane. That is how the modular group is, the fundamental region is defined. And T is a simple translation to the right by 1 unit. T is just Z, it transforms Z to Z plus 1. Just moves the point Z to by 1 unit to the right. And this is a bit more complicated. It transforms Z to minus 1 over Z. So it's actually an inversion. Geometrically, S represents inversion in the unit circle with center at origin on the complex plane, followed by reflection with respect to the imaginary axis, while T represents a simple unit translation to the right. Now every element in the modular group can be represented by the composition of powers of the transformation matrices S and T. That means S and T obey and yeah, there are 2 relations which S and T must obey. S to the power 4 is I, the identity matrix, and S squared, which is equal to S T whole cube, is equal to minus I. That is the negative of the identity matrix, of second order identity matrix. Of course, right now whatever we're discussing in second order, 2 by 2 matrix. So yeah, I is also the 2 by 2 identity matrix. So, and they form a complete set of relations. So we can use the presentation method to specify the modular group. It can be presented as gamma. This we are defining the modular group as gamma. Gamma is just S comma T such that S to the power 4 is I and S square equals to S T cube. And we're writing it like this. That means basically in this whatever you call this, these brackets, whatever. That means what? We have to consider all the possible combinations of powers of S and T. Each possible combination of powers of S and T corresponds to an element of the modular group of the SL2 comma Z group. And of course, there are infinitely many combinations, just like there are infinitely many members in this group. But mathematically, what the mathematics tells us is that all the elements of this group can be generated by different combinations of powers of S and T, just S and T. So they are the generators of SL2, C, or the generators of the modular group. So it's a set of the generators, yeah. So every element of the group can be written as a product of some powers of some of these generators. I mean, either one or both. I mean, there are only two generators, right? So some powers of these generators, in general, we can write of these generators, right? Because see, provided S and T follow the relations, this, because we will define the matrices S and T such that these two relations are obeyed. I will show you how these matrices are defined soon. For example, T to the power L, S to the M, T to the N. This represents an element of the modular group because this is a combination of different powers of S and T, where of course L, M, and N are integers. So, for instance, you see, this can go on infinitely because since alternately we see T, S, T. So since there's an S in between, we cannot combine T to the L and T to the N and write T to the L plus N, because matrix, this S and T, they are matrices, and S raised to the any integer power, T raised to the any integer power, they are also matrices, and matrix multiplication is not commutative. So we cannot actually bring this T to the N to the left. So we cannot simplify. This is the form. So we have to write it alternatively. It is not necessary that we take the product of three matrices, the product of infinitely many powers of S and T. Let's say it is going on S n1, T n2, S n3, T n4. Of course, it should be alternatively, because if two S are side by side or two T's are side by side, then we can just add their powers. In that case, we can add their powers and express them as a single S or a single T, respectively. And yeah, here, of course, these are all integers. So see, this also represents an element of the modular group. And note that matrix multiplication is associative, but it is not commutative. Hence, TL, SM, TN is not the same as TL plus N, SM, etc. Now, for a valid choice of the powers of S and T, we see that S belongs to gamma, and S is essentially, see, S we can just write S to the 1, T to the 0. 0 is also an integer. So any matrix, so this matrix S individually, S also is a member, because S to the 1, T to the 0, that is S. Any matrix S to 0 is the identity matrix of the same order, and similarly S to the 0, T to the 0, that is the second order identity matrix I, that is also a member of gamma. And yeah, S to the 1, I mean S to the 0, T to the 1, that is just T, that also is a member of the identity matrix. S, T, and TS, that is S to the 1, T to the 1, and T to the 1, S to the 1, they are also, the order of the generators doesn't matter as long as they satisfy the relations. Yeah, so they also belong to gamma, and so on. So this is the generator approach to defining the modular group. I mean, we need to define the modular group mathematically, right? So one approach is using generators and using the presentation method of defining a group. This method. I mean, just as combination of different powers of the generators. Now, irreducible fractions and matrices of SL2 commas. Okay, this is not strictly relevant right now, so I'm just skipping the portion, but I will give you time to take a screenshot in case you are interested. You can read further. Okay, just yeah, this, take a quick screenshot, pause the video, and then this, yeah, just this. From fundamental periods I will be discussing. This is important. It's very important. Yeah. So you see, a fundamental pair of periods is an ordered pair of complex numbers. Ordered pair means suppose a comma b maybe, that defines a lattice in the complex plane. This is a bit I won't say difficult, but you should pay close attention to this part. Okay. Because after this we'll move into the fundamental region, right? So this type of lattice is the underlying object with which modular forms are defined. Basically, a fundamental pair of periods is a pair of complex numbers, say omega 1 comma omega 2, such that the ratio omega 1 over omega 2 is not real. Because see, if the ratio is okay, if we express these complex numbers as vectors in the two-dimensional Cartesian coordinate system, such that the x-axis is the real part and the y-axis is the imaginary part, just the complex plane, kind of the complex plane you can think of. But see, it's not exactly, it's, see, basically you consider this is the two-dimensional plane. So this vector, you see this blue vector, just which I'm tracing with my pointer, this say is omega 1. Omega 1 is a complex number, so omega 1 is basically, let us say, a1 plus ib1. So this is a1, this real part, this is a1, and this is b1. And this blue vector, the second vector, that is, let us say, omega 2, that is, say, a2 plus ib2. So this is a2, this small part on the x-axis, the horizontal axis, and this is a3, I mean, sorry, b2, this is b2. So we can express, we can represent omega 1 and omega 2 as vectors on the two-dimensional plane, complex plane, right? And see, omega 1 and omega 2 must be linearly independent. Why? Because see, to define a two-dimensional lattice, we are saying that they define a lattice. A lattice means this thing. You see this, for instance, this black dots. You see the black boxes. They form a lattice. This lattice is defined by all the black points. Points in the sense the points at which the you see these small black squares. All the edges, the vertices of the squares, they are the points that define the black lattice. I mean the points at which the black lines intersect, the horizontal as well as the vertical lines. Then this purple, I mean this light blue, this actually this cyan color, this cyan colored thing which you can see, this which is kind of, you see, slanted kind of, they all that is also lattice. But see, that is actually the same lattice as the black lattice. They may not seem the same because of course it seems slanted and it's a lot bigger. The black squares are small, but these cyan parallelograms are a lot bigger. But why they're the same, kind of the same, because you see, uh, the points on the cyan lattice, they are also the points on this black lattice. They coincide. You see these points, they're the vertices on the vertices of this black square. They also this point, for instance, you consider this point, it's a vertex of this black square, but it's also a vertex of this cyan parallelogram. All the points you see, all the vertex of the cyan parallelograms, they also are a point on the black lattice. But of course, there are some points on the black lattice which are not part of the cyan lattice. Of course, so they're not entirely, they are not the same lattice. But the cyan lattice is kind of, they contain this, they are defined by the same points which also belong to the black lattice. But anyway, so yeah. So why I said that their ratio omega 1, omega 2, omega 1 over omega 2 is not real if this fundamental pair of periods, if this ordered pair is to define a lattice on the complex plane. Because if omega 1, you see, if omega 1 equals a plus ib and omega 2 equals c plus id, then a by b must not be equal to c by d. Because if a by b is equal to c by d, then see what is, that means what, this is a and this is b and this is c and this is d. I mean the real and imaginary parts of the two of omega 1 and omega 2. See, if a by b equals to c by d, then that means you think about this, then that means they can never describe a lattice. Because see, uh, they must be linearly independent. To define a 2D lattice, you need to specify at least two vectors, the basis vectors. Then we can take infinitely many parallel copies of both these vectors. See, we have just defined two blue vectors, and then we have taken parallel copies. We have extended this parallelogram defined by these two vectors infinitely in all directions, and then we have defined this lattice, this cyan color lattice. But see, these two vectors, they are linearly independent. Because if not, if they are not linearly independent, then what would happen? You see, uh, if a by b is equal to c by d, then they will be linearly dependent. Why? Think about this. Think about this. See, in that case, one is a scalar multiple of the other. A by b is equal to c by d. So that means a plus ib and this is c plus id. So that means what, they are kind of, you just try to visualize. I'm not doing the mathematics right now. You just try to visualize. That means they're proportional. So that means you can express omega 2 in terms of omega 1 if a by c, if a by b is equal to c by d. Omega 2 is what, c plus id. But you are saying that okay, a by b is equal to c by d. That means c is equals to a by b, I mean ad by b. So that is ad by b plus d is equal to ac by b, that is ac by b. Right? C is equal to AD by B, and no, D is equal to BC by A. I mean, anyway, I mean, and come on, if you think about this, if this is true, I mean, actually, if you have some knowledge of linear algebra, you can say, if you try to represent this as a matrix, if A by B equal to C by D, then that means they are linearly dependent, not linearly independent. These two vectors, they are linearly dependent. That means one of them is a scalar multiple of the other. That means they will lie on the same line basically. See, only then it's possible, right? A by B. So suppose this is A and this is B. So this ratio is the same as this by this. Same. So for that to be same, you think about it. A by B is equal to C by D. So, oh, I'm sorry. I'm really sorry. I was doing it the wrong. That's why I got a bit confused. I admit. This is A. and this is b. B is the imaginary part of omega 1, right? So a by b is equal to this c by d. Now I get it. Now I get it. Now I get it. So yeah, in that case, if the real, I mean, a is the real part of omega 1 and b is the imaginary part of omega 1 itself, and same for c and d for omega 2. Now in that case, if a by b is equal to c by d, then obviously omega 2 is, I mean, omega 2 can be expressed as k times omega 1. I mean, it's a scalar multiple of omega 1. So both this omega 2 and omega 1 point in the same direction. Then basically you will have a line. You cannot define a lattice, right? And it can be easily shown that, just as this one is a simple calculation, this one I will not elaborate, that for the ratio omega 1 over omega 2 to be real, this is the precise condition: a by b is equal to c by d. But we want that they must not be equal, so that is why we say that the ratio omega 1 over omega 2 must not be real. That means the imaginary part must not be 0. That means b and d must not be 0, because in that case the ratio will be real, entirely real. Then omega 1 will be a and omega 2 will be c. Then omega 1 over omega 2 will be a by c, which is a real quantity. It must not be purely real. The imaginary part must not be 0. Yes, I mean, that means there should be some, you know what I'm talking about. Not just that, this I mean, this should be even if the imaginary part is non-zero, it's possible the ratio is real, but we cannot allow that. We don't, I mean, we don't want that, right? We don't want that. So not any two pair of complex numbers can define a fundamental can, you know, form a fundamental pair of periods. But yeah, these are the conditions. Okay, and this part I got a bit confused, right? So see, if a by b is equal to c by d, that means what? C is ad by b. I'm just telling you, if you want, you can just write this down as I say. So then C is AD by B. Then omega 2 is equal to AD by B plus I. D will be BC by A plus I BC by A. So what is C by A? See, if A by B is equal to C by D, A by B is equal to C by D. So C by A will be equal to D by B. So that means this is B I B D by B, and C is already what? D by B A. So D by B cancel. I mean, canceling this, you can just take it common, because D by B is a real number, scalar multiple, and then you're left with A plus IB. So omega 2 equals to D by B into A plus IB. So omega 2 can be expressed as some scalar K times omega 1, and here the K is D by B. So that is what I was trying to say. In that case, omega 1 and omega 2 will be linearly dependent. It's a scalar multiple of the other. That means omega 1 will be, suppose this vector, omega 2 will be along the same direction, maybe a bit longer, because you're just multiplying with the scalar, but then they cannot describe a lattice. Okay, so now yeah, here we have the lattice shown above is generated by omega 1 and omega 2, and two vectors color blue on the complex plane. Just this I already discussed. And the parallelogram outlined in blue, in deep blue, this parallelogram, you see this parallelogram, it is called the fundamental parallelogram. If you see, the vertices of the parallelogram are 0, this is 0, and this is what? Omega 1, because yeah, this is the omega 1, right? This vector, and this is omega 2, and this is omega 1 plus omega 2. If we just draw the vector from origin to here, it's the resultant. It's omega 1 plus omega 2. It's the resultant vector, right? So this is the vertices of the fundamental parallelogram. And the fundamental parallelogram, by definition, there can be no lattice point lying inside the fundamental parallelogram. You see, here we're talking about this lattice, cyan colored lattice. So there is no lattice point, no cyan point inside this fundamental parallelogram, or inside any parallelogram. All of these parallelograms are equivalent. We just define one of them. See, this is also the same parallelogram, right? So because the points of the lattice are the vertices of the parallelogram, so of course they cannot lie in the interior of the fundamental parallelogram. If they lie, that means that point is not, that does not belong to that lattice. The lattice that has been described by that particular fundamental parallelogram, or by omega 1 and omega 2. Now, while a fundamental pair generates a lattice does not have any unique fundamental pair. In fact, an infinite number of fundamental pairs correspond to the same lattice. I'll show you why. The lattice generated by omega 1 and omega 2 is defined as, you see, say capital lambda is m omega 1 plus n omega 2, such that m and n belongs to integer. This is the general definition, because the lattice that is generated by omega 1 and omega 2, m omega 1 and plus n omega 2 will describe the same lattice for integer m and n, provided omega 1 over omega 2, this ratio is not real. That means, see, this definition is basically the set of all the points of the lattice which can be obtained by taking all possible linear combinations of omega 1 and omega 2. And of course, there are infinitely many possible fundamental pairs, because for the infinitely many values and combinations of m and n, m and n are integers, and there are infinitely many integers and infinitely many combinations. So two pairs of complex numbers omega 1 and omega 2. Yeah, so now this is important. Two pairs of complex numbers omega 1 and omega 2 and alpha 1 and alpha 2 are equivalent if they generate the same lattice. That is, if lambda omega 1 omega 2 and lambda alpha 1 alpha 2 are equal, same lattice. And of course, omega 1 over omega 2 is not real, and neither is alpha 1 over alpha 2, of course. Otherwise, they could not have generated any lattice in the first place. So mathematically, two pairs of complex numbers omega 1 omega 2 and alpha 1 alpha 2 are equivalent if there exists a 2 by 2 matrix belonging to the modular group, say M, such that alpha 1 alpha 2 in this column matrix form is equal to a b c d times this matrix times omega 1 omega 2 in this column matrix. See, basically, if we just write this, if we just actually multiply this, you see, if we multiply the right hand side, we get a omega 1 plus b omega 2 as the upper element. We again get this kind of matrix, column matrix in the right hand side, and the lower element will be c omega 1 plus d omega 2. So if we just compare with the LHS, we can say that alpha 1 equals a omega 1 plus b omega 2 and alpha 2 equals c omega 1 plus d omega 2. You see, this is why we define this is why lattice is defined like this: m omega 1 plus n omega 2 for m and n integer. You see the same thing here in general, right? And of course, a b c d, so here m and n are all possible combinations we're taking, so everything will be covered. We can define, this is a complete definition of a lattice. This thing, this is how a lattice is defined in general. But yeah, from why I'm saying all this, because this is where this modular group comes in. Any matrix belonging to the special unit group SL2 comma 0, the modular group, if we multiply that matrix with omega 1 omega 2, then we get alpha 1 and alpha 2. Then alpha 1 and alpha 2 describes the exact same lattice that is described or generated by omega 1 and omega 2. That is what I was trying to say. The choice of the integers a b c d is arbitrary as long as they satisfy ad minus b is equals to 1. Of course, special linear group, since the matrix belongs to the modular group. This shows that the elements of the modular group provide yeah, this is important, but before that, okay, no, okay, I think that is not required right now. It's already 1 hour 41 minutes. Anyway, I don't think anyone is watching the video. I mean, anyone has watched this, will watch this far, but whatever. Let me just finish what I've started, kind of. Yeah, so you see, this means, this shows that elements of the modular group provide a symmetry on a two-dimensional lattice. This is what we mean by modular symmetry, the very basic example of modular symmetry. What do you mean by the C? Read the statement carefully. Elements of the modular group provide a symmetry on the two-dimensional lattice. The lattice that is generated by omega 1 omega 2 and alpha 1 alpha 2 is the same lattice. Then that is not changing. So that is remaining unchanged. So that means there is some symmetry, and the symmetry is over this group, modular group, because this symmetry is this transformation, this element, it belongs to the modular group. So that means this is a modular symmetry, right? Correct. And it's a symmetry on a two-dimensional lattice. Of course, omega 1 omega 2 alpha 1 alpha 2, they all describe two-dimensional lattice. So this means that the elements of the modular group transforms omega 1 omega 2 to alpha 1 alpha 2. So there is some transformation, but this transformation is happening in such a way that the lattice they describe is remaining the same. This lattice does not change. So that is why this lattices are said to exhibit modular symmetry. And note that omega 1 omega 2 alpha 1 alpha 2 are points on the complex plane, and clearly they are not the same point. Of course not. I mean, of course not. That is why we are denoting them by omega 1 omega 2 and this other pair by alpha 1 alpha 2. But they describe the same lattice. So that is why this lattice, they exhibit modular symmetry, but the points are not the same. Of course, something is changing. Something is being transforming. If we don't change anything, then of course nothing will change. There is no question of symmetry. So omega 1 and omega 2 alpha 1 alpha 2, they are not the same points. So it is not these points that show modular symmetry. It is the lattice they generate that remains unchanged under a modular transformation. This part, it's very important. Nothing difficult, but you should think about this for a moment. Just not, yeah. And you see, for instance, this one, you just follow my cursor, my pointer. This blue small vector right here, this is omega 1 and this is omega 2. And you see this is the fundamental parallelogram, which is shaded light blue, sky blue, whatever. It is the fundamental parallelogram of the lattice, which is generated by omega 1 and omega 2. And you see the points of this lattice. You see this small brown points. Now this is alpha 1. This you follow this. This is alpha 1. This line. You see this line. and this is alpha 2. And if you complete the parallelogram, then this parallelogram shaded in light red or whatever this color is, then this is the fundamental parallelogram for the lattice generated by alpha 1 and alpha 2. Clearly omega 1, omega 2, alpha 1, alpha 2, they are not the same points, not the same vectors. But you see the lattices that they generate, that is, see for the blue, for this case, the first case, you see these brown points, these are the points, right? And for this red, I mean whatever this red parallelogram, you see the vertices of the red parallelogram, see this brown point, then this point, this point, all of these points, they are also a part of this fundamental parallelogram, the lattice generated by omega 1 and omega 2. And if I if you try to extend this red parallelogram, of course extend in the sense you have to extend, just like you have extended this blue parallelogram upwards, and like this you have to, for the red it is not shown, but if you try to extend, you see like this and this, I mean infinitely, you will see that ultimately the all the points described by the red parallelogram will they are all the points will be covered. I mean omega 1 and omega 2 lattice will be the same as the alpha 1 alpha 2 lattice, so the lattices are equivalent, although clearly omega 1 and omega 2 and alpha 1 alpha 2, they are not equivalent. So an element of the modular group is transforming omega 1 omega 2 to alpha 1 alpha 2, but yet the lattices they are describing remains unchanged. So this lattice exhibits a symmetry under the modular group. That is what we mean by modular symmetry. Now again, this is mathematics very well, but in physics, not in physics also we have two-dimensional theories, we need to work with lattices, but there also modular symmetry is interesting, important. That's why we are studying it in the first place. Physicists are studying it in the first place, but not any random arbitrary lattice is important. Only specific kinds of lattice are interesting to physicists. But yeah, from a mathematical point of view, yeah, this is what we. This is a very basic example, a simple example of modular symmetry. What we actually mean by modular symmetry. So see the figure above clearly shows. Have just discussed this only, why this lattice is described by the omega 1 and omega 2 and alpha 1 alpha 2 are equivalent. Just what I discussed with respect to this figure. So just yeah, now let's move on to torus. I'm just just skipping this for now. Torus is basically it's not it's just, see you have a flat space, and then if you just join the opposite edges, you get a cylinder, and if you join the opposite circles, you get this shape called a torus, this tire kind of shape, this donut kind of shape. But basically the geometry, see basically you converted this plane two-dimensional plane to this donut. So the mathematics that describes as normal 2D plane should be capable of describing everything, every feature, every aspect of this donut shape, right? They're equivalent, right? This can be transformed to that, right? So, and why have I included this? Because it is somewhat relevant in the sense, uh, if you want to understand this topological space and everything, but for now we'll just leave this. Now let's move on to fundamental region. This is the last portion of the video, the second last actually. After this I will discuss modular forms a bit, and yeah, maybe congruent subgroups. That's all. But yeah, the main part is over. I guess I think this should not take a lot of time. It will take some time, of course. Anyway, I targeted to finish the video within 2 hours, but I don't think it's already 1 hour 47 minutes. I don't think I can do within 2 hours. But anyway, let's see what I can do. So fundamental region. So see, usually we define a complex torus. Torus is just this thing, but yeah, it's just this. You can think of it as a plane, two-dimensional plane, a plane lattice, just like this kind of lattice, right? It is equivalent to the donut as well. So anyway, just don't focus too much on the torus right now. That is not really important. Just forget it. Okay. Just forget all of this. Not important right now. Basically, okay. Let me just briefly tell you in short. Let me not read line by line all these technical terms which you may not be required right now. Plus, not all of my viewers can probably understand this just by reading. So actually, I have plans to elaborate on these parts before I finally publish this whatever you call this article. But yeah, right now just forget the torus part. So this is how we define the fundamental region. Just don't get too overwhelmed by the mathematics. First, let us look at the figure. Yeah. So this is basically the upper half of the complex plane, capital H, right? Just See, this is the real number line 0, 1, 2. The below this, just forget, we are not interested. And the upper part, this is the upper half of the complex plane. So that means this is the real number line and this is the complex number line. So this is basically 1, that means it's actually I. This is 1.5 I. This is the imaginary line and this is the real line. And this is the complex plane. So the fundamental region is a region on the complex plane. So basically this shaded region, this shaded in gray, this is the fundamental region. Plus these boundaries, this red boundaries, this and this. Only in the second quadrant. We don't take the counterpart in the first quadrant. We don't take that full boundary. I mean, we don't take this and this as well. That is why I've shaded, this is in deep red, you see, deep red. So all the points lying in the inside this region, in this gray part, they belong to the fundamental region, plus all the points lying only on this boundary and this boundary, not this boundary and this boundary. Equivalently, we could have taken this and this. In that case, we should have ignored this and this. I mean, either you have to take the boundaries on the first quadrant or the second quadrant. So conventionally, I took the second quadrant one. So this is how we define the fundamental region. Now, how to define this mathematically? See, this circle you consider. Just follow my pointer. This circle. This circle, the center is at the origin, and it's a semicircle. I mean, because we ignored the down part, but it's actually the semicircle. The center is at the origin and the radius is 1. You see, this radius is 1. All this radius is 1. See, this is also 1. This is also, see, 1. This is also 1. I mean, the magnitude is 1. So the equation of a circle centered at 0 and radius 1 is x square minus y squared. Sorry, x square plus y squared equals to 1. Right, because the center is 0 comma 0 and the radius is 1. So this is how we can define the unit circle. And see, this is how we have defined, right? So u, what is u? First of all, let us see what is u. U is z belongs to h. That means all the complex numbers which belongs to the upper half of the plane, such that mod z greater than 1. So x square plus y square is mod z square actually. If we express the complex number z as x plus iy, we have been doing a plus ib, but let's say x plus iy. So that means basically x plus iy, the complex number z is x plus iy. That means on this plane it will be x comma y, right? X is this part x and this is y. So, and this circle it's x square plus y square, so that is z square, or actually mod z square. But we want all the points outside the circle. You see, inside the circle, these points, they are clearly not a part of the modular group. I mean the fundamental region. So we and if we take mod z less than 1, see, mod z equal to 1, x square plus y square equals to 1, they define all the points on the circumference of the circle. Less than 1, they define all the points inside the circle. Greater than 1, define all the points outside the circle. So u is mod z greater than 1, and we have mod rez, that means mod x, basically the horizontal coordinate, less than half. So mod rez less than half, that means minus half less than rez, or real part of z, less than half. So that means minus half less than real part of z, less than x, less than half. That means x lies between minus half and half. So see, this is minus 1, this is 0. So this is minus half and this is plus half. So x, we are already constraining x lies between these 2 points, and plus we are saying mod z greater than 1. That means we are, so between these 2 points we are only considering these gray points, because it must lie outside the unit circle, mod z greater than 1. So u means we have already defined all the gray points. So that this is how we define u. But the fundamental domain is u in addition with something else. That is why we have taken union. And that something else is c. Basically, c, z belongs to h such that mod z greater than equal to 1, rez equals to minus half. So x is equal to minus half, that means this line plus, but mod z greater than equal to 1. That means equal to 1 means we will consider this point on the circumference, because equal to 1, and all these points greater than 1 is also there. So that means this red boundary we are defining by this. And one more union, mod z equal to 1, rez less than equal to 0. So that means x less than equal to 0, that means this part, right, this part. We have already constrained u, so we cannot go beyond, so just this part. And we are saying mod z equal to 1, that means just the circumference of the circle in this part. That means we are defining this. So this is the the complete mathematical definition of modular, of the fundamental region of the modular group. Now what is the, I mean the benefit of, I mean what is the use of fundamental region? What is the fundamental region? Why are we defining it like this? And what is the definition? That we need to understand. Yeah, we have just defined it like this, but why suddenly this definition? What is so special about this region? right? That is what we will discuss now. Okay, fine. Just let's just ignore this for now. Not required. I've discussed more or less whatever is needed. Yeah, this one you see. We already discussed T and S, the generator matrices. So this is how the matrix T is defined: 1 1 0 1. What did I say? T. What does T just shifts by 1 unit to the right. Translation: T transforms the point Z to Z plus 1. So you see, if we multiply this matrix and with the column matrix Z over 1, C will get Z plus 1 over 1. So Z is being transformed to Z plus 1. And integer powers of T or T to the n, where n is a positive or negative integer, has the general form 1 n 0 1. So if you left multiply the matrix T, here just that is just T to the n with n equals 1 with the basis of a lattice given by Z comma 1. See, just what I told you, we get Z plus 1 comma 1. So that means the transformation is Z to Z plus 1. So, and again, if we try to think about it in terms of the lattice or torus, this tells us that the torus described by Z is equivalent to the torus described by Z plus 1. In other words, we have invariance under this transformation, right? Because see, clearly Z and Z plus 1 generate the same lattice lambda under the transformation, since the matrix T belongs to the modular group. T to the 0, S to the 0. I mean T to the 1, S to the 0. T and S are generated, so T belongs to the modular group. Right. Now if we define Z prime to be Z plus 1, and you look at this figure. Look at this figure. You see, yeah, the figure below shows that a T transformation tau to tau plus 1. I couldn't get a figure with Z, so just in place of Z in the figure they have used tau. So see, this was 1 and this is tau. So these are the lattice points, and this is tau plus 1. See, this is 1, this is tau. So if it is a resultant vector, this is tau plus 1. Now this is 1 and this is tau plus 1. So this shaded in gray parallelogram, this is the fundamental parallelogram for tau plus 1 comma 1 lattice. But again you see the same points. So clearly you can see that tau plus 1 comma 1 and tau comma 1, they describe, they generate the same lattice. That is what I'm trying to see. But now you see, suppose Z plus 1, let us say it is Z prime. Then Z prime equals to Z prime plus 1 is also a possible transformation, a T transformation. Now Z prime plus 1 will generate the same lattice as Z prime, which in turn generates the same lattice as Z. But what is Z prime? It is Z plus 1. And Z prime plus 1 is Z plus 1 plus 1 or Z plus 2. So Z plus 2 and Z are the same. Similarly, Z plus 3 and Z are the same. And Z plus any integer, it will generate the same lattice as Z. So that is why we in general we use this T to the n form. We raise T to the integer power. And this is the general form 1 n 0 1. So the thing about the generator matrix T is that there are infinitely many possible T's, because n is an integer, so there are infinitely many integers, positive or negative. You start from T to the minus, say 10, minus 9, all of these are possible. See, 1 minus 9 0 1 is T to the minus 9, T to the minus or plus T to the any integer, it's a T transformation. They are of all of the same structure, same thing, but they will transform. For instance, T transforms by 1 unit to the right, but T square, that means 1 2 0 1, it will transform by 2 units to the right. T to the minus 2, that means 1 minus 2 0 1, it will transform by 2 units to the left, because minus 2. So all T does is just a horizontal transformation. T will only transform a point horizontally, left or right, by 1 unit or by n units. That depends on the n, of course. But T will never move a point vertically, shift a point vertically. Okay. But now, yeah, so this is the general form of the T matrix. T matrix, this, and T to the n is this. Now let's look at the S matrix. The second kind of transformation is called S transformations, and this is the transformation matrix. S is defined like this. You see 0, minus 1, 1, 0. See, A square is minus I and S to the 4 is I. See, if you can just verify, you have the matrix, you can just verify that they will hold true. You can also verify, but see, in case of S, we don't have infinitely many possibilities, because S to the 4 is I and S square is minus I. So see, S is S, S square is minus I, S cube is minus I into S cube is what? S square times S, but S square is minus I, that is minus I times S, that is minus S. S to the 4 is again I. S to the 5 is S times S to the 4, that is S times I, that is just S. S to the 6 is again, what is S to the 6? It is S times S to the 5. So that is S times S to the 5 is again S, that is S times S, that is S squared, which is again minus I. S to the 7 is S times S to the 6, which is S times minus I, which is minus S. S to the 8 is S times S to the 7, which is S times minus S, which is minus S squared, but S squared is minus I, so that is minus minus I, that is I. So you see, even even as n tends to infinity, n is a positive integer, whatever. Of course, n is a positive integer here. So see, we started from, even for negative integers, it doesn't matter, whatever. S is such a matrix. You see, we started with S, S to the 1, S to the 2, S to the 3, S to the 4. You see, it's a cyclic order. The result of any integer part of S, S to the n, will always be either S minus I, minus S, or I. No matter what, it will, we will get only these 4 values. In case of T, it was not the same thing. We got a general form, but yeah, for infinitely many n, we got infinitely many T's, T to the n's. But for S, it's a periodic, it's cyclic. We will get only these 4 values, no matter what. It will keep repeating, no matter as n tends to infinity. Even for negative integers, you see the set of all possible values of S to the n is still finite. You can check it if you want. And now if we left multiply the matrix S with the basis of a lattice given by z comma 1, just like we did for T, we will see that we get 1 comma minus 8, because of course S transformation is this, right? Z2 minus 1 over Z. See, 1 comma minus 8, that means minus 1 over Z, right? This is basically 1 over minus 8, right? So this tells us that the lattice generated by Z is equivalent to the lattice generated by minus 1 over Z. Since clearly the matrix S belongs to the modular group. Again the same thing. But yeah, in case of T, it was easy to visualize. But in case of S, you see, S transformations are essentially conformal mappings in the complex plane and are difficult to visualize. We can get a rough idea of S transformations by considering an arbitrary complex number Z equals A plus IB, expressing minus 1 by Z in the form of U plus IV. See, minus 1 by Z means minus 1 by A plus IB. That means you have to rationalize, because the denominator must always be real. So that means, of course, you know how to rationalize a complex number, right? You just multiply with the conjugate of the complex number, multiply both the numerator and denominator, and then you get you express this minus 1 over Z in the form of U plus IV, where U and V are functions of A and B, and then you plot some test points on the UV complex plane, U versus V plane, and guess the approximate shape of the transform curve. Yeah, this can be done, but yeah, it's not as easy to simply visualize S transformations just like we did for T. It's a bit more difficult to visualize. Also, we must keep in mind the condition that Z must belong to the upper half plane H. The S and T transformation. Now here we will actually see this confusion. This actually, when I was studying, this was a confusion that I had to face as well. So it's better I cleared this, because yeah. The S and T transformations generate the modular group. We can also verify that for the matrices S and T as defined above, S to the 4 is I and S to the S square equals ST cube, where I is the second order additive matrix. Now, to make sure that the modular group acts faithfully on the upper half plane H, we define the projective special inner group as the modular group and not SL. So initially I told you that SL2, C is the modular group. So far that is what we have been considering. Actually, it is the full modular group. But in case of the fundamental domain and everything, we consider PSL2, C, that is the projective special unit group, second order of integer, as the modular group. Because SL2, C does not act faithfully on the upper half plane, but PSL does. So that in this case, we consider this to be the modular group. Now, why this does not act faithfully, but this does? Because you see, that is why in this case, whenever, see, the full modular group is SL2, C, but we define the fundamental region with respect to this PSL2, C. So don't get confused, because sometimes modular group means SL, sometimes PSL2, C. Now, why? Yeah, so in the very beginning, I already discussed a little about faithful action. It's a group action. Sorry, oh no, not this. Okay, yeah, group action. The action of a group G on the set S is faithful if for G star S equals S. I mean, if G star S equals S, then that means it is only possible for G equals the E, the identity element of the group. Otherwise, no, for any other element of the group, this will not hold. G star S equals S, where S belongs to the set, small g belongs to the group, capital G, and star is the group operation. So let's see why. You see, to make sure that the, yeah, okay. So SL2, C, first to consider SL2, C. The 2 by 2 identity matrix I is the identity element of the group SL2 comma Z. Of course, since for any matrix A belonging to SL2 comma Z, AX equals XA equals A holds true if X equals I. And of course, it holds true. Although, no, this is true. But see, although for some particular matrix A belonging to SL2 comma Z, AX equals X equals A may be true even if X not equal to I. I mean, even without, yeah, for X equals to I, this will definitely be true. But for some other A, also this might be true. We can call X the identity element of SL2 comma Z only if this equation holds true for all A belonging to SL2 comma Z. And note that the identity element of the group is unique. See, basically, see, faithful means what? If this is the case, that means X must be the identity element I. No other. If X is something else and this is still holding true, that means it's not a faithful action. But in this case, you see, even if X is not equal to I, we can actually find some matrix A belonging to the SL group such that this will be satisfied. So it's clearly not a faithful action. See, we can call X the identity element of a group of this group SL only if this equation, that means if AX equals X equals A, holds true for all elements of this group. And note that the identity element of a group is unique, meaning that SL2 comma Z can have only one identity element and it is I. So we already know that I is the identity element. That means even if we can find some other matrix such that this is satisfied, that matrix is not the identity element, right? So that means why is the action of now? So this is about the special unit group. Now, why is the action of PSL, projective special unit group, is faithful but not that of SL? See, consider negative I. I mean the negative of the identity matrix. See, minus I belongs to SL as well, a special unit group, but it is not the identity element because identity element can only be one and it is already I. But you consider the complex number Z equals 1 plus I. It's a complex number, right? Clearly Z belongs to H. It belongs to the upper half. See, the imaginary part, the Y part is positive. It's just 1. It's 1 I. Now multiplying minus I with 1 plus I represented as the column matrix as usual. We see this is the minus I and we get what we get. Just do the matrix multiplication, we get minus 1 minus I over minus 1. So just do the division, cut the minus, we get 1 plus I. So see, the original point was 1 plus I and the final point after the transformation is also 1 plus I. So that means minus, so 1 plus I means Z. That means minus I times Z is equal to Z. And minus I belongs to special unit group, but minus I is not the identity element. That means even if minus I is not the identity element, but still it is satisfying this equation. That means the special unit group, it's not a faithful group action if we use the special unit group, right? For the action to be faithful, minus I must be the identity element, but it is not true because identity element is already I and it must be unique. So this single example is enough to prove that the action of SL2 comma Z on a capital H is not faithful. But what about PSL, projective linear group? See, projective linear group is the quotient group SL2 comma Z modulo I comma minus I. The center, we discussed this already. So that means we already know how to define a quotient group. This means we multiply each element of SL2 comma Z with I and then with minus I, and PSL2 comma Z is the group containing all these elements. Of course, if we get an element more than once, we drop the duplicates and count it as a single element of the group. Now we consider matrix A such that A as well as minus A belongs to SL2 comma Z. If A belongs to SL2 comma Z, minus A will definitely belong to SL2 comma Z as well, because A belongs to 2 comma Z, minus I belongs to 2 comma Z. So, and a group operation is multiplication. So A multiplied by minus I, that is minus A, must also belong to 2 comma Z because SL is a group and it thus must satisfy the closure property. Yeah, now it is possible. So consider matrix A such that A as well as minus A belongs to SL2 comma Z. Now both minus I comma A and I comma minus are elements of PSL, because see, PSL means the quotient group. So that means we are I and minus I, that means we have to multiply all the elements of SL with I and minus I, right? So suppose A is an element of SL, special linear group, and we have to multiply that with minus I. I mean, this is one element of the projective special linear group among the other elements, and minus A is also an element of SL, and I is this, here we have I, so I times minus A will also be an element of the special projective linear group PSL, projective special linear group PSL. But minus I times A and I times minus A are the same thing. So that means the matrices, this means from here we can say that the matrices A and minus A in SL2 comma Z are actually treated to be equivalent in PSL2 comma Z, because in PSLC they are the same thing. I mean, of course, we are multiplying this with I and this with minus. I get your point, but see, they are the same thing in the projective linear group because both of these are the same matrices. See, actually, if you see, if we do this calculation for the quotient group, you will see that uh, for all A and minus A, A and minus A separate matrices in SL, but in PSL they are actually equivalent. So this means I and minus are also equivalent in PSL, right? Now, if I and minus are equivalent, then you see, then in that case, you see, for this case we got this minus I times z is z, but minus I is equivalent to I. So again, that means it is now it is a faithful action because I and minus are equivalent. So uh, even this equation does not violate the condition for faithfulness, because yeah, minus I and I the same thing. So this basically this is the same as saying that I is the identity element, so minus I is also the identity element, they're equivalent. So yeah, it's the identity element, so no harm done, it's still faithful action. In fact, we can prove that A times Z equals Z, A belongs to PSL and Z belongs to H if A equals I, which is the identity element of PSL, in addition to SL. Thus, the action of PSL on H is faithful. This is why in this case, especially when defining the fundamental region, we consider the, this full group. I mean, we consider the projective special linear group to be the modular group, but the full modular group is the SL2 comma C. Okay. Okay, now modular transformations from H to D. D is the fundamental domain. Any point, D is this fundamental domain. Any point lying inside the fundamental domain in the gray region or on these straight curves, they belong to D. And any other point on this figure on the upper half, they belong to H. Any other point outside the fundamental domain, that is what we mean by H. Of course, the points inside the fundamental plane, technically they are also part of the upper half complex plane. They are also part of H, but yeah, I mean, they are trivial cases. So for when we will talk about transformations from H to D, right? So this is H and this is D. So just like the fundamental parallelogram for the lattice lambda is a fundamental domain for the, I mean, this part again I actually didn't explain because this part for the action of A on the complex plane C, this was actually anyway. See, basically D is the fundamental domain for the action of the modular group gamma on the upper half plane H by fractional linear transformations. So fundamental domain, this fundamental domain is basically its fundamental domain for the action of the modular group on the upper half plane by fractional linear transformation. That means you take a point Z on the upper half plane and you multiply it with a matrix belonging to the modular group, and then you get a transform point Z prime. So this is what we mean by the action of the modular group on the upper half plane H by fractional linear transformations. And the fundamental region or fundamental domain, so the fundamental domain, we saw how to mathematically define the fundamental domain, but why is it special? I mean, why are we considering this particular region to be the fundamental domain? What is so special about it? So see, the fundamental region of fundamental domain for the action of modular group on H is the region D, for which the following conditions are satisfied. These three conditions. Number one, for all Z belongs to H, any point belonging to the upper half plane, there exists some matrix A belonging to the modular group satisfying AZ belongs to D. That means AZ means if we transform this point Z or Z by this matrix A, then the transform point AZ must belong to D. D is this, this uh, must belong to D means must belong to the fundamental region. D is the fundamental region. Again, group operations multiplication. And for a given Z belongs to H, there is only one possible A belongs to lambda, such that AZ belongs to U, that is AZ lies in the interior of D. See, for AZ to lie in the interior of D, I mean in this gray region, suppose here we have a point Z here, just where my pointer is, and then there is only one unique such matrix A, such that if we multiply A with this point Z, we will get Z prime, such that Z prime equals to AZ, such that Z prime will lie in the interior of this fundamental domain. There is only one such A. For any other matrix belonging to the modular group, this point Z will never be transformed to anywhere inside the fundamental region. There is a unique for a unique for a unique Z, there is a unique A. Yeah, okay. So the second condition is that the second point is that if Z prime belongs to D, z not equals to z prime and z prime equals to az. I mean, I know it's a, see, basically I'm telling you what this means in simple terms. We take 2 points belonging to the fundamental region z and z prime. They are not equal, of course, and they are related by a modular matrix. We are assuming the z prime is equals to az such that a belongs to the modular group. If all of this is true, then that means that inevitably means either, you know, this real part of z is exactly equal to plus minus half, and z equals to z prime plus 1, or mod z equals to 1 and z equals to minus 1 over z. See, if you, this what this means basically, you see, this means that the 2 points both belonging to the fundamental region can be mapped from one to the other by some a belonging to gamma modular group if they lie on the boundary of D. No 2 points in the interior of D can be mapped to each other by a matrix belonging to the modular group. So we take 2 points z and z dash inside the, I mean, belonging to the fundamental region, but if they lie in the interior of the fundamental region, the gray region, then they cannot be related by any modular transformation. Here we have a z, here we can then this z, and we have a z prime in the interior. Then, like just now we discussed, then that z prime and that z, they can be related by a unique modular matrix, that z prime equals to az. But if both z and z prime lie in the interior, in this gray part of the fundamental region, then they cannot be related by any modular matrix. But yeah, in some special cases, in the case, suppose if z is here on this straight line, it's still a part of the fundamental region, not the interior, but it is still a part of the fundamental region. So if z, if suppose we have a z here, let me see, let us look at the condition clearly. In that case, see, real part of z is plus equal to plus half or minus half, and z equals z prime plus 1, or mod z equals to 1. I mean, it lies on the circumference of the circle, and this means the 2 points both belonging to the fundamental region can be mapped from one to the other by some modular matrix if they lie on the boundary of D. I mean, basically, yeah, that is, so if 1 point is here and then this point is here, I mean, if you just do a simple t transformation, it will be shifted by one unit to the right. See, this is minus half, this is plus half, minus half plus 1 is plus half, it will move shifted here. I mean, see, the points on this boundary, they are not part of the fundamental region, right? On this boundary are. And similarly, any point on this boundary, if we just apply a simple S transformation, they will be shifted to the corresponding point on this part, on the semicircle part, their reflection in the first quadrant. But yeah, if we have a point here and maybe, I mean, then they can be related. But yeah, no 2 points in the interior of the fundamental region can be related by a modular matrix. We will be proving all these 3 points, very rigorous proof. Once you get this proof, you will actually know why, you will actually understand what the fundamental region is all about. The third point is a stab z, which means the stabilizer of z is I. That means a stabilizer of z means az equals to, if az equals to z, that means a is a stabilizer of z. Here it is I, because yeah, for all z belongs to the fundamental region, if a equals to I, then of course I z equals to z. If you multiply this point z with the identity matrix, you will always get back z itself. But basically, stabilizer means it's a matrix such that if you use the matrix, if you use this transformation to, if you use this matrix to transform a point, you get back the point itself. It's a kind of self transformation. I mean, so these are called fixed points, because fixed points under these transformations, under the stabilizer matrix, because under this transformation, under this matrix, the point does not transform to some different point, it comes back to itself. See, z was the original point, we transformed with a, but az gives back z, gives z back to us. But yeah, I is the trivial case. I is, for any z, if we multiply with I, we get back z itself. I is not what we're interested in. But for z equals to small I, this is the identity matrix I. Okay, this I is the a matrix. This holds for any z. But for z equals to small I, that means 0 plus 1 I, z equals to e to the 2 pi I over 3, which can be expressed in Cartesian form as well, and z equals e to the pi I over 3. For these particular z's, I is not the only stabilizer. I is a stabilizer for any z. It's a trivial case. But for these 3 values of z, which are called the fixed points, for these 3 values of z, az equals to z holds for I as well as some other matrix as well. We will find out what those matrices are. So no point except these 3 fixed points. These are the fixed points in the modular fundamental domain. I mean, for the modular case, these are the fixed points. You see, z equals to I and z equals to 2 pi I by 3. I mean, z equals to I and z equals to e pi I by 3. Both of these belong to the fundamental region. And this does not belong to the fundamental region, but this, if you can just shift this point by 1 unit to the right, just a simple t transformation, then you get this point. So they're the fixed points. And no point except these three fixed points belonging to the fundamental region. Actually, two of them belong to the fundamental region, but we assume the third one as well because we can just draw a simple shifting. Technically, yeah, is mapped to itself by any matrix. So yeah, no point except these three fixed points is mapped to itself by any matrix belonging to the modular group other than the identity matrix I, which is the trivial case. And since the three fixed points lie on the boundary of the fundamental domain or D, we see previously we claimed this, right? So no 2 points in the interior of D is related by some matrix A. So this claim is not violated. Here they're the same points, of course, because yeah, except for the trivial case when A equals I, since I maps any point to itself regardless of whether the point belongs to the interior of D or not. So yeah. Yeah, so first let's discuss about fixed points and why these 3 points are, mentioned above are the fixed points. See, a fixed point or invariant point represents a value that does not change under a given transformations, in our case a modular transformation. And basically, as I already told you, a fixed point maps to itself under the appropriate modular transformation. So for some point Z inside the fundamental region, the matrix A belonging to the modular group Z is a fixed point under the transformation A if A is equals Z. It's obvious that every point is a fixed point under the transformation A if A is the second order identity matrix, but again, it's trivial case, so we ignore this. Other than that, Z equals to I is a fixed point under the transformation matrix S, as we already defined S above. I mean S, I mean the way we defined this is your S, just a second. Yeah, this matrix, this. This can be easily verified. You see, if you just S already belongs to the modular group, of course. See, if you just S is called the stabilizer of I, since the Z equals to I remains stable or fixed under the S transformation. So we can verify this by pre-multiplying the matrix S with the two. By pre-multiplying the matrix S, yeah, with the two. Two cross one column matrix with its first element as I and the other element as 1. Yeah, I, that is how we write. So this operation gives back another 2 cross 1 column matrix with the first element as 1 and the second element is minus I, which essentially translates to minus 1 over I, which is I, using I square equals minus 1. If I square is minus 1, so that's basically, if we just multiply both numerator and denominator with I, then we have minus I over minus 1, so that is just I. So I remains I under S, Si equals to I. One more fixed point, this one for the matrix ST is the point, you see this point already told you, Z equals e to the 2 pi I by 3, which can also be written as minus half plus I root 3 by 2. So basically it is this point, you see. I was this point here, this point, just where this red curve has ended. And the point right now I talked about e to the minus 2 pi I by 3. This is this point, this boundary. And the other point, the third fixed point is just the opposite, the reflection, this boundary. So again, this point is not directly related to this point, but yeah, it's just, they're just related by simple T transformation. We can just add one, we will get back this point, right? This point, it's not technically a boundary of the modular of the fundamental domain, because this boundary, it's not part of the domain, just this one. Yeah, I mean, some people say that we should define this and all this boundary as a fundamental domain, but that is not how it works. I mean, then you have to make some modifications in the way the fundamental domain is defined. As far as I mean, this is actually a very pretty confusing topic, but as far as I researched on the internet, I did quite a bit of research. This is what I concluded, and yeah, I also confirmed it. So I think yeah, this is okay. So yeah, for this point, this is in the polar form representation. In the Cartesian form, this is minus half plus I root 3 by 2. You see, root 3 by 2 is approximately 0.86. So you see this the y coordinate. See, this is approximately 0.86. And minus half, this is minus half. So minus half plus I root 3 by 2 is this point, right? So you see, this is, where was I? Yeah, if we plot this point on the complex plane, which belongs to the fundamental domain T, is the vertex at the intersection of the two red curves in our case. Finding the product of the matrices ST and pre-multiplying it with the 2 by 1 column matrix with its first element as minus 1 plus I root 3 and the other element is 2, because see, minus 1 plus I root 3 whole divided by 2, that will give you minus 1 by 2 plus I root 3 by 2, right? This thing. We get another 2 by 1 column matrix with the first element is minus 2 and the second element is 1 plus I root 3, which on rationalization translates the original point, translates to the original point minus half plus this. I mean, you get back the same point. So this is again a fixed point under this under ST. Note that if we would have taken the fundamental domain to be U plus the reflections of the two red curves in our figure about the vertical axis, which is equivalent to what we have done, then the point e to the 2 pi I by 3 would not belong to the fundamental domain. In that case, along with z equals to I, the point z equals to e pi I by 3, that is plus half the other vertex, right? This one I'm talking about, this one, yeah, this one. See, this was minus half plus I root 3 by 2, and this is just plus half I root 3 by 2. And then this would be the other fixed point. This case for TS, not for ST. So you see, e to the pi I by 3 is just e to the 2 pi I by 3 shifted to the right by 1, right? So hence those 2 points are related by the transformation t. T e to the 2 pi I by 3 equals e to the pi I by 3. So clearly all the fixed points lie on a boundary of the fundamental region and not in the interior U, right? So far, so good. Okay. So yeah, now you see, now we have to we want to guess the general form of the matrix A such that A corresponds to a fixed point transformation for some point z equals to d. We already know. See, for I, the S is the matrix, this S under which I is a fixed point. Then for this point it is ST, and for the other one it is TS. But we need to guess the general form of the matrix. Let us try. So it will be a good mathematical exercise, right? So we first of all we start by setting imaginary part of AZ equals to imaginary part of Z, because AZ equals to Z, the very condition of fixed point. So if AZ equals to Z, then their imaginary parts and their real parts must be equal. Because if AZ and Z are to represent the same point in D on the complex plane, their imaginary parts, the corner vertices, must be the same as well as the real parts. So if imaginary part of AZ is equal to imaginary part of Z, then see, it can easily be shown that imaginary part of AZ is equal to this imaginary part of Z over CZ plus D mod square. Why? Because A is this matrix, small a, small b, small c, small d. So you just do the multiplication Z, AZ. If you do AZ, and if you do the rationalization, what is Z? Z is what? A plus IB or X plus IY, whatever you have assumed. So then if you just do this, for Z equals X plus IY, imaginary part of Z is just Y, and the matrix A corresponds to the linear fractional transformation Z equals AZ plus B CZ plus D, and AD minus BC equals to 1. If you use all these conditions, this one is a pretty simple mathematics. I'm not showing this. Then you will get that you can show that imaginary part of AZ is this. I mean, just think about it. Imaginary part of AZ. So what is AZ? This is, this is Z and that is A. So Z is X plus IY over 1, and A is just ABCD. So if you just do it and do the matrix, you get this thing, and then you write that in fractional form and you separate the imaginary part. That is what you want, the imaginary part of A. And you see it will be this part. It will be this thing. For Z to be a fixed point under A, imaginary part of AZ, yeah, this we already told this must hold. So that means, you see, if this should be equal to this and just this, then that means this denominator, this must be 1. CZ plus D mod squared must be 1. So what does this mean? This represents a circle with radius 1 over mod C and center on the horizontal axis at the point minus D over C, comma 0. I mean, just divide this by C, that is Z plus D over C mod squared equals to 1 over C, or 1 over C, 1 over mod C whole squared. But yeah, it's the radius squared, so the radius will be 1 over mod C. And yeah, as for this, what is Z? Z is X plus IY. So if you can again distribute Z and all, you will see that the center of the circle is minus D comma C comma 0, because with the X, with the real part, there will be this D comma C, minus D comma C. But with the imaginary part, there will be nothing. So it minus G comma C 0. That means the center of the circle lies on the horizontal axis, since this is 0. And this Z must lie on the circumference of the circle, right? Yeah, because this is equal to, right? Equal to. So Z must lie on the circumference of the circle. But for Z to also lie inside the fundamental region D, because yeah, we have already assumed that Z lies inside the fundamental region D, right? If AZ and Z are to represent the same point in D. Now, so think about this. Z lies on the circumference of the circle plus Z, but Z must also lie on the inside the fundamental region D. That means if the circumference and the circle is just like this, You see, the circle is just a circle with its center on the horizontal plane, not 0 exactly, but yeah, somewhere here. So that means if the radius of the circle is very small, then the circle is here, then z lies on the circumference of the circle, then clearly z cannot at the same time lie in the fundamental region as well, because there will be a gap in between. So that means the radius should be at least 1. It should be greater than 1 also. That is also allowed. That's also good. This is see, this you have to visualize. It's I'm sorry, because due to time constraints and everything, I cannot show you all the figures and all. But this you have to visualize. If you give a little bit of thinking, I think it's nothing beyond you, beyond anyone. Okay, so for z must lie on the circumference of the circle, but that means the circumference of the circle must touch or must enter or at least touch the fundamental region, because z must also lie in the fundamental region. So that means the radius of the circle must be at least 1 or greater than or equal to 1, right? So 1 by mod c greater than or equal to 1, or mod c less than or equal to 1. So this means c can be 0, 1 or minus 1, because it's an integer. And mod c less than or equal to 1. So that means minus 1 less than or equal to c less than or equal to 1, right? So c is minus 1, 1 or 0. So consider c equals plus minus 1. Under this condition, the center of the circle becomes plus minus d comma 0, because it's minus d over c comma 0, and c is plus minus 1. So for the circumference of the circle to at least touch the fundamental region d, d must lie between minus 1 and plus 1. Meaning d is either 0, 1 or minus 1, since d is an integer. Because if the center of the circle radius 1, since c equals plus minus 1, is at any point beyond this range, the circumference of the circle will never touch the fundamental region d, and thus z will not belong to d. Let me just simply show you. Okay, so this circle, the center is at origin 0, 0, and yeah, for this circle, if the radius is at least 1, the radius must be at least 1 or greater than 1, only then we can say the circumference of the circle will touch or enter the fundamental region. But this is not enough. This condition is not enough, because in our case, the circle center is minus d over c comma 1. So for c plus minus 1, it's minus d comma 1. So suppose if the center is the circle is here, then also it's a possibility the circle will might enter the fundamental region if the center is here minus 1 and the radius is 1, then the circle will touch the fundamental region exactly at one point, at this point. You see, at this point, this circle we're talking about, this circle, it cuts at exactly one point. But if the center is beyond minus 1, say, suppose the center is here, then here, then this circle, also center is here, then this circle, see this circle, it will never, and the radius is already 1, right? So it will never touch the fundamental region. There is a huge gap. Similarly here also, if the center is beyond 1 on this side, beyond positive 1 on this side also, the circle will never touch the fundamental region. I mean, it can never be beyond that, right? So that is what I'm saying. So that means the for c equals to 1, the values of d are also constrained. D can either be, that is what I'm saying, d can either be plus 1, d can either be minus 1 or plus 1. D must lie between, I mean, d can either be 0 or minus 1 or plus 1, because the c, d, a, b, all of them are integers. So keeping all this in mind, we can fix c equals to 1 and d equal to 0, because for c equal to plus minus 1, 0 is a valid value of d. Then we get a matrix of the form c, a, b, c, d. So it's a minus 1, 1, 0. See, c is 1 and d is 0. And we know that AD minus BC equals to 1. So since D is 0, so AD is 0. So minus BC must be equal to 1. C is 1, that means minus B must be equal to 1. Or B must be equal to minus 1. So from this condition, we already get B to be minus 1. And A can be anything as, because D is already 0. So A doesn't matter, A can be any integer. So choice of A is arbitrary as long as it is an integer. But to satisfy AD minus BC equals to 1, B must be minus 1. So see, if we put A equal to 0, then the above matrix is actually S. You see, this was S. Right? This was S. 0, minus 1, 1, 0. And this is what we mathematically derived. A minus 1, 1, 0. If we put A equal to 0, this is S. Under which Z equals to I is a fixed point. Right. For A equals to 1, the above matrix is TS. You can just, you know T, you know S. You can just multiply TS and you get the same thing if you put A equals to 1 here. Under which this point is a fixed point. Yeah. Now let us set C equals to 1 and D equals to 1. Again, they're valid choice, you see. Then we get a matrix of the form this, because C and D both are 1 and AD minus BC equals to 1. So A 1, that is just A minus B 1, that is A minus B equals to 1. So B is A minus 1, right? So that is what I've written here, B is A minus 1. Here also the choice of A is arbitrary, but yeah, B is A minus 1 to satisfy AD minus BC equals to 1. And here also for A equal to 0, you get what? 0, minus 1, 1, 1. You get actually S. If you multiply S and T in this order, you will get 0, -1, 1, 1. So for equal to 0, the matrix ST under which this point is a fixed point. So that means, yeah, we actually, it's not a rigorous mathematical derivation, but we actually followed the logic that for fixed point, imaginary part of Z must be equal to imaginary part of AZ, and following the logic, we actually derived the we actually could derive these matrices S, ST, and TS fundamentally, mathematically. That is what I wanted to do in the first place, right? Now we have to prove the first condition of fundamental region. You see, there are three conditions. The third point is already done, proved. We will prove 1 and 2 now. Okay. So see, what was point number 1? For all point belonging to the upper half complex plane, there must exist some matrix belonging to the modular group satisfying AZ belongs to D. Right. I mean, any point outside the fundamental region on the upper half of the complex plane can be transformed to some point belonging to the fundamental region by some modular matrix, by some unique modular matrix A. That is what the first point. So let's see if we can mathematically prove this. Okay. Okay. So for some point Z, it belongs to H and Z not belongs to D. See, we ignore the trivial case of the transformation of some Z belongs to D to itself, because if the point Z belongs to the fundamental region, then also technically it belongs to capital H also, the upper half plane. But then what we will do, the transformation matrix, then I will transform it to itself. It's already inside the fundamental region. So what is the point of transforming it into the fundamental region? So we only consider those points Z belong to H and Z does not belong to D. I mean, upper half points in the upper half complex plane, but outside the fundamental domain. So for such Z, we can find some matrix A belonging to the modular group. A is a product of certain powers of the generator matrices T and S, as we have already discussed, such that the point AZ belongs to D. This is the first point of claim. Now we have to prove this. So geometrically, we take a point in H outside the fundamental region T and subject it to a combination of appropriate translations and inversions. That means T's and S, until it's mapped to the fundamental region T. For example, Z equals 1 plus 0.5 I. It's a point, see 1 comma 0.5. It's a point which belongs to the fundamental region. It's clearly outside the fundamental domain. See 1 comma 0.5. So this is 1 and this is 0.5. So the point is here. It's outside the fundamental domain. Clearly. Where was I? Yeah, here. So this point, it is mapped to Z prime equals 2I. Now 2I is this point. You see, it's this point. Somewhere here. I mean here. So it's clearly inside the fundamental domain. So this point can be mapped to 2I by some matrix of the modular group. That we have to prove. Of course it can. If we use the matrix, transformation matrix S T inverse. If it, T inverse means T to the -1 means just what? I already told you. This is the form, right? So just put n equals to -1. 1 -1 0 1. That is T to the -1. So, and we already know what S is. This is S. So multiply S with this, putting -1 in place of n. So then you will get ST inverse, and if you do ST inverse Z, where Z is this point, you will get 2I. And clearly ST inverse belongs to the fundamental domain because it's a combination of different powers of the generators S and T. And if you, but see, this is just, we just showed that. Say one more example, you can consider this point Z outside the fundamental domain, and but belonging to H, 1.3 plus 0.6 I. This is mapped to Z prime is 0.34 plus 1.34 I. This again belongs to the fundamental domain under the transformation T ST inverse in this case. And of course, both of these, they belong to the modular group. But these are just examples. But we have to mathematically prove that for every point, every Z belonging to H and not belonging to D, there exists a unique matrix A of this form, whatever form, such that it can transform Z to some Z prime which lies inside the fundamental domain. We have to do a mathematical general proof. Of course, we cannot take each and every possible Z and manually check. I just showed you two examples here. You can do the detailed calculation for these two examples. It might help. But yeah, now we will do the mathematical proof. So see, for every Z belonging to H and Z not belonging to D, there must exist some A belonging to the modular group which maps Z to some point belonging to the fundamental region D. In other words, for AZ equals to Z prime belongs to D. So let us start the proof, the general proof, that Z equals X plus IY. It's a general proof, so we cannot take any particular Z like this. We have to take X plus IY. Z belongs to H. So clearly X is the real part of Z and Y is the imaginary part of Z, and let A belongs to the modular group, this matrix is A, B, C, D, and obviously AD minus BC equals to 1. So evaluating AZ, what is AZ? It is this thing. We get this. Now rationalizing the result, so AX plus B plus IAY divided by CX plus D plus ICY. If we, and then if we rationalize this, we will get we rationalize this. Yeah, now we, okay, just a second. So now we rationalize the resulting complex number. Then by using this fact that imaginary part of z is y and z equals x plus iy, I'm sorry, yeah, and AD minus BC equals to 1. It's a I've not shown all the steps, but it's pretty simple. We can show that, we already discussed this. We can show that imaginary part of AZ is equals to imaginary part of Z over CZ plus T mod squared, right? But you see, in the previous case, we were doing for fixed points, so we assumed that imaginary part of AZ will be is equal to imaginary part of Z. Here, that is not necessary, but still, this result is important in this case also. So see, clearly, imaginary part of AZ is greater than 0 because it lies in the upper half of the plane. Imaginary part of Z is greater than 0 also. Imaginary part of Z is greater than 0 because Z is belongs to H, upper half of the plane. So by definition, and Cz plus D mod square is a positive quantity. So this is also greater than 0. This is also greater than 0. The RHS. So the LHS, imaginary part of AZ, must also be greater than 0. It's a valid conclusion. Now Cz plus D must be on the lattice generated by Z and 1. Because see, I already told you now, how do we define a lattice? See, it's defined by like this: m omega 1 plus n omega 2, and this is Cz plus D, or Cz plus D into 1, we can say. So Z is omega 1 and 1 is omega 2, so that is Z and 1, and C and D are integer. Here they're just m and n, right? So it's easy to see if you just think a bit why Cz plus D must lie on the lattice generated by Z and 1. This means that the distance of the point Cz plus D from the origin, which is given by mod Cz plus D, must by construction be greater than or equal to either plus minus z plus 0 modulus, or plus minus z plus minus 1 modulus, or 0 plus minus 1 modulus. Because otherwise the point C, if it's not greater than or at least equal to this, then the point Cz plus D will lie inside the fundamental parallelogram generated by Z and 1, which is not allowed. Then we already discussed when we were discussing lattices on 2D complex plane and the fundamental fundamental pairs. So that would contradict the fact that Cz plus D must lie on the lattice generated by Z and 1. See, basically the points plus minus Z comma 0, plus minus Z plus minus 1, and 0 plus minus 1, they are the vertices except the origin. Origin is 0 comma 0. They are the vertices of the fundamental parallelogram generated by Z and 1. One vertex will be just Z and 0. One vertex will be 0 and 1. Right, and the other will be the resultant vector. We take Z and 1, and plus minus we have taken C. Because just a second. Hence the possible points for Cz plus D closest to the origin are these, which is why mod Cz plus D cannot be smaller than this. And yeah, we use the plus minus symbols because with respect to some origin, the fundamental parallelograms, all of these, see, Z1, Z minus 1, minus Z1, minus Z minus 1, they're the same. It doesn't matter. Suppose, let's go back to that picture, you know, that figure, whatever that was, yeah. So suppose this, we have defined our fundamental parallelogram. Here, this is positive, this is also positive. I mean, lying in the first quadrant. So we could have defined this parallelogram in the third quadrant. Is the same thing basically. But for that, both x and y are negative. We could have defined this parallelogram in the second quadrant, in any quadrant. So all the possible values of x and y, all the possible signs, positive, negative, we have to consider. But here, since we are considering the magnitude, we have taken the modulus, but inside the modulus, we have considered all the possibilities. That's why we have taken plus minus signs. But see, they're all inside the modulus because, yeah, we are trying to find out the distance, the minimum distance. This is also mod Cz plus D. So essentially for mod Cz plus D, we have considered the cases C equals plus minus 1, D equals 0, and C equals plus minus 1, D equals, yeah, this thing, and finally C equals. So we have basically considered three cases: C equals plus minus 1, D equals 0, number 1. Number 2, C equals plus minus 1, D equals plus minus 1, and finally C equals 0, D equals plus minus 1. Why? Because see, these are the only cases. If you think about it, Cz plus D. So these the other cases are. I mean, if you do for these cases, for the other cases you can automatically do. These are the only cases, right? So we can define possible matrices A belonging to the modular group for these combinations of C and D. Of course, the constants on A and B can be obtained from AD minus BC equals to 1. That will always hold for any matrix belonging to the modular group. And then we can represent Z as a column matrix and verify that for AZ equals Z prime, the lattice generated by Z prime is the same as the one generated by Z. We can of course generate this same lattice using different combinations of C and D, but in all of the cases, this mod CZ plus D will be greater than these three, the three we took. But see, this set is finite. For a particular value of Z, uh, this set is finite. See, plus minus Z plus 0 plus, I mean, if we are given the value of Z, there are a finite number of elements in the set, right? It's not an infinite number of elements. So that means we can find its minimum, that smallest element of the set for a given set, and the value of Im, the imaginary part of Az, this value, you see this value, corresponding to the minimum value of Z, the minimum value of Cz plus G will be maximum, because imaginary part of Az is imaginary part of Z divided by this. So if Cz plus G, this minimum value we choose, the denominator is minimum, plus it is squared, then this will be maximum. Imaginary part of Az will be maximum. So the value of imaginary part of Az, this value of this corresponding to the minimum value of this will be maximum. Thus for a given Z, using the values of C and D, for which Cz plus D is minimum, mod Cz plus D is minimum, and finding suitable A and B such that AD minus B is equals to 1, we can find some matrix A belonging to the modular group such that the imaginary part of Az is maximum. Next, we find a suitable n belonging to Z, the set of integers, such that Tn Az. See, I know this proof is a bit mathematically involved, a lot mathematically involved, to be frank, to be honest, but see, it's a very important proof, and if you get it, it's a good mathematical exercise. So I think it should be clear up till here. It's nothing difficult. Now see our strategy. The next strategy is that for a given value of Z, we know the value of Z. So from here we can find the minimum one. We will find, see, we have some options. We can choose C. We have some options of C and D. From these different cases, we have some options, right? So from these options, we will see that for this particular value of Z, for what choice of C and D will my mod Cz plus D will be minimum. That we can do. And we can find suitable A and B as well, correspond, because we already know C and D. Now we can find A and B such that AD minus B is equals to 1 will be satisfied. And once we know A, B, C, D, we can define the matrix A belonging to the modular group such that this automatically for that matrix imaginary part of A Z will be maximum, because we have chosen them such C and D such that the mod Cz plus D is minimum. That we can do. Okay. So next we find a suitable integer such that t to the suitable integer n such that t to the n Az equals Z prime belongs to H, the upper half of the complex plane between minus half and half. This is possible. I mean, why? Because see, basically we already have Az. We already have Az. We have, in the sense, we have evaluated Az, and we know we have expressed Az as a complex number. Now we don't know where this complex number lies. I mean, in a general case, it can lie anywhere in the upper half of the complex plane. Like we are doing a general proof, right? But for some suitable n, if we pre-multiply Az by t to the n, we can bring the result, say Z prime, between minus half and plus half on the x-axis. Because you see, let's just go back to the figure. This one. Suppose the Z Az lies here, right here. This is what point is what 1.5. So if we choose t to be what? If we choose n to be minus 2, then t to the minus 2. If we do t to the minus 2, then this Az, then this point will be shifted. Suppose this point here, where the x coordinate is 1.5, it will be shifted twice to the left by 2 units. So 1.5 minus 1 is 0.5. That means first it will come here. Then 0.5 minus 1 is minus 0.5. Then it will come here. See, this it belongs. I mean, anyway, even if it comes here, I mean, it's clearly we can bring it somewhere between this region, minus half to half. If it lies here, suppose some random point, maybe say this is 1.3. Then also if we just move it to the left by 2 units, see, the t transformation t to the n can only move to the left or right by integer units. It cannot move to the left by 1.5 units, either 1 or 2. But if it's 1.3, so if we move by 1, then even if we move by 1, it will be 0.3. See, it already comes, it is between minus half and plus half. It is between minus 0.5 and plus 0.5. Right, 0.3 is less than 0.5 and greater than minus 0.5. So suppose we take a point far away to the right, which is not even visible in the figure. Say the point, the x coordinate of the point is say 72. Then we will take the n to be minus 73, the t to the minus 73. It will shift the point to be 73 units to the right. Any point, basically any point on the complex plane, any a to the z. It is possible to choose some integer n such that t to the n will bring the point here. Not necessarily always inside the fundamental domain, but at least here. I mean, between minus half and half on the x-axis. It could be here also. See here in this. So it's not inside the fundamental domain, but it's still between minus half and plus half on the x-axis. That is possible. It's clearly possible. I have shown you. I've shown you from the figure that. So you should understand that. Right. So you see, this is t to the n az. That is that this is yeah, this is possible. Just what I've told you, forget it. Okay, so now see, obviously the matrix T to the n belongs to the modular group, and it's possible to bring any point AZ belonging to the upper half plane H and AZ not belonging to D to some point Z prime such that it lies between minus half and half along the x-axis under the transformation T to the n for some suitable integer n. Now we're essentially shifting AZ horizontally left or right depending on the initial position of AZ until we can bring the horizontal component of AZ between minus half and half. No constraints to the vertical component of AC. So now let Tn A equals A prime. So since see we've already assumed that A belongs to modular group. So A can be expressed as some product of some powers of S and T. Now again if we multiply that with Tn, again then Tn A will also belong to the modular group clearly, since the matrix is generated by the products of all possible combinations of powers of S and T belong to the modular group. Clearly Tn T to the n A equals A prime also belongs to the modular group. Now also note that imaginary part of AZ equals imaginary part of A prime Z, which can be easily verified by multiplying the matrix A prime equals T to the n A with the column matrix Z and determining its imaginary part. See, Tn A means you're just shifting A, but you want the imaginary part of A is not making, see, you are shifting horizontally. That is what the matrix T does, the T transformation does. You are only changing the x coordinate, but not the y coordinate. So the imaginary part, the y coordinate is of AZ or Tn AZ, that is A prime Z, will remain the same, right? You can just do the calculation, which is pretty simple, but you can also just understand it visually. So in that case, if the imaginary part of AZ is equal to the imaginary part of A prime Z, but A prime is T to the n A. So if we have chosen A and Z such that imaginary part of AZ is maximum, then for the same A and Z, imaginary part of A prime Z is also maximum, where A prime is T to the n A, right? Now A prime equals T to the n A. We claim that any point Z belonging to H and Z not belonging to D is mapped inside the fundamental region D by A prime. In other words, A prime Z belongs to D. See, now we make a claim. We'll prove it, of course. Of course, we'll prove it. But right now, let us assume for a moment that any point Z belonging to H and not belonging to D is mapped inside the fundamental region by this A prime, such that A prime equals T to the n A, where n we have appropriately choose so that it lies between minus half and half. It is on the x-axis, and yeah, and that is A. In other words, A prime Z belongs to D. That is what we claim. Now, if you can prove this claim, then we prove the point one, what we were trying to prove, that for every Z belong to H and Z not belong to D, there must exist some matrix belonging to the modular group which maps Z to some point belonging to the fundamental region D. Now, the last claim, what is the proof? So let us assume the claim that for Z belonging to H and not belonging to D, A prime Z belongs to D is false. Let us assume it is false. Now we can prove the contrary, prove that we run into a contradiction. That means it must be true and our proof would be complete. Since real part of Z prime or real part of A prime Z, whatever, already lies between minus half and half, for A prime Z to not belong to the fundamental region, see, we are assuming our claim to be false. That means this thing A prime Z, it must not belong to the fundamental region, but it already lies between minus half and plus half. So for it to not belong to the fundamental region, A prime Z must lie inside the unit circle centered at the origin. Let me show you. Already we are constrained in this region between this minus half and plus half. Now we are assuming that our claim is false. That means this point does not lie in the fundamental region. The fundamental region, it extends infinitely upwards, but we are saying no, it's not here. So that means it must be somewhere here inside the fundamental region, inside the unit circle, somewhere here. This white part. See, follow my pointer. It must be somewhere here, according to our assumption, right? Okay, so far so good. But now you see, it must lie inside the unit circle centered at the origin. And in other words, that means what is the equation of the circle? It's mod a prime z less than 1. I mean, we are doing for the point mod a prime z, right? So for this point to lie inside the circle, mod a prime z must be less than 1. Now, if a prime belongs to the modular group, which obviously it is, we have already proved that, then S a prime will also belong to the modular group. S is again a generator matrix, and for the generator matrix S, C is 1 and D is 0. If you look at the general form of S, just a second, uh, just a second. Yeah, so if you look at the general form of S, where was S matrix? Yeah, this was S, right? So you see, here C is 1. I mean, A, B, C, D, if you just compared A is 0, B is -1, C is 1, and D is 0, right? So this is the form of S matrix. Now here also you see, here that is what we have, this knowledge we have basically used here. If A prime belongs to the modular group, then S A prime also belongs to the modular group. It's any combination of S and T. I mean the generators. So, and for the generator matrix S, C is 1 and D is 0. Thus for the transformation S A prime Z, using imaginary part of Az is this, we can write imaginary part of S A prime Z is imaginary part of A prime Z over A prime Z mod square. We can write this. Think about this. Why is this true? Because see, this is in general, this will be true. See, imaginary part of S A prime Z. Imaginary part of A Z is, this is in general, this is true. Now here you consider Z to be A prime Z, and here imaginary part of Z, so imaginary part of A prime Z. Fine. And this here we have the CZ plus D. Here Z is A prime Z. Right. So we have C A prime Z plus D mod square. But C is 1 and D is 0. So that is 1 A prime Z plus 0. That is just A prime Z mod square. Just if you just compare, you can get it. So this we have got. Now since A prime Z less than 1, mod A prime Z less than 1, obviously from, because we have assumed our claim to be false, that means it must lie within the unit circle. So mod A prime Z less than 1. So mod A prime Z less than 1, that means 1 by mod A prime Z whole square must be greater than 1. That means this thing must be greater than this. I mean, we're just multiplying this inequality with by imaginary part of A prime Z on both sides. So that means this thing here, I mean this equation we get easily, but the LHS is equal to imaginary part of S A prime Z. So that means imaginary part of S A prime Z is greater than the imaginary part of A prime Z, which is a contradiction because we chose A prime and Z such that imaginary part of A prime Z is the maximum, right? You see, we already told you. We already said, you see, we have chosen A and Z as the imaginary part of A Z is maximum, then for the same A and Z, imaginary part of A prime Z is also maximum. This is we have chosen. But here we're getting that there is something which is even greater than this. Some imaginary part of S A prime Z is even bigger than this. But this was supposed to be the maximum. See, we are doing the entire analysis for a particular A and Z, but the proof is general, says the choices of A and Z are arbitrary as long as A belongs to the modular group and Z belongs to, or Z belongs to capital H and does not belong to capital D. So thus the claim A prime Z mod A prime Z less than 1 must be incorrect, meaning A prime Z lies within the fundamental region D. Our last claim is true in that case. I mean the assumption which we did, we assumed the contrary, that is incorrect assumption. That means our claim that this A prime Z transforms any point inside the fundamental domain is correct, and this completes the proof. See, this completes the proof. Now our next claim is that the number two, point number two. What was point number two? Let me just show you quickly. So this was point number two. See, point number three we proved at the beginning. Point number one also we just finished proving, and point number two says that if Z prime belongs to D, Z not equal to Z prime, and Z prime equals to A Z, I mean, yeah, basically for 2 points both belong to the fundamental domain, they are not related by any modular matrix if they lie in the interior of the fundamental domain. Yeah, this proof is simple. I mean, the major part is already done, so let me just quickly cover this as well. It's almost a 3 hours video. Oh my goodness. But yeah, anyway, where was I? Yeah, here. Now our next claim is that for a given z belongs to H and z not belong to D, again we ignore the trivial case of the transformations by the identity matrix. Okay, we are not yet moving to point number 2. Our point number 1 is not complete. One part is left. We have proved that there is a matrix A belonging to the modular group that will transform any z belonging to H and not belongs to D inside the fundamental domain. But we have to prove that this matrix is unique. There is no other matrix that can transform the same point inside the fundamental domain to a point inside the fundamental domain, to a point belonging to the fundamental domain. That also we have to prove. So we have to prove that there is only one possible A belonging to the modular group such that AZ belongs to U. That is, AZ lies in the interior of D. I mean, yeah, actually, this is the second part of proof. Actually, I mean, even in the first case, I mean, there is only one matrix. So let us assume this is not true. Thus, for some Z in H and Z not belong to D, and for A1, A2 belong to yeah, for suppose we have two matrices. Suppose we assume that there are two modular matrices, both belong to the modular group, and we have 2 points lying in the actually we're doing the proof of point number 2 only. Sorry about this. And there are 2 points Z1 and Z2 both belonging to the fundamental, to the interior of the fundamental domain, and we are assuming that Z1 not equal to Z2, of course. So we are assuming that Z1 is equals to, I mean, Z2 equals to Z1 equals to A1Z and Z2 equals to A2Z. We are assuming. We are assuming the contrary. This should not be the case according to point 2, but we are assuming the contrary, and now we'll prove that this assumption is incorrect. See, Z1 equals to A1Z. That means what? This matrix A1, it transforms the point Z to Z1, and the matrix A2, it transforms the point Z, the same point Z to Z2. So the same point Z is being transformed to two different points inside the fundamental domain, Z1 and Z2, by two different matrices. But according to us, there should be only one matrix that can transform a point Z to a point Z prime inside the fundamental domain. Actually, we're doing the okay. Let's see. So this means what? From this, what we can say, Z is A1 inverse Z1. From this, you see, from this we can say Z is A1 inverse Z1. We're just multiplying both sides by A1 inverse, and also Z is A2 inverse Z2. If we multiply both sides by A2 inverse of the second equation, so both are Z, right? So equating them, we get A1 inverse Z1 equals A2 inverse Z2, or Z2 equals A2 A1 inverse Z1. Now again, if A belongs to the modular group, then the inverse matrix A inverse also belongs to the modular group. Now since A1 belongs to the modular group, A1 inverse also belongs to the modular group, and since A2 belongs to the modular group, the product A2 A1 inverse equals to say A3 also belongs to the modular group, because the group operation here is matrix multiplication. So A2 belongs to the group, A1 inverse belongs to the group, and we're multiplying them. So by closure property, their product A3 must also belong to the modular group, right? So that means Z2 equals this. This is A3 Z1. So Z2 equals A3 Z1, where A3 belongs to the modular group. Now it clearly violates the claim that we will prove next. Yeah. Now here we're using the point number 2. We are not yet proving the point number 2. We are finishing the proof of the point number 1. So according to point number 2, 2 points lying in the interior of the fundamental region Z1 and Z2, they cannot be related by any modular matrix A3. So for now, let us assume point number 2 is correct. That is what we'll be proving next. But clearly this is violating point number 2 if we assume that there are two matrices. So that means if point number 2 is correct, which of course it is, will prove, that means there is only one unique matrix, no A1 A2. There is only one matrix A that can transform a point from outside the fundamental region to the interior of the fundamental region. Now this completes the proof of the point number 1. We have just assumed that point number 2 is correct, which we'll prove next. Then we'll be completing all our proof in a satisfactory, mathematically rigorous manner. Right. So thus for a given Z belonging to the H and not belonging to D, there is only one possible matrix, modular matrix, such that AZ belongs to U. Now we will prove that no 2 points, the second point, the no 2 points Z1, Z2, Z1 not belonging to Z2 in U, the interior of the fundamental region D satisfies Z2 equals to A Z1, and for some A belonging to the modular group. First we start by assuming Z1, Z2 belonging to D. Without loss of generality, we assume imaginary part of Z2 greater than or equal to imaginary part of Z1. You could have assumed the contrary also. That's why I've already written WLOG, right? Without loss of generality. So now we assume Z2 equals A Z1, where the matrix A is given by the usual. So this is not allowed, right? But let us assume this and let us prove that this assumption is incorrect. So again, clearly imaginary part of Z2 is equal to imaginary part of A Z1, because Z2 is equal to A Z1, right? And imaginary part of A Z1, we can write imaginary part of Z1 over mod C Z1 plus D squared. And again, imaginary part of Z2 is greater than equal to imaginary part of Z1. So this is greater than equal to imaginary part of Z1. So see, from this, what we can say, imaginary part of Z1 over this is greater than equal to imaginary part of Z1. So this reduces, if we just cancel Z1, imaginary part of Z1 from both sides, this reduces to the inequality, we get this inequality mod C Z1 plus D squared less than equal to 1. So this is the interior plus boundary because it's less than equality is also there, and interior because it's less than. So this region, this is the interior plus boundary of the circle centered at minus d over c comma 0 with radius 1 over mod c. The same circle, we already considered this, right? Previously also. Now since z1 belongs to d, the radius of the circle must be greater than or at least equal to 1, so that because z1 must lie on the circumference of the circle also, or interior of the circle. Even worse, because the best case is the z1 lies in the circumference of the circle, it cannot go beyond that. But it must also belong to D, the fundamental domain. So the circle, the radius must be at least 1, 1 over mod C, the radius, it must be greater than or at least equal to 1. The same thing previously. Which means C mod C less than equal to 1. Since C is an integer, this leaves us with 3 possible values of C, 0, 1 and minus 1. So first let us choose C equals to 0. So this reduces C Z1 plus D mod square less than equal to 1 to since C is 0, this is just mod D square less than 1, which means D is either 0, 1 or minus 1. Now C equals to 0 and AD minus BC equals to 1 means AD equals to 1 because C is 0, so just ignore BC. So AD equals to 1, so if D equals to 1 then A is also 1, A has to be 1 because AD must be 1, and if D equals to minus 1 then A also needs to be minus 1 because AD must be 1. And again clearly D cannot be 0 because although it's possible geometrically, from this geometrically in the sense, yeah, from this it's possible, but here D cannot be 0. Why? Because if D is 0, then AD minus BC will be also be 0. D is also 0, C is also 0. So AD minus BC will be 0. AD minus BC will not be 1. But it must be 1 because we are considering A to be a modular matrix. So since we have fixed C equals to 0, so D cannot be 0. So either we have to choose A1, D1 or A minus 1, D minus 1, and C is 0. And B is can be anything. B is just B. As long as B is an integer, the choice of B is arbitrary. There is no restriction on B. Because anyway, we are multiplying B with C, C is 0, so ultimately B will not have any effect. So the general form of this matrix for these choices, the matrix is this: plus minus 1, B is 0, plus minus 1. Right, because A equals to D equals to 1 or equals to D equals to minus 1. So it's A, B, C, D, and C is 0, right? So yeah, you see, fixing A equals to D equals to plus 1, the above matrix is 1, B, 0, 1. So that is just T to the B, if you just recall. And for A equals to T to the B, since Z1 belongs to D and A Z1 belongs to D holds true if and only if B is either 0, 1 or minus 1. See, since Z1 belongs to the D and A Z1 belongs to D will hold true only if B is either 0, 1 or minus 1. Why? Because see, for other values of B, T to the B will shift Z1 left or right by 2 units or more. See, Z1 is already belonging to the fundamental region. So that means Z1 is between somewhere minus half to plus half. Now if we shift, yeah, now A Z1 should also belong to D, right? So that means B should either be 0. If B is 0, that means T to the 0 is the identity matrix. That means it's no change. That is allowed. If it is 1 or minus 1, then also see if it is in this boundary by 1 or minus 1, maybe it moves to the other boundary. That is still okay. But if we choose the value of B greater than, other than these things, say minus 2 or minus 3 or plus whatever, then T to the B will shift Z1 left or right by 2 units or more. Then it will clearly not lie within the fundamental region. A Z1 belongs to D will not hold true. Right? You see, you just see, look at this figure. It's clearly, look at this figure. See, we have assumed Z1 belongs to D. So see, even if Z1 is in this, suppose Z1 is here, this boundary. So T to the minus 1 is okay, it will bring it here. Or T to the, if it is here, T to the plus 1 will bring it here. Or if it is somewhere here, T to the 0 will keep it there. That is okay. But T to the 2, wherever it is inside D, T to the 2, T to the minus 2, T to the 3, T to the 4, T to the minus 5, any of these things, for any of these values of B, the point will be taken out, shifted to some point outside the fundamental domain. So that's not allowed. So yeah, it's not true that any value of B is allowed. If you think about it, only those values of B, B is either 0, 1 or minus 1, right? Since the width of the fundamental region D is 1 unit, no translation of Z1 belongs to D by 2 units or more can bring it to a point inside D. Thus B is either 0, 1 or -1. For B equals 0, A is the identity matrix. If I set B to be 0 and I've chosen A equals D equals 1, then A is the identity matrix, right? And A Z1 equals to Z1. Yeah, if it's A is the identity matrix, then of course A Z1 equals to Z1. So it's a trivial case again. If we assume A Z1 equals to Z2 and Z1 not equal to Z2, but it's a contradiction because here we're getting A Z1 equals to Z1. So this implies Z2 equal to Z1, but we assume Z1 not equal to Z2, so it's a contradiction. So for this case is discarded. Now for B equals to plus minus 1, you see Z1 belongs to D, Z2 equals A Z1 lies in the fundamental region D if Z1 lies on either the left or right vertical boundary of D, right? This is because T to the power plus minus 1 shifts a point left or right by 1 unit, and the horizontal width of the fundamental domain D is 1 unit. Now if Z1 does not lie on the boundaries but on any other point in D, any interior point in D, shifting it horizontally by 1 unit will never bring it to a point in D. So this proves that Z1 and Z2 cannot lie in the interior of D, they must lie in the boundary. And now let's consider the other case, that C is plus minus 1 and D is 0. See, we took all, there were all these possible cases, right? C, it could be 0, 1 or -1. So for C equal to 0, we took all the cases of D and we are finished. We have already proved that for C equal to 0, we have proved our claim that if the 2 points lie inside the fundamental domain, then no, they cannot be related by modular matrix. But now let us do it for C equals to, there are two other possible values of C, 1 and -1. So let's take it together, C equals plus minus 1. Right. So for C equals plus minus 1, and if C equals plus minus 1, and let's choose D equals 0. Okay. So in that case, this will just be what, plus minus Z1, and D is already 0. So plus minus Z1 mod square less than equal to 1, or just mod plus minus Z1 less than equal to 1, right? Because yeah, it's already squared and it's mod, so plus minus, and see 1 squared is 1, so we can just take the square root also, so doesn't matter. So mod Z1 less than equal to 1, which is the interior plus boundary of the unit circle centered at the origin. Now clearly for Z1 to satisfy mod Z1 less than equal to 1 plus belong to the fundamental domain, Z1 must lie on the curved boundary of D and not in the interior of D, right? Because D is the unit circle and centered is origin. So yeah, I mean D is basically this circle, yeah, the unit circle. So Z1 must lie either inside the circle or on the circumference, but if Z1 is inside the circle, then clearly Z1 cannot belong to D. But if Z1 is on the circle, then yeah, there is a possibility Z1 will belong to D on this boundary. So that is the only possibility, that Z1 must lie on the circumference of this circle. That mod Z1 less than 1, this less than equal to 1, this circle, the circle defined by mod Z1 less than equal to 1. Where were we? Yeah, here, somewhere here. Okay. So Z1 must lie on the curved boundary of D, not in the interior of D. Now let us consider the case, the last case, where C equals to D equals plus minus 1. So for C equal to 0 we did, for C equals to plus minus 1, D equal to 0 we did. The last case that remains, actually two more cases. So C is also plus minus 1 and D is also plus minus 1. That means either C and D both are 1 or C and D both are -1. So in this case, this mod C Z1 plus D mod squared less than equal to 1 reduces to Z1 plus 1 less than equal to 1. I mean the minus also we can ignore. I mean ultimately, yeah, this is the thing which we will be left with. So this region is the interior plus boundary of the unit circle centered at -1, 0. If you know the equation of circle, I will just write Z1 as x1 plus I y1 and separate the real and imaginary part. The imaginary part basically the y coordinate and the real part the x coordinate. Then you can easily see the center of the circle is -1, 0, and radius is still 1, so it's the unit circle. See, that's why I've written the unit circle. Now this region is the interior plus boundary of the unit circle. Yeah, okay. So clearly this circle has only one point in common with the fundamental region, which is this, and which clearly does not lie in the interior of D. And if we take the case that C equals to minus D equals to plus minus 1, that means when C equals to 1, D is -1, and when C is -1, D is 1. This is the last case. No other cases remain. In that case also, we get this region, this circle Z1 -1 mod less than equal to 1. This is again the circle interior plus boundary of the unit circle centered at 1, 0. So similar to the previous case, this circle also has only one point in common with the fundamental region D, which is e to the I pi over 3, and which again does not lie in the interior of D. This proves that no 2 points Z1, Z2, Z1 not equal to Z2 in the interior of the fundamental region D, that is in U, satisfies Z2 equals A Z1 for some matrix A belong to the modular group. So basically for the last two cases we got this circle, the circle centered at -1, that means this -1, 0, that means this circle You see, I already showed it. It is only one point in common with the fundamental domain, and this point is clearly lies on the boundary, not in the interior. And if we choose the circle centered at 1 comma 0, then also it has only one point in common, this point. So we are done. I mean, just a second. Actually, see, if we define the fundamental region to be entirely all the boundary, I mean this boundary and everything, then only we can say that only for 2 points at the interior in the fundamental region, they are not related by a fundamental modular group. But for 2 points which are not in the interior of the fundamental region, but maybe lie on the boundary, they still belong to the fundamental region. Then two such points are actually related by a modular matrix. Then we can say, because see, this boundary, it's also part of the modular of the fundamental domain, and these points on this boundary are also part of the fundamental domain, and they are related by a T matrix. So then we can say, but see, in this case, the way I have defined the fundamental domain, I have only taken these boundaries, not this. So even the point on the boundary, suppose a point here, even this is not related to any point in the fundamental domain by any modular matrix. So it's not just for the interior, but also for these points. And if we take these points on these red boundaries, then they already lie in the fundamental domain. But if we take any two different points, then I don't think then they will also not be related by any fundamental domain. Suppose you take a point here and take a point here. I mean, in my case, in the way I have defined the fundamental domain, because some people define all the boundaries as the fundamental domain, but the way I have defined, I think we can modify. Actually, I'm sorry, I should have overlooked this mistake. Point number 2 is that if z and z prime belongs to D, and yeah, all this. This means that 2 points both belonging to the fundamental region can be mapped from one to the other by some, if they lie on the boundary of D. No, I think no 2 points in the interior of D can be mapped to each other by a matrix belonging to the modular group. I think the way I have defined the fundamental region, no 2 points, no 2 points belonging to D can be mapped. We can say it's not just for the interior. We can even make it more general. But anyway, I think you get the concept. I will make the corrections later on before publishing this, if I ever publish it. But yeah, that's not the. I mean, yeah, for the video I anyway told you. So if you have the patience to watch this video, watch this. If you're watching till now, 3 hours 16 minutes, then I mean, hats off to you, honestly. But yeah, anyway. So in conclusion, we say that this is the way we define. This is a fundamental region for the action of the modular group on the upper half complex plane by fractional linear transformations, since we have proved that it satisfies all the three defining properties of a fundamental region. Now we'll just do discuss a simple interesting kind of, you can say, exercise. Consider the lattice 0.5 comma 0.5 I. That means you take this square 0.5 comma 0.5. You just take, I mean, these points. You see the blue points. You can see the blue points on the fundamental domain. You see all the blue points, they define the lattice 0.5 comma 0.5 I. That means basically, yeah, like the fundamental parallelogram, it has the dimension 0.5 cross 0.5, this square. In this case, the fundamental parallelogram is square. It's a very simple lattice. So let us consider the lattice and assume that we're in the upper half plane and ignore the lower half plane. And clearly this lattice is the collection of all the points in the upper half that are 0.5 units away from its immediate neighbors on all sides. In the figure below, the horizontal axis represents the real axis and the vertical axis represents the imaginary. I mean, this is basically just the complex plane, right? I've actually done this in Desmos graphing calculator. So the fundamental region is the region enclosed by the red and black curves plus the red curve. You see this red curve, it's the part of the fundamental domain, and this black curve is defined as the boundary, but it's not part of the fundamental domain the way I have defined. And yeah, inside this the region enclosed by all these red and black curves, that is of course the part of, that is of course the fundamental, belongs to the fundamental domain as well, the interior basically. And of course the lattice points extend infinitely leftward, rightward, and upward. In the figure we have only shown the points within the region enclosed by -3 to 3 along the horizontal axis and 0 to 2 along the vertical. You see, minus here it's -3 and here it's 3. I mean, we have just discussed, I mean, just shown a limited region, of course. Now, of course, it's possible to find a matrix belonging to the modular group for each of these blue points that transforms the point to a point belonging to the fundamental region. Let us call this matrix A. Now, since the case above is extremely simple, we can easily divide the blue points into some regions, and for each region, come up with a general form of the matrix that would transform the points in that region to some point in the fundamental region. I mean, just a general form matrix instead of doing this individually for all the points. So first, let's consider all the blue points except those whose coordinate on the vertical axis, say y, is 0.5. Let us call this category 1 points. I mean, I'm talking about these points. You see, all the blue points except those whose coordinate on whose y coordinate are 0.5. I mean, these points, you see, not this point, because see the y coordinate is 0.5, not this, but yeah, this point is okay. This point, I mean all the blue points here, but not this, not this blue points, not this one, not this. Clearly, why am I doing making this separation? Because you see they lie below the fundamental region, so the transforming these points will not be easy. I tried with many different cases, so transforming these points will not be easy. I mean they're a bit difficult. I mean, so we need to say the general form of the transformation matrix for these points will be different. That's why I separated these to category 2 points, and category 1 points are, you know, these kind of points. We further divide these set of points into two subcategories. The points whose coordinates on the horizontal axis, it is x, are integers and say category 1a points, and for those who that are fractions. I mean, so these points, right, category 1 points, these and these. Among them, we further divide these points. See here, the x is 1 integer, then this x is 2. I mean, just for these three, x is 2, x is 3, then x is what, minus 1, minus 2, minus 3. These are subcategories, category 1a points. And the remaining points in category 1 whose x coordinate is fractional, say minus 1.5, 0.5, 1.5, let me call that category 1b points. This is how you should do the division. Actually, I had to do a lot of trial and error initially. First I thought that maybe I should divide it with whose x is positive and x is negative. The first coordinates point, this is category 1 and this is category 1b. But then I found that no, I should make the division based on the x coordinate is integer or not. So anyway, if you do this, then you see that for the first set of points, that is category 1a points, the matrix t to the minus x, where x is the x coordinate basically, it is given by, where t is given by this, then this matrix will transform any point belonging to category 1a to the fundamental region. You can check it out, it's a general form, right? And yes, t is one of the generators of the modular group, so clearly t to the minus x belongs to the modular group. For instance, let me show you a simple example. Category 1a point, that means its x part is an integer and y part is anything but 0.5. So let me choose this point. Okay, this point, its x coordinate is 2, which is an integer, and y coordinate is 1.5, which is not 0.5. So x is 2, that means t to the minus x, t to the minus 2. That means if I shift this point 2 units to the left, that means 1 and 2. You see I reach here, it lies in the fundamental domain. Now let me choose this point. Suppose, I mean, yeah, for any other point it will technically work, right? Now for category 1b points, that means for these points with y not equal to 0.5 but x is fractional, I mean x is not an integer. For these points, you see category 1b points, the form of the general matrix that will transform these points to the into the fundamental region is t to the minus box x minus 1. Okay, see, box x is the greatest integer function of the box function. It is the greatest integer that is smaller than x, because in this case x is not an integer, x is a fraction, but the power of t cannot be a fraction, right? So we do this. I mean, see this, if it do, let me take an example, t to the minus box x minus 1. Okay, so category 1b point, suppose this point, let me choose this point, minus 1 point, okay, this point minus 1.5 comma 2. So y is 2, so it's clearly category 1 point, and since x axis is fractional x coordinate minus 1.5, so it's a category 1b point. So minus 1.5, x is minus 1.5. What is what is box x? It is the smallest integer. I mean, it is the minus 1.5 is not an integer, but what is the smallest integer, which is what is the largest integer which is smaller than minus 1.5? So minus 1 is actually, see, it's negative, so minus 1 is greater than minus 1.5, but the nearest integer to that is smaller than minus 1.5 is minus 2. Minus 3, if you take, it will be smaller, but the biggest integer that is still less than minus 1.5 is minus 2. So box minus 1.5 is minus 2, and we have t to the minus box x minus 1, that is t to the minus minus 2 minus 1, that is t to the plus 2 minus 1, that is just t to the 1. So t to the 1, that means if I just shift this point by 1 unit to the right, I end up here, and say I end up in this blue point, and see this point is it lies, see the red on the red line, so it's a part of the fundamental domain. So you can check with the other points also. So this is the general form. See, if I choose a point, see, minus 2.5, then also the x is minus 2.5, so automatically t to the minus 2 point, minus box x minus 1, it will shift, it will shift such that, you know, it will come inside the fundamental domain. You can check it. So this is the general form for category 1 points, 1a or 1b. So now we missed out on this thing, the category 2 points, when y is 0.5. I mean, just this category, just this point. Okay, just these points. Again, here also we have to make this further subdivision, 2a and 2b. So that is for, yeah, let us call all category 2 points with x less than 0, that is points lying on the second quadrant, as category 2a points, and the rest x greater than 0 as category 2b points. Okay, here I have done this division in a different way, not whether x is an integer or fraction, but whether x is positive or negative. So you see, for category 2a points, that means where x is less than 0, this is the form. It's a bit complicated. The form of general matrix that will transform these points to the fundamental domain, it is t to the box x plus minus box x, I mean box minus x, sorry, not minus, box minus x, s to the 1 t to the box minus x. And for category 2b, it is t to the minus box x minus box minus x, s to the 1 t to the minus box x. Where again s and t are the generators of the modular groups, x is the coordinate of the point of the horizon of the generator. Yeah, anyway, all of these things are the technical. And yeah, if x is an integer, we see that both this and this, they reduce to a equals s1 t to the minus x, because for integer, you see, this box x and box minus x, they're the same. I mean, box x is just x and box minus x is minus x, so x minus x is just 0, t to the 0 will be identity, and here also this will also go away. So yeah, so if x is an integer, the matrix s t to the minus x transforms both category 2a as well as category 2b points to points of the fundamental region. And if x is not an integer, for category 2a points, yeah, we have this, and 2b points we have this. I mean, yeah, this is the more simple one, this is the more complicated. From this only we can actually simplify down to this. Okay, now also for more than one blue point, okay, let me just, I'll discuss this, but before that let me just show you, just let me just show you one simple example. For okay, let me do category 2a points. I'm not doing 2b again, but for 2a, let me take simple example. 2a means x is negative and y is 0.5. So I'm claiming that this is t to the minus 1 s1 t to the mod minus. Actually, it is, see, there is an s involved, so you cannot just visualize it with your eyes. You have to do the calculation. Okay, so let's proceed. For example, consider the point minus 3 plus I. It has the coordinates minus 3 comma 1, clearly category 1 a point. So yeah, for this, if we do this, just some verifications which we have already done. But now let us see, consider the category 2b point, 2.5 plus 0.5 I with coordinates 2.5 comma 0.5. Now in this case, yeah, this we have, right? So x is 2.5, so box x is, see, it's plus 2.5, so it's box minus is outside the box. So box 2.5 is just 2. The largest integer which is lesser than 2.5 is plus 2. But box minus x, that is box minus 2.5, is minus 3. So we have minus 2 minus minus 3, that is minus 2 plus 3, that is just 1. So t to the 1 and s to the 1, and this is t to the minus box x, that is t to the minus 2. So if we multiply t to the 1 s to the 1 to the minus 2, then, and with this point, the point is this 2.5 plus 0.5 I 1. So doing this, we get this I over 1, and again clearly I lies in the fundamental domain, right? So the transform point is again I, thus demonstrating that more than one blue point. Now yeah, you see here in this example, this is a category 1a point. Here also we did this, we transformed to I, and here also we transformed to I. So the transform point is again I, thus demonstrating that more than one blue point can get mapped to the same point in the fundamental region. See, previously when we were doing this derivation, this proofs, mathematical proofs, what we claimed, one point, a single point can be mapped inside the fundamental domain by a unique matrix. I mean, a single point cannot be mapped to 2 points within the fundamental domain by two different matrix. But two different points outside the fundamental domain can be mapped to the same point inside the fundamental domain. That is allowed, right? And that is what has happened. See, this point minus 3 comma 1, it is also mapped to I inside the fundamental domain, and this point 2.5 comma 0.5, it is also mapped to I in the fundamental domain. So more than one blue point means these lattice points, more than one point belonging to the lattice, can get mapped to the same point in the fundamental region under the corresponding matrices. The matrices will be different, of course. This 2.5 comma 0.5 is transformed to I under this matrix, t to the 1, t is t to the minus 2, and this is under the matrix t to the t cube. They're different, but the transform point is the same, right? This means in loose terms, it is possible for the density of a mapped point in the fundamental region to be more than that of a blue point. Because see, for instance, you consider this point I in the fundamental domain. It is more dense because this I, it represents the transform point of this point 2.5 comma 0.5. as well as this point minus 3 comma 1 plus maybe some other points. So the I is very dense. I is I, it's a single point, but it is more dense. That's what I'm saying. But these points, they are just unique. In the lattice points, there is no, I mean, they're just unique points, right? So, sorry, yeah. So in loose terms, it is possible for the density of a map point in the fundamental domain to be more than that of a blue point, a lattice point, because a single map point in the fundamental region can correspond to more than one blue point. Now, in fact, if you do the map of, if you just run a simple computer simulation, I just ran a simple computer simulation, and I found that all the blue points in this lattice, that is 0.5 comma 0.5 I, the map of all the blue points inside the fundamental region is given below. See, just these few points. I mean, here we have seen only a finite region, but yeah, it will lie here. I mean, it will go on above, go up infinitely. But yeah, for this simple lattice, it's a very simple case. For this lattice 0.5 comma 0.5 I, for this lattice, this is the mapping. This is how the mapped points will look like. These green points, the blue points are mapped to green points. You see in the figure below, we have plotted both the set of the original points in the upper half plane, the blue dots, as well as the set of the transform points inside the fundamental region, the green dots. You see, these are the green dots. So now, after doing so much discussion about fundamental domain and everything, you may ask, what is the need? I mean, what is the benefit of defining this fundamental domain? Now you get your answer. You see, clearly the set of transform points belong to the same lattice as the set of the blue points. You see these green points, they describe the same lattice, clearly the same lattice as the blue points on the same points, 0.5 comma 0.5 I. Now for this particular lattice, the transformation to the fundamental region is symmetric under the modular group. This means that the set of all the blue points can be equivalently represented by the set of all the green points, because they describe the same lattice. Just for instance, if you are fixed in this limited domain of -3 to 3 along the x-axis and 0 to 2, then so many blue points are there. If you count 1 2 3 4, 1 2 3 4 5 6 7 8 9 10 11 12 13, so 13 into 4, how much is that? 20 40 50 52, right? So 52 blue points you have. Even if I consider the blue points, the lattice points inside the fundamental domain, you have 52 blue points. You are transforming all of them to just 6 green points. Now can you imagine what is the, I mean, now you are asking what is the benefit of this? It's 52, right? I mean, whatever, 52 or not. The thing is that so many blue points can be transformed to so less points. Even this is infinite actually. If we consider this infinite lattice, even the mapped points will also be infinite, but still the number, it's much easier to study, it's much easier to deal with, right? So that means the set of all the blue points can be equivalently and completely represented by the set of all the green points. Thus, if you can show that a huge but finite set of points is symmetric under the modular group to a smaller set of points, we can considerably simplify the study of the initial set of points. Now, this is a huge advantage when, say, this set of points represents different states of a real physical system. Here, we are just doing from a mathematical perspective. They're just points on the complex plane. They're just a mathematical abstract mathematical lattice. But in physics, if these points represent some different states of a real physical system, and then if we can actually reduce this a huge number of points to a smaller number, then we can actually simplify the study of the initial set of points. So this is why symmetry is very important in physics, and especially modular symmetry is just an example. Modular symmetry is important in many other cases, in due to other reasons also. For instance, in the standard model of particle physics, we have a lot of arbitrary parameters, free parameters. In the sense, let me just give you a very rough idea in the sense, rough discussion. Even I don't know the details, the mathematical details. I mean, basically, see what happens. A standard model is basically, it's again it's a model which describes the interactions between the elementary particles. It covers all the three fundamental forces except gravity. I mean, it covers electromagnetic forces, weak nuclear and strong nuclear forces. And yeah, in standard model, you use group theory. You have to use group theory extensively. For instance, like I said, symmetry means something is remaining unchanged, conserved under some particular group. And in standard model, it's the Lagrangian. For instance, for the electromagnetic force, we have this group called U1. That is the group of all unitary matrices of order 1. Unitary matrix, you should know what a unitary matrix is. It's a basic matrix theory. Then we have this for weak nuclear force, we have then for the other two forces, weak nuclear and strong nuclear forces, we have SU2 and SU3 groups. SU2 is the group of all special unitary matrix of order 2. I mean 2 by 2 matrices. Unitary matrix must be a square matrix. So 2 by 2 matrix of order, that is order to SU2. A special unitary means again the determinant must be 1. and SU3 means a special unitary matrix of order 3. So that means SU1, that is U1 times SU2 times SU3. So these three groups, then the Lagrangian is concept. I mean, basically this is how you define the standard model. But and it's a pretty successful theory. Standard model has predicted many new particles, which have many of which have been detected in particle accelerators and all these experiments, high energy physics experiments. And yeah, it's experimentally it's very successful theory, and it explains all the three forces of nature in from the point of view of quantum field theory, except gravity. That is the only that is not the only problem though. The main problem, the one of the main problem and with standard model is that there are a lot of free parameters in the standard model. You might have read this in popular science books, but what do we actually mean by free parameter? See, standard model is a perturbative theory. I mean, see, we have I mean, there's a limit. So I mean, basically we know the limits. So standard model basically describes the interactions of the particles. So whenever we can use the standard model, the mathematical framework of the standard model, to make predictions about new particles, their masses and everything. But whenever we're doing that, we all the theory can tell us is that the mass or whatever you're trying to measure, the measurable, the quantity, it must lie between this and this. It must lie within this range for the theory to be satisfied. But it does not give us the exact value. Now, when we do the experiment, we get a value which satisfies, which lies within the range, but the standard model lacks predictive power in some sense because it cannot tell us the exact value. It can only give us the range, right? Now, the thing is that to explain why to actually derive that exact value which our experiment gives us from the theory, we scientists, physicists actually, to put it roughly, even I don't know how the exact mathematics is done, but to put it roughly, they play around with the free parameters of the standard model, they tweak it and they manipulate it so that we get the result we want. But for a fundamental theory, that is not what we expect. We expect that it should give us the exact values. It should give us the exact values because it's a fundamental theory. Why should I have to manually tweak the parameters to get the value I want? It doesn't feel like a fundamental theory. It feels like a kind of, yeah, you know what I mean. But the thing is that the basic idea is that if we can impose, see, in conventional standard model framework, we don't use modular symmetry, but the idea is that if you can impose modular symmetry on standard model, then maybe we can reduce the number of free parameters, which means we can improve the theory, make it more fundamental. Just like by imposing modular symmetry, we can reduce all of these blue points to just these few green points. Similarly, suppose if these points describe some Lagrangian of some particular, if these points have some physical meaning in context of standard model, then this is where we expect modular symmetry to might play a role. That is why from the physics point of view, that is why we're studying this. Otherwise, this is just mathematics. Even if you see in this video, so far whatever we've discussed is just mathematics, right? So that is one thing. Okay. Now, mapping any point in H with y greater than equal to 1 inside the fundamental region. See, now I don't want to make the video any longer, but yeah, it's just a this lattice 0.5 comma 0.5 I. It's a very simple case, See, in our case, it's a omega 1 is 0.5 and omega 2 is 0.5 I, and the ratio is not real. 0.5 over 0.5 I is 1 over I. It's clearly not a real number. So 1 over I is what? 1 is minus I square. So that is minus I square over I. That's minus I. It's not a real number. That is why this it could describe a lattice, right? But anyway, yeah. But now if we try to make things a bit more general, because in lattice we have just equally spaced points. But if we have a random point, suppose we choose a point randomly here a random distribution of points, uniform distribution, but not, see, uniform distribution of point, it's a very common misconception that high school students have. Uniform distribution of points means they picture something like this lattice, these blue points. Of course, this is a uniform distribution, but not necessarily. Even if I have a random distribution of points, but as long as if I choose any point randomly and if I take a radius, a same radius, suppose I take a radius 1 unit, and if I draw a circle, then the number of points lying within the circle, and if I take some other point and draw a circle of the same radius, and if I see the number of points lying within that circle, if I do this a huge number of times for many different points, and if I see in all the cases the number of points lying inside the circle I draw of the same radius is more or less the same, then even that is a uniform distribution of points, even though all the points may not be uniformly spaced like this lattice. So anyway, if I try to make it more general, mapping any point in H with y greater than equal to 1 inside the fundamental region. Now, any point in H with y greater than or equal to 1. I mean, not just the points belonging to this lattice, any random point. So again, I'm not going through all of this, but you see, if I just tried a bit of mathematics and I also did the simulation, you can see actually the simulation, the best is if you can do in Wolfram Mathematica. It's pretty simple to use also, but unfortunately, that software is not free for personal use. And I don't know, the institute in which I was doing my fellowship, research fellowship, they gave this option. All the computers in the institute, I mean, in my office in the institute, I mean, in the room which I was allotted, in that computer I could access Mathematica and everything. But you see, I could not access the Mathematica from my home PC. Mathematica is good, but yeah, if you don't have Mathematica, it's okay. Even Python will do, even Python will work. And if you just want, even, I mean, Python will be best in that sense, because you can just do any Python will work for. And if you see, I'm not very, I was also not very good in coding. I am not very good in coding in computational physics. But see, if you can understand the algorithm, if you can know what to do, if you can find out this general form of the matrix, then you can, yeah, sorry, yeah, so I mean, if you can find the general form of the matrix or of the transformation. Suppose you want to do a S transformation, so your initial point is x comma y, and you want to transform it to x dash comma y dash. So how will you find x dash comma y dash? Well, S is what, 0 minus 1 1 0, right? I forgot. Yeah, somewhat like that. Let me just check this once. Yeah, S is, yeah, 0 minus 1 1 0. So that means 0 minus 1 1 0 comma xy in a column form, I mean, not comma, multiplied with xy in a column form, is equal to x dash y dash. So do the multiplication, you find the value of, I mean, find the expression for x dash and y dash in terms of x and y, and then you just write the code like you define x and y, and then you define x dash equals to this, y dash equals to that, and you just plot. I mean, see, just you should just need to figure out the algorithm, and then you should, the exact syntax, the code that you can ChatGPT will help you. In today's world of ChatGPT, you don't need to be an expert in coding for that. That can help you. I mean, you can do this in Python. It's actually not very complicated, and Python will, for a fairly small step size, Python will do give you the simulations in 1 or 2 seconds. It will not take a lot of time, and if you have a decent laptop, decent PC, I'm not saying MacBook Pro or anything, I think your laptop can handle this even if you're doing for thousands of points on the complex plane on capital H. You can, Python can do that. Yeah, Mathematica would have been best actually, but yeah, Python will also work. I personally did the Python I did in Jupyter Qt console, IPython, that is. But yeah, there are a lot of Python text editors, so whatever you're comfortable with, you can do that. And if you run into some difficulties with some particular syntax, you can just take help of ChatGPT for this coding part. Just for this part, I think there is no I mean, ChatGPT is actually helpful. It saves a lot of time. But yeah, don't get too dependent on ChatGPT for everything. But yeah, for the coding part, even I use ChatGPT. I mean, it's the only thing I use ChatGPT for. Okay, and yeah, ChatGPT is not always effective, even in this regard. But yeah, it sometimes is. It fairly is. Okay, so yeah, so in this case, what I've done a lot of calculations and all. I'm not showing you the exact transformation. You can just take a screenshot if you want. You can read it. Okay, these are the forms and anyway. But yeah, for general points, you see, this is the transformation. I've taken a set of random points. See, not any particular well-defined lattice or equally spaced points like the previous case. So these green points, if I transform to the fundamental region, their image will look like this. See, the same thing basically, exactly the same. I've just kind of taken a snapshot of this square, this square which I'm look at my pointer, and I've just pasted it here. Nothing else. Now you see this. I've just added some more points, these violet purple points on these boundaries, right? Now also you see it's the same thing, just the same. I've taken a snapshot and pasted it here, except that these points, the points lying here, see, basically they're all being we are all just kind of subjecting them to a t transformation, t to the minus 1. So let's just take this point, this purple point. It is being transformed to this black point. So this purple point, the x coordinate is 1, and the black point, the x coordinate is 0. So t to the minus 1. So these points also under t to the minus 1, these points have been transformed to this here. But again, as per our definition, this does not belong to the fundamental domain. This does. So for these points, I mean, for these few points which lie on the boundary, which they initially under t to the minus 1, they will be mapped here. But we need to, only for these points, we need to further map them t to the minus 2. I mean, t to the minus 1 one more time. So t to the minus 2. So they are here. This again lies in the fundamental domain. So yeah, I mean, of course, I'm not manually doing this. I have defined the general form of the matrix such that, for instance, you see these points, their x is fractional, their x coordinate is it's fractional, minus 1 point, I mean 1.5, but this is integral 1. So I've written the, you can just take a screenshot and just read it. I mean, it's already 3 hours 43 minutes. I cannot, talk any longer. I'm sorry. Plus, I think, yeah, anyway. So, but for these points, automatically the way I've defined the form of the general matrix using the box function and all, automatically these points will be transformed here and the other points just here. I have run this simulation. You see, this is what I've got. Now, see, we have considered this square, 1.5. So now let us consider this square. Okay, so here, so this will be transformed here. This is pretty simple. It is all the points are transformed just normally shifted, because it's clearly all of the points are automatically they lie in the fundamental domain. Now this point, yeah. So I just tried with a lot of case, and finally, you see, finally, I'm sorry, yeah. So finally, I did. Here you see this image, this figure, picture, whatever. So what I found was that for all of these black points, I mean, you see these alternate black points. You see this black alternate. They are being transformed to these red points within the fundamental domain, and all the blue ones, the alternate blue ones, they are being transformed in the green point. But for the green point, you see there are no green points here. They are here. So here you see here on this line, and yeah, there's some here also. I mean, that is as usual, as expected, right? Great. So now you see here it's important. See, it's clear that as we consider random points outside the fundamental region in the upper half plane H, capital H, farther and farther to the left and right, infinitely many points in capital H will be mapped to the same point in the fundamental region D. For instance, you consider this this green point. Now this particular blue point is being mapped to this green point. This particular blue point is being mapped to the same green point. This particular blue point is also being mapped to the same green point, right? So that is what I'm saying. Infinitely many points in capital H will be mapped to the same point in the fundamental region D. For the alternate squares of length 0.5 units in regions 1 and or 2 outside D. I mean, these are just technical. You just I have already explained the figure to you, but yeah, this you see in all of the cases, the points in capital H with x coordinates of the form n.5, where n is a positive or negative integer, get mapped to the corresponding points in D with x equals minus 0.5 and the same y. And the points with x coordinates of the form n, where n is a positive or negative integer, the mapped points and the points with x coordinates of the form n, where the mapped points in D have x, and for the points, yeah, for the point, I'm sorry, the mapped points in D have x equal to 0. Now look at the figure below. Yeah, all of the green points are in the square with coordinates, yeah, I mean this square, except the green points on x equals minus 0.5. You see, x equals minus 0.5, these green points, which correspond to the blue points with x equals n.5. I mean this fractional x kind of, okay. N can be positive or negative integer. I mean minus 1.5, 1.5, 2.5, whatever, minus 2.5. And the black points as of the fundamental region is in alternate squares get mapped to the red points in D. If we consider, see now, if we consider all the points in the regions 1 and 2, by region 1 and 2 I'm just talking about this, this region, just forget that. Because I've not gone through this line by line, but yeah, I've explained everything worth explaining. Plus I don't want to make this video any longer. It's the largest YouTube video I've made. It's kind of my record. So if we consider all points in regions 1 and 2, clearly the concentration of map points in D with x equals minus 0.5 is higher than that for any other x belonging to minus 0.5 to 0.5. I mean, this is because of the extra set of points outside the fundamental region in region 2. I mean, see, basically just forget all this language. What I'm trying to say is that, see, for all of these points inside the fundamental domain, they correspond to more than one point outside the fundamental domain. That is okay. But see, it's equal in the sense, suppose this green point which I was saying, from the left infinitely many blue points, and from the right the same infinitely many blue points. But you see, for the points lying on this line, you see the density is more in the sense, because see, for all this black squares, they are getting mapped to the red square, fine. But for all the blue squares, they are getting mapped to the green square, but except this, for this it is again coming here, right? So this line not only contains all the points for the blue square, but all the points for the black square as well. So here I've only shown a few finite number of points, but if we actually do the transformation for all the points on the upper half plane, on H, on this plane, you will see that the density of this line, that is x equals minus 0.5, this line will be twice. Yeah, it should be twice, right? Then the density of all the points, I mean definitely it should be more than the density for the other points in the other parts of the fundamental region. That we can conclude, right? Now if I, so we did for this region, for any, for this, for y greater than 1, yeah, from here above, for here, for this also the same formulas will work. Now if we do for this small region, you can see for the small region, minus 3.2 minus root, I mean sorry, root 3 over 2, that is this region, and this is 1, I'm sorry, and this is 1, sorry, this you can see it's 1. So for this small slice I am trying to do now. Again further I have to divide in a lot of regions, for this left region, then the right, and then the ones in between, okay, because the forms of the matrix, they are not the same, they're different, so I had to subdivide into a lot of regions, okay. And anyway, again I'm not showing you all this, you can just take a screenshot if you want. So I'm not showing you all the calculations and the forms of the fundamental matrices, but I'm showing you what I got. What I got was that, yeah, you see, for the red points here, you see, I've considered all the points within this region. For the red points, they're getting mapped like this. The blue points here, they're getting mapped to the blue points. The green points here are getting mapped to the green points in the fundamental domain, and so on. And that's it. Basically, see, and if you consider the points on this circumference of this circle, so any point, suppose this point here, where my pointer is, it will be mapped to some point here by an S transformation. Now, or conversely, this point will be mapped to this by some S transformation, because this point does not lie on the in the fundamental domain, but this point does, according to our definition, right? This curves does. And any point here in this region, you see any blue points in this region, they are just a simple S transformation will transform them inside the fundamental region. And for these points, these red or green, it's some t to the, first you just need to use some t to the n transformation for some appropriate integer n to shift this point somewhere here. They're already here, so you just shift it somewhere here, and then you just use the s. That is the basic idea, right? So now this I did all of these simulations and calculations, but the thing is that there is actually a figure. Let me show the figure, because you have to. It's not so simple, because you cannot define there. You cannot divide this upper half of the complex plane into a finite number of regions, and find out with the, come up with the general forms of the transformation matrices that will transform the points to the fundamental region. Actually, okay, just let me open the figure once. Just a second. Shit. Yeah, can you see this now? Okay. Yes, I hope it should be visible. Yeah, you can see this now, right? Now, so basically here you see, here they have divided the fundamental region into this region. Actually, you should divide it into this kind of region, because if you see, in my case also, if you see, after it became apparent to me after I did the calculations. See, even for this region, you see, basically the points here, I mean, actually, I should divide it into this kind of spherical. I mean, like, because this, the points here, the points, all of the points belonging in this shape, they can, like this, suppose here, they can be translated and brought here directly to the fundamental region. So you see all of these points. You can see, if I follow the pointer of my mouse, I mean, just follow the arrow. So for all the points lying in this part, t to the minus 1. That means actually it's t to the minus 1 means they have t to the 1. I mean, if you multiply these points by t to the 1, I mean, if you shift them by 1 unit to the right, they will fall inside the fundamental region, fundamental domain. Here it is t to the 1. I mean, actually this should be t to the minus 1. They have shift, but they have written in the sense in this figure, it's written t, because it's, they are trying to show that it's t, it's just t times, it's 1 unit right of the fundamental region, that's why. But the transformation matrix to transform points in this region to the fundamental region, that should be t to the minus 1. Here t to the minus 2, here t to the minus, here t to the plus 1, t to the plus 2. You get it? Here I already told you, here it is s. So for this region, it's totally s. Then it's s t to the minus 1 t. So I have not been able to, it's not possible to physically, verify by hand for all these regions. But if you can run the mathematical simulations, I mean, computer simulation, you can see that this holds true more or less. But the problem is that as you go down nearer and nearer to the x-axis, the horizontal axis, you see, you have to divide into more and more and more, almost infinitely many regions. You see, here we have only, just a second. Yeah. So here we are only see one. I mean, still it's a countable number of regions at this level. But below we have even more regions, and for all these regions there are different combinations of s and t that will actually transform a point inside that region, in that region into the fundamental domain. right? See, because there are infinitely many possible combinations of S and T. There are infinitely many elements in the modular group, but it's difficult to figure out because here we have to. The more down you go, the fundamental group, the upper half plane is you have to divide it into into infinitely many regions. So maybe there exists some general forms of maybe we can use some advanced computational techniques. But yeah, that is not the point actually these are all open questions, research questions. It's not like you can get this in textbook, but the point of this video was to give you an idea of modular groups, which I think I have accomplished by now, although I took almost twice the time I wanted to I targeted 2 hours, but it's almost 4 hours. But anyway, so finally, before we end the video, let me give me one 10. I don't know if anyone is watching right now. Anyone will be watching till this point. So, but yeah, let me just finish the video. I'll just Mobius transformation. I'm not discussing. It's basically a modular group is a subgroup of a bigger group, the Mobius group. The Mobius group also it's a kind of fractional linear transformation, but just like we define the modular group for the special linear SL, for the Mobius group, it is defined as GL, the general linear group, and it's not for only 2 dimension or anything. It's for just n. I mean it's sorry, it's 2 dimensionally, right? I, I'm not really sure about the Mobius one. I whatever. And yeah, here I have some stuff about geometry, the Mobius transformation. How does it look like? Let's just leave this for now. And why the matrix multiplication and composition of two functions, they act essentially the same transformation. I mean the same group operation. They act as the same. This I have shown here. I mean anyway, just Mobius group, just forget it. Fixed points under Mobius transformation not strictly relevant. Yeah, modular forms, and then we have congruent subgroups, and then yeah, we will end the video here. After just these last two, I have to discuss. This is important. Mobius I skipped. So now that we know what a modular group is and how we define the fundamental domain and why is it important, how it might be beneficial, I mean used in physics and everything. So what is a modular form? A modular form is a complex analytic function. Analytic means it is complex differentiable. Its differentiation is well defined in that domain. So it's analytic in the on the upper half plane. So see, it's mentioned. So modular form is a complex analytic function on the upper half plane H, satisfying a certain kind of functional equation with respect to the group action of the modular group and also satisfying a growth condition. I mean, see, basically in simpler terms, if we know how this function behaves inside the fundamental region D, we can find out how it behaves everywhere else in the upper half plane. Like I said, that is why defining the fundamental domain and studying how to transform points outside the domain to points inside the domain, that is why it's important, you see. And modular forms must exhibit all the symmetries of the modular group SL 2 comma C, of course, plus be holomorphic as well as bounded. Holomorphic means analytic. It's analytic, and it should be bounded, because if it's unbounded, then again it will be undefined, right? So mathematically, a modular form of weight k. Yeah, for modular form, we need to define this parameter called weight. It's usually denoted by k, where k is usually a positive integer. There are special cases. I mean, people have tried working or study. I mean, even negative k's have all negative weights have also been studied, but usually k is a positive integer. It's called the weight of the modular form. Even fractional k, yeah, you see, in some cases can be a fraction also. Yeah, fraction, I guess. Yeah. And for the modular, so see, this is the modular group, especially in a group 2 comma z, which is the group of all such matrices a b c d, such that a b c d are all integers and ad minus bc is 1, the determinant is 1. So the modular form of weight k for this modular group is a complex valued function f on the upper half of the complex plane H, such that f is a holomorphic function on H. A complex function is holomorphic or analytic on a set U if it is complex differentiable at every point of view. Already discussed at the very beginning of the video, if I remember right. And if is bounded means, see, as z tends to I infinity, I mean as the imaginary part of the this z, I mean z tends to I infinity means as z, I mean as z moves upper and upper. In other words, there exists some real number r and some constant c. What I'm saying is that the function f is bounded as z tends to I infinity. In other words, more mathematically, we can say that there exists some real number r and some constant c greater than 0, such that mod fz less than r for all z with imaginary part of z greater than c. So imaginary part of z is greater than c and c is greater than 0. So no matter if imaginary part of z is increasing, but fz is still bounded. Its mod fz is still less than r, where r is some finite real number. So these are the conditions. It must be a holomorphic function, f must be a holomorphic function, and f must be bounded as z tends to I infinity. I mean, it must be a bounded function. Even if z tends to I infinity, the function must be such that it is bounded. The function must not diverge. And for any z belonging to H, upper half plane H, and any matrix as above belonging to the modular group SL2 comma Z, the modularity condition holds. Yeah, this is the main condition of modular group. Apart from satisfying all this condition, for a function f to be a modular form, it must satisfy the modularity condition, and the condition is given by, you see, for any z belonging to the to capital H, and for any matrix belonging to the modular group. You see, this is the condition: if of az plus b over cz plus d equals cz plus d whole raised to power k, where k is the weight of the modular form, into f of z. So see, in the left hand side, the function is itself a function of az plus b over cz plus d. So be careful about the change of variable. It's not like, I mean, the function is a function of this thing. Here the variable is your entire this thing in the bracket. So yeah, let us try some simple cases. Let us choose a equals d equals -1 and b equals c equals 0. Then ad minus bc is equals 1 is satisfied. So then if we put it in the above condition, what do we get? A is -1, right? So -1 z, I mean minus z plus b is 0. So minus z over -1, because c is 0 and d is again -1. That is just z or z. So we get f z equals, again c is 0 but d is -1. So f z equals -1 to the power k f z. Now you look at this equation. See, these choices of a, b, c, d, they are a valid choice, because a, d minus b, c is 1 is satisfied. So the matrix defined by a, b, c, d will belong to the modular group. But for these choices, we are getting f z equals -1 to the raised to the power k f z. Now for odd k, we have, for if k is odd, then -1 to the power k will be -1. Then fz equals minus fz. Clearly only the zero function, I mean fz equals to minus fz is true only for the zero function. Zero function means a function whose output is always 0, because yeah, 0 is equal to -0, right? Otherwise fz can never be equal to minus fz, can it? You ask yourself. See, output of the function fz must also be a complex number, and 0 is the, of course it must be a complex number. I mean in general I'm saying, and 0 is the only complex number. 0 is a complex number. Every real number is a complex number, right? With the imaginary part 0. So 0 is the only complex number that is its own negative. You see, a plus ib equals to minus a plus ib. Suppose f of z is a plus ib, so minus f of z will be minus a plus ib. If we solve this for this condition, you get that a must be equal to minus ib, which means a plus ib must be equal to 0. So f of z must be equal to 0. So the only modular form of odd weight, k is odd, is the 0 function. This is the only modular form of odd weight. The proof was pretty simple, right? And this result is a general result. See, it's not like that we did for a equals d equals -1 and b equals c equal to 0, but that does not mean it's a general result, because the matrix with these values of a, b, c, and d, that is the negative, basically is the negative of the second order additive matrix minus I. It belongs to the special inner group. Hence, these choices of a, b, c, and d are valid. Now, if only the zero function can satisfy the modularity condition for this matrix and for odd k, this means in general the only modular form of odd weight, that is odd k, is the zero function. Because even if the condition holds for some other matrix and odd k, it does not hold for minus I. And even, like I say, even one counterexample is enough to show that. I mean, see, since minus I is a member of SL, the SL group, so at least for one, for the zero function, the modularity condition is satisfied for odd k and any matrix belonging to SL2 comma z. It's a general case, not just minus I. But for if it's not a zero function, then it depends. But yeah, in general we can say that zero function, I mean, what is this? Zero function is the only modular form of odd weight. In general we can say. I mean, see, you think about this. We took some specific values of a, b, c, and d, which are valid, and of course which are valid obviously, and we arrived at this result. But say you choose some other values of a, b, c, and d, does not matter. Even in that case, even if for those values of a, b, c, and d, maybe the modularity condition is satisfied for odd k. Maybe some function other than the zero function satisfies the condition. It may be the case, but since at least we can say this with certainty, that for these particular choices of A, B, C, D, which are valid choices, zero function is the only function that satisfies the modularity condition. So in general, and of course the zero function will satisfy the modularity condition for all other choices of A, B, C, D, obviously, since it's a zero function. So in general, you can say that the zero function is the only modular form of orbit, because see, modular form means this is the modularity condition. This means this modularity condition must be satisfied for all A, B, C, D, all possible values of A, B, C, D, right? It's a general condition. So that's what I was talking about. Now, if k is 0, modularity condition translates to, if k is 0, see, then f of this thing, the LHS, will be equal to c, just f of z, because k is 0. Cz plus d raised to whole raised to the power 0 is just 1. So this means f of z prime equals to f of z, where z prime is just az plus b, az plus b whole divided by cz plus d, just a linear fractional transformation we already discussed. This means the output of the function is always constant regardless of the input, right? So the only function satisfying fz prime equals fz, or fz equals h for some constant h, and for z belongs to the upper half of the complex plane, are the constant functions. Yeah, what do you mean by constant function? The output is always a constant. Yeah, the output must be a constant, because if the output of a function is constant, why, how can we see this? Because if z prime is equals to f of z, regardless of the input is in our hand. Z, we can put in any z, we can choose values of a, b, c, d, provided they satisfy their integers and satisfy ad minus b is equals to 1. You must be tired of hearing this same condition over and over again, but yeah, you should keep this in mind whenever dealing with anything modular. But yeah, that is in our hand. But the thing is that after doing all this, whatever we're getting f of z prime, that is equal to f of z. So yeah, there is some kind of what to say, like constancy. The output does not depend on the input. The output is always constant. Input is z, but the output does not depend on z, because the output is also equal to z, right? So I mean, yeah, because you see, it's f of z prime. That means it's a function of z prime, and that is giving you the same result as is being given by a function of z. So that clearly means that the output of the function is always, I mean, it must be a constant function. Only the constant functions will satisfy this. Otherwise, a function of z prime and a function of z will not give you the same result. I mean, not in general, in any case. Yeah, so now as we have seen, the matrices S and T belonging to SL, they generate the modular group, the generator matrices I've already discussed. Now substituting the corresponding, so see, for S the value of A is 0, B is -1, D, C is 1 and D is 0. So we substitute, first let us do for S. So we substitute these values of A, B, C, D for S in this modularity condition. What do you get? See, A is 0 and B is -1, so -1 in the numerator, and in the denominator you get just Z, because C is 1 and D is 0. So f minus 1 over z equals z to the k, because c is 1, d is 0, z to the k f of z for s. And for t, see, everything is 1 except c is 0, so it's just z plus 1 over 1, that's z plus 1. So f z plus 1 equals to f of z, because yeah, c is 0, so and d is 1, so 1 to the k. So you see that t was this transformation, that it transformed z to z plus 1, and you see, if we put this in the modularity condition, we get that f z plus 1 is equal to f z. You see, and here we get that f of -1 over z is equal to z to the k f of z. Yeah, z to the k, this extra weight factor is there. Otherwise, this was z was transformed to -1 over z by the S matrix. Recall that we define a modular form for the modular group SL 2, C. Since S and T can generate this group SL, and the above conditions are equivalent to the modularity condition. Now since fz plus 1 equals f of z, modular forms are periodic functions with period 1. Of course, if sine x plus 2 pi equals sine x, so we say sine function is a periodic function with period 2 pi. Similarly, f of z plus 1 equals f of z, so it's a periodic function with period 1, meaning they can be expanded into a Fourier series. This is basic. You should know what a Fourier series is and Fourier transforms. I mean, Fourier series knowledge is enough for this video. Transform is not required, right? So see, for z belongs to capital H and k greater than equal to 4 and k even, we can define this series of weight k, which is known as the Eisenstein series. It's GKZ. I mean, capital G is just a way to denote the name of the series, and k is the weight of the series, and we take a k to be even and it's greater than or equal to 4. I mean, that's how we define it. It's the summation of this thing 1 over m plus nz the whole raised to the power k such that m and n belongs to z square. I mean, that means just m, just kind of like we define Cartesian coordinates x comma y. Similarly, m comma n, they're all integers, and m comma n not equal to 0 0. We just exclude the point 0 comma 0. That's all. So note that the series runs over all integers m and n provided they are not both 0 at the same time. Yeah, if m is non-zero, n can be 0 and vice versa, but they cannot be 0 at the same time. So as k is greater than or equal to 4, this series is absolutely convergent because k is greater than or equal to 4 and 1 over anything to the power something greater than or equal to 4. See, this is a basic result of series and sequences. Then this is always convergent. This summation, I mean this sequence, this series, the summation of this series, it's always convergent. I mean, it's absolutely convergent if since k is greater than or equal to 4. Now it can be proved that the above series, so since it's convergent, it satisfies that condition of this boundedness. It can be proved that the above series represents a modular form, and yeah, if it is holomorphic, that also can be proved, bounded, and follows the modularity condition. No, it's convergent is not the same as bounded. So yeah, to prove that it is bounded, we can break the series into two parts. First, for the case n is equal to 0 and then n is not equal to 0. So see, for n equal to 0, m is not equal to 0 and m belongs to, see, if n is 0, then automatically there is no, you don't need to bother about n. So this reduces to 1 over m to the k, and the conditions just become m belongs to z and m not equal to 0. Fine. Of course, m not equal to 0 because m is in the denominator. And the second case, the second part which we are dividing, plus summation m n belongs to m comma n belongs to z2 and n not equal to 0, because here the condition is n not equal to 0, and you don't need to write m comma n not equal to 0 comma 0, because if m not equal to n not equal to 0, then there is no restriction on m can be 0, m cannot be 0. You don't need to write it, right? And yeah, this is as usual 1 over m plus nz whole raised to the power of k. Now since k greater than or equal to 4, the first series converges to a finite value, of course, and as imaginary part of z tends to infinity, or as f tends to I infinity, already that was the boundedness condition. I mean, sorry, z tends to I infinity. Then the second series tends to 0. Why? Because you see, z tends to I infinity. So in the denominator there is z. So denominator there is infinity. So second series tends to 0. And first series is also convergent. So overall the sum of both the series is bounded. It's convergent as z tends to I infinity. See, this was the boundedness condition, right? You see, z tends to I infinity. Yeah, somewhere around, yeah, z tends to I infinity. Okay. So that means it's bounded. We proved it. We can also prove that Eisenstein series follows the modularity conditions. First, condition. Basically, see, the above conditions are equivalent to the modularity condition we wrote here, because this is the modularity condition in general. But since this S and T, since they can, I mean, they can generate all the members of the modular group, and since if we for the particular cases of S and T, from this general modularity condition we got these two conditions. So if we can show that these two conditions are being satisfied, then we can show in general that then we can tell that in general the modularity condition is being satisfied, because it's easier. Here is no A, B, C, D. Here is just Z. But here, if you cannot directly prove that this condition, because how will you prove for all values of A, B, C, D? That's why usually we prove this, and that is what we will be doing. That is why see, I have used the language modularity conditions. So both the conditions will be proven. First, we can fix m and replace z by z plus 1 in the Eisenstein series. We get a similar series because we are trying to prove that f of z plus 1 is equals to f of z. That is the second. I mean, that was one of the modularity conditions. See this one. I mean, see this one. F of z plus 1 is f of z. So just simply fix m and replace z by z plus 1. Yeah, just a second. Yeah. We get a similar series. We get the same thing actually, because see, the only change being the replacement of m by m plus n, because see here, look at the series m plus nz. So m is fixed and n is free to run, so that is m plus nz plus 1. Z is z plus 1, so that means m plus nz plus n. That means m plus n plus nz. So that means that is basically m plus, so you just replace m with m plus n and nz is there. So that is the thing. That is what we have, right? So just do this on the on pen and with on paper if you're confused. It's pretty simple. I mean, at times it might get confused because yeah, maths is not something you can hear and understand. You have to do it on paper as well or board, whatever. So see, we can prove, yeah. So we get a similar series, the only change being the replacement of m by m plus n. But see, for a fixed m, since m is fixed, and if we let n run through all the integers, clearly m and m plus n will both generate all the integers because m is fixed in any case. Suppose m is 0 is a trivial case, obviously, because if m is 0, then clearly m plus n and m, I mean, replacement of m by m plus n, but in the first case, originally m was not fixed. M itself was running through all the integers. In this case, m, we have fixed m, but n is free to run through all the integers. So m plus n. So if say n is 2, m is 2. So n, if when n is 0, then m plus n is 2. When n is 1, it is 3. I mean, ultimately for all the values of n, there will be a shift, but it will cover all the integers. So ultimately these series are equivalent. So gk z is equal to gk z plus 1. One of the modularity conditions we have already proved. And the second one, I mean this one, that f of minus 1 over z is equal to z to the k f of z. That can also be easily proved. We start by replacing z with minus 1 over z in the Eisenstein series and proceed as follows. So see, this is our series, Eisenstein series, and so we replace z with minus 1 over z. Here we do minus n over z to the k, and then we do some simple calculations, and we get this z to the k over zm minus n to the k. And now z to the k, see, m and n are being varied in the summation. Z and k can be easily brought out of the summation. So z to the k, and here we have summation, this thing 1 over zm zm minus n to the k. But if you write zm plus n to the k, and since the summation all m and n are running through all the integers, so ultimately both of these series are the equivalent series. They will generate all the integers, right? So ultimately we can do this, and then we are left with z to the k gkz. So gk minus 1 over z, z whatever, is equal to z to the k gkz. See, that was the other condition which we have also proved. So since Eisenstein series is a modular form, it's in fact the most simplest and one of the most popular modular forms. So note that since we span, this only have written, since we span all values of n belonging to integer, both zm minus n and zm plus n are equivalent. Equivalent, yeah. Also, we can interchange m and n since both represent the set of all integers and act like dummy variables. Interestingly, for a given weight k greater than or equal to 4, the set of modular forms of weight k is a finite dimensional vector space over the complex numbers. The set of modular forms of a particular weight is a finite dimensional vector space. This is finite, right? For instance, the space of modular forms of weight k equals to 4 is one dimensional, which means that there is really only one function that can satisfy these conditions up to scalar multiplication. All other functions that satisfy these conditions can be written as a scalar multiple of this one function, since the vector space is 1D. So modular forms also preserve multiplication. If f is a modular form of weight k and g is a modular form of weight m, fg is a modular form of weight k plus, I mean the weight will get added. Though these are getting multiple. I mean, anyway, these are just some for information, because these things I cannot explain now and not really relevant. I mean, not really possible to cover anymore. It's already 4 hours 70 minutes. Oh my god. And yeah, finally, just bear with me a little longer. I promise I'll finish the video before 4:30. I mean 4 hours 30 4 hours 30 minutes. So finally, congruent subgroups of the modular group. Yeah, if you start reading about modulus groups on the internet, you will, a term will come across quite often is congruent subgroups. And again, it's not difficult to understand, but it's difficult to I mean, confusions might arise initially. So here, let me tell you quickly what do we mean by congruence subgroups. We can define congruent subgroups for any group, but right now we are interested in the congruent subgroups of the modular group. Yeah, sorry, just a second. Yeah, okay. So a congruent subgroup of a matrix group, yeah, the elements of the group must be matrix only, yeah, I guess, whatever, with integer entries is a subgroup defined by certain congruence conditions on the entries. For example, a subgroup of invertible 2 by 2 integer matrix of element 1 in which the off diagonal, so this is basically the special linear group, but if we further put a constraint that the off diagonal entries are even, then this is a congruent subgroup of this special linear group. Off diagonal elements are even. That means this is the principal diagonal element A and D, and this is the off diagonal element B and C. So the principal congruent subgroup of level n, where n must be an integer greater than or equal to 1 of the modular subgroup, the modular group SL2 comma Z is given by. So this is the congruent subgroup of level n, principal congruent subgroup of level n. It's denoted by gamma n. It's again all the matrices belonging to SL, such that this is the congruence conditions: a comma d equivalent to 1 mod n and b comma c equivalent to 0 mod. Actually, see what we mean by this. See, this is the condition a comma t, this equivalent symbol 1 mod n, and this, they are congruence conditions. And what do they mean? More specifically, they are called congruence modulo n relations, and these relations are equivalence relations. This means that, see, if a equivalent to b mod n and c equivalent to d mod n, then these are all you can just verify. That's just mathematical relations. But yeah, what does this mean? That is what I'm trying to say. The condition a comma d equivalent to 1 mod n essentially translates to a equivalent to 1 mod n, read as a is congruent to 1 modulo n. Actually, it's congruent, not equivalent. A is congruent to 1 modulo n and d equivalent to 1 mod n. A comma d equivalent to this thing, this thing. Yeah, this means this and this together. If you want to express, you can write a comma d congruent to 1 modulo n, right? Since mod n applies to both sides of the equation, and see, mod n is not like it applies to both sides of the equation. So this means what? This means actually this a congruent to 1 mod n actually means a mod n equals to 1 mod n. If you want to transform this congruent to an equality symbol, then you have to apply mod n to both sides. So this is equivalent to saying a mod n is equal to 1 mod n, where a mod n is the remainder obtained on performing the division a over n, and 1 mod n is of course the remainder obtained by performing the division 1 over n. So these two remainders must be equal. Only such values of a are allowed. N is given. We are defining for that particular n the congruence level. So that means we are putting some constraints on the level of a, b, c, and d, and that is why it's a subgroup. And since the conditions are congruence conditions, it's a congruent subgroup of a group. In our case, we are considering the modular group. So this a comma d congruent to, just a second, where was that? Yeah, so a comma d congruent to 1 modulo n means a congruent to 1 modulo n and d congruent to 1 modulo n, which further means a modulo n equal to 1 modulo n and d modulo n equal to 1 modulo n. Both of these must be satisfied. And of course, a mod n means the remainder obtained on dividing a with a over n, and this is the remainder obtained on dividing 1 over n. And same for this, same for all this b, c, the second condition also. See, let's say a simple example. Suppose a is 13 and n is 5. Then what is a mod n? 13 divided by 5. If we do 5 divided by 13, so 5 2 is 10. The remainder is 3. So a modulo n will be 3, right? Since the division 13 over 5 gives a remainder of 3. 13 is 5 times 2, or 10 plus 3. Now clearly 1 mod n is always 1. Why? Because see, you're dividing 1 with n is 5, right? So okay. So 1 over 5. Provided n is not equal to 0, because 1 over 0 is undefined. 1 mod n is always 1. Why? Because see, 1 over 5. So that means what? 5 over 1. That means what? First of all, you cannot divide 5 by 1. So you 0 point. Then 10. So 5 2 is 10. 0 0.2. No, just a second. Yeah, like okay, let's take a simple example. As for say n is 2, so 1 divided by 2, we all know it is 0.5. So 1 divided by 2, that means first of all you try to divide. So 2 and 1 you have. So first of all you cannot do it, so 0 point, and then you have you add a 0, put a 0 after 1, so 10. Now 2 5 is 10, so 0.5, and then you have 10 gone, and then your remainder is 0. So 1 mod n is always 1. Oh, I'm sorry. We cannot we cannot do that, because we cannot bring fractions in here. We cannot do that, put a decimal or not. So 1 by 2 we have, right? So that means what we have to we have to write 1 in terms of 2. So 1 is equal to 2 times 0 plus 1. So remainder is 1, right? we must stick to integer. So that means, yeah, in that case 1 mod n is always 1, of course. If n is not equal to 0, because 1 over 0 is undivided. Say n is 3, then the division 1 over 3 gives a remainder of 1. Of course 1 over 3 is a fraction, but we cannot use that here. Here we have to express in terms of integer. So suppose 1 by 3, if you have to divide in terms of integer, suppose you have 3 and you have 1, and you cannot do any decimal, you have to divide in terms of integer, then what will you do? You will just 0, I mean 1 is what, 3 into 0 plus 1, so remainder is again 1. Whatever you do, 1 mod n will always be 1, right? Divisor will always be 0. So let's choose a equals 3, d equals 7, n equals 2. Clearly a mod n as well as d mod n is equal to 1 mod n, because what is a mod n is what? N is 2, so a is 3, so 3 divided by 2, that means 3 is 2 into 1 plus 1. So remember a mod n is 1. Then 1 mod n, okay, d mod n, d is 7 and n is 2. So 7 divided by 2, okay. 7 is 2 into 3 plus 1, 6 plus 1. So again d mod n is also 1. And 1 mod n, what is 1 mod n is always 1, we already discussed. So for a is 3, d is 7 and n is 2, it's satisfying this condition that a comma d is congruent to 1 modulo n. Okay. Now let b be 10 and c is 2, n is still 2, right? Since 0 mod n is always 0, yeah, why 0 mod n is 0? Because 0 divided by anything is 0 anyway, and otherwise if you try to express it like this, 0, suppose 0 over 3, then that means what? 0 is 3 into 0 plus 0. So whatever you do plus 0, I mean the remainder will always be 0. So that means b comma c congruent to 0 mod n, that means what? B mod n is equal to, should also be equal to 0, and c mod n should also be equal to 0. That is what the second condition is, second congruent condition is telling us. So we have chosen b to be 10 and n is 2. Of course 10 divided by 2, the remainder is 0. 10 is perfectly, I mean 2 5 is 10, and c is 2. Again 2 will also perfectly divide by with 2. So yeah, all of them are 0. So both the congruence conditions are being satisfied for n equals to 2 and these values of a, b, c, d. So that means for this, and see again ad minus bc, if we do ad is 3 7s are 21, bc 10 to the 10, I mean 10 to the 20, so 21 minus 20 is 1. Again this is also satisfied. So this matrix with these particular values of a, b, c and d, it's clearly a modular matrix, belongs to the modular group, and it is also satisfying the congruent conditions. So this matrix not only belongs to the modular group SL2 comma z, it also belongs to the congruent subgroup of level 2, because n is 2 of the modular group. It belongs, that means in short it belongs to this gamma 2 congruence, the principal congruent subgroup of level 2 of the modular group. This is not the only example, I just gave you an example. So all such matrices satisfying the required conditions from the principal congruent subgroup of level 2. Any subgroup of the modular group that contains the principal congruent subgroup is the congruent subgroup of the modular group. Any subgroup of the modular group that contains the principal congruent subgroup is a congruent subgroup. There are many possible congruent subgroup, but yeah, if the subgroup contains the principal congruent subgroup, then it is a congruent subgroup of the modular group. Mathematically, subgroup H of the modular group SL2 comma Z is called a congruent subgroup if there exists some n greater than or equal to 1 such that H contains the principal congruent subgroup gamma n. The level of H is the smallest such n. Now here we did for level 2, but ideally the level is the smallest such n. I mean, see here we just defined the principal congruent subgroup, but when we're given a random congruent subgroup, then yeah, subgroup H is called so when we're given a random congruent subgroup H such that it contains the principal congruent subgroup gamma n, then the level of H is the smallest such n. It can contain the principal congruent subgroup of level 2, level 4, level 5, level 6. So in that case, the level of the congruent subgroup, the level of the entire H will be 2, because smallest n is 2. Although maybe it may contain principal congruent subgroups of 3 also, 4 also, but we will not consider that. We will only consider the smallest n to define the level of this entire H. Now modular forms of level 1, that is modular forms defined over a level 1 congruent subgroup of the modular group, are essentially defined over the full modular group. Because the level 1 means what? N is 1, right? So that means a comma d congruent to 1 mod 1 and b comma c congruent to 0 mod 1. So they are satisfied for any a, b, c and d. I mean, see, 1 mod 1 means what? If you divide 1 by 1, the remainder will always be 1. If it, I mean, if it, see, if you divide 1 by 1, the remainder will be 0. If you divide anything by 1, the remainder will be 0. Right? 3 by 1, whatever we divide by 1, 3 by 1, what? 3 is 1 into 3 plus 0. When 1 times anything, you can generate the number. So this is clearly satisfied. And this is also satisfied because, see, 0 mod 1 is 0. And b mod 1, what is b mod 1? That is b divided by 1. C mod 1, that is c divided by 1. I mean, anything divided by 1, and again the remainder will be 0. So it's all 0. So both of this is satisfied. So uh, all a, b, c, d, for all values of a, b, c, d, it's valid. For in this case, you see, you cannot choose any value of a, b, c, d. You have to make sure that a, b, c, d satisfies this condition plus these two congruent conditions. I showed you a special example that for this particular choice 3, 10, 2, 7, it's satisfied, but not for all. But for the modular from, and this was for level 2, right? In fact, the higher and higher you go, the number of I mean, the constants will increase. I mean, for less and less a, b, c, d, you will I mean, the lesser the number of members in the principal congruent subgroup. Okay, see, for level 1 congruent subgroup, it's defined over the full modular group. It's essentially the modular group itself, because no a, b, c, d is left out. I mean, of course, as long as they are integers and satisfy AD minus BC equals to 1, but that is the condition of modular group only. I mean, no integer from the modular group is left. No matrix from the modular group is left out in the level 1 subgroup. This means the congruent subgroup of level 1 is the modular group itself. For n greater than 1, I mean, for higher levels, we can define modular forms that are defined over the corresponding congruent subgroup of the modular group. Clearly, congruent subgroups of the modular group are more constrained as compared to the full modular group, and thus more useful in the study of certain puzzling phenomena in high energy physics. I mean, suppose we have this particular phenomena for which we know these kind of constants. So we will apply these constants and work with only those congruent subgroups, because these congruent subgroups, they have a very little elements, they're constraints. But it's not possible, it's not easy to work with an infinitely large at the full modular group. I mean, at least from a physicist point of view, not from a general mathematician's point of view. Right. So I think I hope I could give you a basic idea of modular forms and everything, modular groups especially, not modular forms. Especially we discussed modular groups and the fundamental domain for modular groups. So that was all for this video. Hope you enjoyed the video, and I would like to hear your feedback, your suggestions, or whatever. If you're expert on the topic, I would like to hear. If I if I made any mistake, made any incorrect. Told anything, said anything incorrectly, please comment below if you're an expert on the topic, because I'm also learning this topic. And anyway, you can just comment below, share your thoughts, and hope you enjoy the video, guys. Thank you very much. Thank you.